Welcome students. In this class we will be starting off with a new topic called as differential equations. Now foremost, what is a differential equation? This is a very important question. What is a differential equation? So what's your answer for that? Now the answer is differential equation is an equation which involves differential coefficients or differentials. So having given this definition, we will see some examples. So I'm going to be listing out a few examples. The first example would be e to the power of y times dy positive e raised to the power of, say, 2 times x dx is equal to 0. Example number 2 would be d cubed x divided by, say, dt cubed positive sum n cubed x is equal to 0. So the variable here is t and the differential is d cubed x over dt cubed. Example number 3 is, say, 2 times y is equal to x squared times dy over dx positive 3 times x divided by dy over dx. Example number 4, I can have this to be as dy over dx raised to the power of, say, some 4. The entire thing is raised to the power of 5 over 2, and probably this is equal to e raised to the power of some 2x. And finally, one more differential I can give. Dou squared y over dou x squared is equal to e raised to the power of, say, some 3x dou squared y over dou t squared. So these are all some of the examples. Now example 1, 2, 3, 4, they are all called as ordinary differential equations. So let me write that down, ODE. And example 5 is called as partial differential equation. Now foremost, we will have to now understand the order. Welcome students. In this class we will be dedicating the session for doing questions related to order and degree of a differential equation. Now this is one particular topic which predominantly occurs in all forms of examinations, be it the high school level examination, graduate school examination, or even if you want to get into a research project. This particular topic keeps occurring on and on. Now, having mentioned about this particular topic, without any further delay, let me just recap what exactly the order of a differential equation. So the order, it is the highest differential that is present in a differential equation, right? So this is the first important point that you will have to know with regard to order. Now coming to degree, what exactly is degree? Now it is the highest power of the highest differential when, after converting the differential equation into polynomial form. So have that in mind. So what do you mean by polynomial form? We will have to remove the fractional powers. Okay, so we have got two important definitions which we will be using to answer and to solve questions related to order and degree. Okay, students, we've been given this question. We expected to find the order and the degree. Now, just to go and review the definition given for order. It is the highest differential that is present in a differential equation. Now, what is the highest differential that you can see here? This is dy over dx, but this is d squared y over dx squared. So, naturally, without any element of doubt, you can clearly state that the order is 2. But when it comes to degree, you will have to be a little bit cautious, because according to the definition, it is the highest power of the highest differential after converting the differential equation into polynomial form. So that means we will have to get rid of these fractional powers. So how are we going to do that? Now this has got a fractional power of 1 over 5. So what I will be doing, taking fifth power both sides. So this is going to be d squared y over dx squared. Now I'm taking fifth power both sides, and on the right hand side is going to be 2y positive dy over dx raised to the power of 6. This is 1 over 5. This entire thing has to be raised to the power of 5. So what happens when you do that? Clearly you can see the 5 and the 5 will be cancelled, and that would leave me on the right hand side 2y positive dy over dx raised to the power of 6, and on the left hand side it is d squared y over dx squared raised to the power of 5. So what does the degree state? It is the highest power of the highest differential. You can clearly see the highest power of the highest differential. This is the highest differential. So what's the degree? So the degree is 5. So that is the solution for this question, students. Students, let's do the next question. We've been given dy over dx positive 3 times y is equal to 1 over dy over dx. Now clearly you can outrightly state that the order is 1. But when it comes to degree, as I mentioned to you, you'll have to be a bit careful. Now this is not in polynomial form. To bring it in polynomial form, I would be multiplying both sides by dy over dx. So when I do that, I would get dy over dx raised to the power of 2 positive 3 times y times dy over dx, and when I multiply by dy over dx, this is going to be equal to 1. And of course I can bring this 1 to the left hand side, but it does not matter because this is already in the form that we wanted. Now clearly you can see this is the highest differential, and what is the power here? 2. So that would be the solution for this question. Students, we are given this question: negative e raised to the power of d squared y over dx squared positive 2 times x dy over dx positive y is equal to 0. Now the highest differential in this case would give me the order. So my order is equal to 2. Now but when it comes to the degree, we will have to represent this in polynomial form. So foremost what I wish to do is I would like to move this to the other side. So that means I would now have e raised to the power of d squared y over dx squared is equal to 2 times x dy over dx positive y. Now taking ln both sides, let me write that down. Taking ln both sides, we get. So what do we get? This is going to be ln of e raised to the power of d squared y over dx squared is equal to ln of 2 times x dy over dx positive y. Now we know that ln of a raised to the power of b is nothing but b times ln a, and we also know that ln e is, suppose the base is actually e here, right? So ln e to the base e will give us 1, and we also know that suppose you have something like this, ln e raised to the power of say some a, I can rewrite this as a times ln e, which is nothing but equal to a, right? So these are all some of the snippets that we will have to know. So first, what I wish to do is I would like to bring this down, okay, bring the quantity to the forefront using this law. Ln e raised to the power of a can be written as a times ln e. So I'm going to do that. So that's going to be d squared y over dx squared times ln e is equal to ln of 2 times x dy over dx positive y. Now ln e to the base e is equal to 1, right? So that would mean I get d squared y over dx squared is equal to ln of 2x times dy over dx positive y. So this is what we've got. Now the question comes, is this polynomial form? Yes or no? The answer is a simple no. Because when we talk about polynomial form, we do not have a presence of the logarithmic function involved. So what should be the answer in this case? So in this case, the degree is undefined. You can say not applicable, or you can use the word undefined. So depending on what choice that they are giving you. The problem in this case is that the derivative dy over dx is fused inside the logarithmic function. So that is the major issue. So because of that issue, that the derivative being stuck inside the logarithmic function, I am unable to represent this entire equation in polynomial form. Okay? So because of that, we have the degree to be undefined, or you can say not defined. We can use any of these things. So we'll move on to the next question. So we're given this question, we expected to find the order and degree. So we got tan inverse of dy over dx is equal to x positive 2y. And first and foremost thing that we need to do is we need to make sure that this equation is in polynomial form. So I'm going to rewrite this as dy over dx by moving the tan inverse to the other side. So that would mean I now have tan of x positive 2y. Now the first observation you will have to make or do here is to check for dy over dx, or for that matter any order of dy over dx, to see if it is fused in between any functions or so. Now clearly you can see here that there isn't any dy over dx present here, unlike the previous case. Now if you were to look at the previous case, you can see that dy over dx is actually inside another function. So that means we are unable to obtain the polynomial equivalence for this. And that is the reason we have arrived at a situation that the degree is undefined. But in this case, if you were to observe the question, clearly you can see that dy over dx is standing alone, and there isn't any dy over dx sandwiched between a third function. So that would mean I got the form that I'm looking for. So clearly you know that the order, the highest differential is 1, and the degree of the highest differential is also 1. So that is the end of the solution for this question. Students, we are given this question, ln of d squared y over dx squared is equal to a times x positive b times y. We are expected to find the order and the degree. So foremost, we will have to rewrite this in polynomial form. Now you might be wondering, oh, the differential quantity d squared y over d squared is present inside a logarithmic function. And we clearly have seen a question where d squared y over dx squared was fused inside a logarithmic function, and we immediately concluded that the degree of the equation was undefined or not defined. So I can say, use the same precedence that I have experienced to conclude that in this case also the degree is undefined. Well, before you could make that decision, you will have to ensure that you are firmly correct on your decision. So for that, the only criteria, or in other words, the yardstick that would help you to make sure that your decision is correct, is to convert this given equation into the polynomial form. So first make that attempt. Now clearly I know that if I've got something like this, say ln a to the base e, if it is equal to y, by logarithmic laws I can write this as a is equal to e raised to the power of y. Now using this law, I'm going to write this quantity as d squared y over dx squared is equal to e raised to the power of a times x positive b times y. Now the first thing that you will have to see here is, observe that if the differential operator, or for that matter d squared y over dx squared, or any order of differential, is sandwiched or it's caught between a third function or another function. Now clearly you can see that there is nothing that stops d squared y over dx squared being encircled by a third party function or by another function. Clearly I can see on the left side I only got d squared y over dx squared, and on the right hand side it's a quantity which comprises of terms without the presence of dy over dx or any differential operator. So that means we have obtained the form that we are looking for. So clearly we can find the order from here. The order in this case is the highest differential, so that's going to be 2. And in this case the degree is going to be the power of the highest differential, and that's going to be equal to 1. Simple as that. So that completes the solution to this question. Students, we will move on to the next one. Students, we are given this question, we are expected to find the order and degree. We are given one positive 3 times dy over dx raised to the power of 2 over 3 is equal to 5 times d cubed y over dx cubed. Now there is a fractional component here, so we will have to get rid of this and write this in polynomial form. So what I'm going to do is I'm going to be erasing both sides to third power. So if I were to do that, this is going to be 1 positive 3 times dy over dx raised to the power of 2 over 3. This is raised to the power of 3, which is equal to 5 times d cubed y over dx cubed. This is raised to the power of 3. Now clearly you can see that this 3 and the 3 here can be cancelled, giving me 1 positive 3 times dy over dx, and that has to be raised to the power of 2. In this case I get 5 cubed and d cubed y over dx cubed, and this is raised to the power of 3, right? So clearly you can see the order, this is 3, and the degree is nothing but the power of the highest differential, so that's also 3. So this is the solution to the question. Students, we are given this question, we are expected to find the order and the degree. Now the question is dy over dx is equal to 2 positive square root of dy over dx. Now you can clearly see that the differential operator dy over dx is actually caught within another operating function. So our main aim is to first disentangle the operator dy over dx. In other words, I would like to remove this dy over dx from the clutches So our objective is to remove this operator from the hold of the square root operation. So let's do that. So foremost, what I would do is I would like to bring this 2 to the left side. So if I were to do that, I would get dy over dx negative 2. On the right hand side, it's going to be dy over dx. So to get rid of the square root, I would have to square both sides. So if I were to square both sides, this is going to be raised to the power of 2. This is going to be raised to the power of 2. Now clearly you can see that the radical sign and the square, they get cancelled, leaving me with dy over dx. On the left hand side, this is a minus b raised to the power of 2, which is going to be a squared negative 2 times ab positive b squared. So if I were to use this expansion, this is going to be dy over dx raised to the power of 2 negative 2 times, and there is a 2 there, that means there's going to be 2 squared times dy over dx, and followed by 2 squared. So this is what I've got. Now clearly you can see that the highest derivative is of order 1, and the degree of the highest derivative here is 2. So this should be the solution. So you've got to be a little bit careful in handling this question. Now if in case they give another variation, say for example they have this like this, say d squared y over dx squared is equal to, say, negative 1 positive square root of dy over dx. Now as I mentioned to you, we will have to make sure that the required differential equation is in polynomial form. So I would have to move this negative 1 to the left hand side. So that would mean I now have d squared y over dx squared positive 1 is equal to square root of dy over dx. Now squaring both sides, what do we get when we square both sides? I would write it here. So this is going to give me d squared y over dx squared positive 1 raised to the power of 2 is equal to root of dy over dx raised to the power of 2. So clearly you can see that the radical sign and the 2 gets cancelled, leaving me with dy over dx on the right hand side. On the left hand side, this is going to be d squared y over dx squared raised to the power of 2 positive 2 times d squared y over dx squared positive 1. Now we are looking for the highest order differential. So clearly the order in this case is going to be 2, and the degree is nothing but the power of the highest derivative. So in this case the power is 2, so the degree is going to be 2. So prepare yourself, and most of the times when it comes to order and degree, these will be the problems that would predominantly be posed to you. So with this extrapolated exposure, I am sure with some amount of practice you will be able to click the things when it comes to order and degree. So we will move on to other related questions on order and degree, making sure that you are able to get a hit on. Students, we are expected to find the order and the degree for this particular question. We are given 6 times y double dash is equal to 7 positive y dash raised to the power of 2. The entire quantity is raised to the power of 5 over 2. Now we are not given terms like d squared y over dx squared, but instead of that we are given y double dash. Now this can also be confusing. Now foremost, what you have to do is you have to convert this into polynomial form. Now what prevents us from converting this into polynomial form is the presence of this fractional power. So I will have to get rid of that fractional power. How could I do that? By squaring both sides. That is the remedy. So if I were to square both sides, this is going to be 6y double dash raised to the power of 2 is equal to 7 positive y dash raised to the power of 2. Now this is 5 over 2. This entire thing is squared. So when it is squared, naturally the 2 and the 2 gets cancelled. Why does it get cancelled? Suppose you got a quantity like a raised to the power of m over n, and you are taking it to the power of n. Then by the law of indices, this can be rewritten as a raised to the power of m over n times n, which means I can still further rewrite this by cancelling the n as a raised to the power of n. So that's from the law of indices. So having obtained the output, we need to formulate this. So this is going to give me 6 squared times y double dash raised to the power of 2 is equal to 7 positive y dash raised to the power of 2, that is raised to the power of 5. Now this has got no significance to the order or to the degree in this particular question, because we are always concerned with the highest differential. So if I were to look into the highest differential, clearly the order of this differential is 2. So we can just place the value there. So let me just go and place the value 2 there. And what is the power in which it is raised? That gives the value for the degree. So that solution is going to be 2. So that completes the solution for this question. Students, we will move on to the next question. Students, we are given this question: d cubed y over dx cubed, this is raised to the power of 2 over 3, is equal to dy over dx positive 5, and we are expected to find the order and the degree. Now foremost, the best thing to do is to get rid of this fractional power and then write it in polynomial form. So for that I need to remove this 3. So I would be cubing both sides. We get, so this is going to be d cubed y over dx cubed. This is raised to the power of 2 over 3. Now I'm cubing this term, so I get a 3 there. This is going to be equal to dy over dx positive 5, which is raised to the power of 3. Now clearly from the law of indices, I can cancel the 3 that you see here, and that would mean I would now have d cubed y over dx cubed raised to the power of 2 is equal to dy over dx positive 5 raised to the power of 3. Now from here, clearly I can see that the order is 3. I can write that. And then the degree is nothing but the power that the highest differential has. So in this case, the power is 2. So that completes the solution for this question. So we'll move on to the next question, students. Students, we are given this question: y equal to 1 positive dy over dx positive 1 over 2 factorial times dy over dx raised to the power of 2 positive 1 over 3 factorial times dy over dx raised to the power of 3 positive, etc. up unto infinity. So this is actually an infinite series. Now this has got a lot of correspondence with our e raised to the power of x series, which is nothing but 1 positive x over 1 factorial positive x squared over 2 factorial positive x raised to the power of 3 over 3 factorial plus up unto etc. It goes up to infinity. So this is a very important series, and we will try to use this series to solve this question. So if I were to take x to be as dy over dx, then I can clearly see that all I need to do is to substitute in place of x dy over dx, and I would get this entire series dy over dx positive 1 over 2 factorial times the dy over dx raised to the power of 2 plus etc. So clearly we can see that I can write y to be as e raised to the power of dy over dx, but this is not in polynomial form because of the presence of this exponential. To get rid of the exponential, we will take natural log on both sides. So this is going to be ln y is equal to ln e raised to the power of dy over dx. This is going to be dy over dx, and on the left hand side is going to be ln y. So clearly we see the differential operator is not within or inside any function, so this is acceptable. So this is the only differential that we have got, so therefore we can state that order is equal to 1 and the degree is equal to 1. So this completes the solution to this question, students. Students, we given this question, we expected to find the order and the degree. Now this question can be very tricky. Now because we got the degree, or I should say we got the entire component b raised to the power of 5, and on the left hand side we got x cubed times d squared y over dx squared. Now if you were to observe this, this is exactly in the polynomial form, and also it is imperative to observe that the differential operator is not inside any other third function. So this is a straightforward question. All you need to do is to find the highest differential. In this case is d squared y over dx squared, so the order is going to be 2 here, and then followed by that find the power to which the highest differential is raised. So in this case it is raised to power 1, so that would be my degree. That's it. This is the end of story for this question. So we got this question, we expected to find the order and the degree. The question is d squared y over dx squared positive x squared times dy over dx raised to the power of 2 is equal to 3 times x cubed times log of d squared y over dx squared. Now if you were to make an observation here, your focus should fall on this right hand side, because you can see that d squared y over dx squared is entangled within logarithmic function. So that would mean if you were to, or if you want to find the degree, you should remove this logarithm. In other words, you have to remove the differential operator d squared y over dx squared from the logarithmic function in which it is present. So how are you going to do that? Because the logarithmic function is directly covering the differential operator d squared y over dx squared. So in that case, at the most what you can do is you can move this 3 times x cubed down as a denominator. That's it. If you want to remove this logarithm, even if you were to manipulate the left hand side, the logarithm will still come haunting back either to the left side, or it would manifoldly augment its tentacles, because of the fact that the logarithmic function is holding on to the differential operator d squared y over dx squared. So in other words, what I'm trying to convey here is it's just not going to be possible for you to get the polynomial form, and that would mean our degree is not going to be present there. So for that, let me start off with the order. Clearly the highest differential present here is 2, so I can write that 2. In case of the degree, as I mentioned to you, the only feasible solution is going to be not defined. So that's it. So this is going to be our solution for this question. Welcome students, in this class we will be learning about formation of differential equations. Now it is a very important topic. Now the first and foremost question is, so how and when do we come across or forming a differential equation? Now this happens when you are given family of curves, and from the family of curves you are asked to obtain a differential equation. Now how are you going to do that? Now between the family of curves and to forming a differential equation, there is a process which we call it as differentiate. So what is the meaning of this? The meaning is, if you are given a family of curves and you are asked to obtain a differential equation, then you will have to use the concept of differentiation to extract or to obtain the differential equation. So having mentioned this, what if you are given a differential equation and you are asked to obtain the family of curves? In that case, you will have to perform the action of integration. So let me reiterate one more time. You're given a family of curves and you're asked to obtain a differential equation. Then the action that is required from you to achieve the requirement is to differentiate. On the contrary, if you're given a differential equation and you're asked to obtain a family of curves, the action that is expected from you is integration, or you can use the word integrate. Now, having mentioned this, let us move on in achieving from the family of curves the required differential equations that has been associated with the family of curves. Now, it is imperative to understand that every family of curve has a unique differential equation associated with. So have that in mind. Let me reiterate one more time. Every family of curves has a unique differential equation associated with. In other words, no two family of curves will share a differential equation. Have that in mind. So unique is a very important keyword that you will have to take into account. So we are given this question, y is equal to mx, and we are expected to form the differential equation. So foremost, what we got to do is we will have to start off with differentiating this with respect to x. So when we do that, this is going to give me dy over dx. M is a constant. Differential of x will give me 1. So now I can rewrite m to be as dy over dx. Now what is the idea? The idea is whenever you are asked to form the differential equation, you have to get rid of this arbitrary constant. So that is your basic idea. Now I've got this m is equal to dy over dx. Now if I were to take this as 1, therefore I can rewrite 1 as, now I've got this y is equal to mx, right? So I'm going to rewrite this as y over x is equal to m. And then I can safely use, now since m is, this is for your understanding, you don't have to write all these things, okay? Since m is dy over dx, this would imply that y over x is equal to dy over dx. So this is my final solution, right? So clearly you can see that I have got rid of m. Probably you can either stop here, or depending upon your requirement, you can rearrange this. So you can simply say, you can either stop here, or you can say that y is equal to x times dy over dx. You can either write it like this. So whatever is the requirement, based on that you can formulate or form or present the solution. Now on the contrary, if you are given this y over x is equal to dy over dx, so let me have this as a question. Okay, you are given y over x is equal to dy over dx, and you are asked to form the family of curves. So how are you going to do that? Now, as I mentioned to you in the start of this class, if you are given the differential equation and you are expected to obtain the family of curves, then all you have to do is to integrate. So that is exactly what we are going to do. So from here, I'm going to rewrite this. Let me start off by presenting the problem. Y over x is equal to dy over dx. Now by using variable separable, which I have already explained to you, we had a class before this. So I'm going to rewrite this as dx over x is equal to dy over y. Now I will be integrating both sides. Integral of dx over x will give me ln x. Integral of dy over y will give me ln y. Of course, there is a presence of an arbitrary constant. Now I can either place the arbitrary constant on this side, or I can place it on that side. I like to place the, I don't want to place the arbitrary constant here. I will place the arbitrary constant on the x side. So that this is going to be ln y negative ln x, and on the left side you got ln c. It's all constants. Why am I using ln c? Because you have a logarithm here, so that should also involve a logarithm because I can clearly remove the logarithm from the constant. Now, I got a formula. What is the formula? Ln A negative ln B. I can rewrite this as ln of A over B. So by this, what I can do, I can rewrite this as ln of Y over X. On the left, I got ln C. Now, I can clearly remove the logarithm from both sides, and then I can write this as Y over X is equal to C. Now, this C can be anything, right? I can also write this C to be as some constant M, and then subsequently rewrite this as Y is equal to mx. This is what will be the final solution, where I can say that M is an arbitrary constant. So this is one of the ways that you can obtain this. Probably you can also simplify it in other ways, but no matter in what way that you're simplifying, the family of curves will be Y is equal to mx. So this will be the final solution. So having mentioned this, let us move on to other questions, students. Now I would like to give some points to remember. So these are important things that you will have to have it in mind, points to remember. The first one is every family of curve has a unique differential equation associated with it. As I mentioned to you, this is the first point I mentioned to you, right? So no two families will have the same or will share the same differential equation. So have that in mind. So number two, the number of arbitrary constants, the number of arbitrary constant present in the family of curves reflects the order of the differential equation. So what is the meaning of this? So in the previous case, you can clearly see that we started just with y is equal to mx, and there is just one arbitrary constant. And the differential equation that we got is dy over dx is equal to y over x. Now clearly you can see the order of the differential equation over here. The order is actually equal to 1. Why is it equal to 1? Because we add just one arbitrary constant present here. Now if in case we would have to have, say, probably two arbitrary constants, then the order of the differential equation would become equal to 2. So this is a very important point. The number of arbitrary constants, I can place an S, present in family of curves reflects the order of the differential equation. So have that in mind. So having got this, point number 3, when you form a differential equation, the differential equation formed should not contain any arbitrary constant. Okay, this is a very important point. So whenever you have a differential equation that is being formed, you should not have the presence of any arbitrary constant. So these 3 points which I have given you are vital and key for the study of this particular topic. So we'll move on to the next. Students, we are given this question: form the differential equation which represents the family of curves y is equal to c1 times e raised to the power of c2 times x, where c1 and c2 are arbitrary constants. So what are we given? We are given that y is equal to c1 times e raised to the power of c2 times x. Now we have two arbitrary constants, so the order of the differential equations is going to be equal to 2. So that is the important observation that we will have to take into account, and that would mean we will have to perform 2 times, or in other words, we will have to perform twice differentiation, right? So now first what I will do is I will differentiate with respect to x. So when I do this, this is going to be y dash is equal to c1 as an arbitrary constant. Differential of this would give me e raised to the power of c2 times x. However, the coefficient of x is c2, so place it there. Now I can rewrite this as c2 times of c1 e raised to the power of c2 times x. Now clearly c1 times e raised to the power of c2 times x is actually equal to y. So I can write this as c2 times y. On the left hand side it's going to be y dash. Now what I wish to do is I would like to differentiate this again with reference to x. So this is going to be y double dash is equal to c2 is a constant times y dash. Now this is equation 2, this is equation 3, and this original one is equation 1. So now what I wish to do is I would like to divide 2 by 3. Now when I do that, dividing 2 by 3, what do I get? I get y dash divided by y double dash is equal to c2 times y divided by c2 times y dash. Now clearly c2 can be cancelled, so this would mean I got y dash divided by y double dash is equal to y over y dash. I cross multiply this, I would get y dash raised to the power of 2 is equal to y times y double dash. So this is my final solution to this question. Students, we are given this question. We are expected to find the differential equation of all circles passing through the origin with center on the x-axis. So let us get the circle drawn first. So this should be the x-axis we are talking about, and the y-axis is over here. This is the origin. Now the circle is passing through the origin with center on the x-axis. So approximately this would be the circle. Now the center is given to be on the x-axis, so probably you can have a center as some a comma 0. So that would mean the radius will be from this particular 0 comma 0 to the center. So if we were to write the equation of the circle, then the equation of the circle would be x negative a raised to the power of 2 positive y negative 0 raised to the power of 2 is equal to some a squared. If I were to expand this, I get x squared negative 2 times ax positive a squared positive y squared is equal to a squared. Now clearly I can see the a squared can be cancelled. I now have x squared positive y squared is equal to 2 times ax. Now I need to form a differential equation. So what I will do, I will be differentiating with respect to x, and that would give me, say, 2 times x positive 2 times y dy over dx is equal to 2 times a. Now I can cancel the a's that you, the 2's that you see here, and that would in turn give me x positive y times dy over dx is equal to a. Now our aim is to eliminate this arbitrary constant a. So if I were to take this as, say, 1, so I can say, therefore I can rewrite 1 to be as x squared positive y squared it's equal to 2 times, in place of a I will have to substitute x positive y times dy over dx is equal, there is a multiple of x there, so probably I can place an x over here. So this should be the differential equation that we are looking for. Now if you want to simplify, you can do that. I can rewrite this as x squared positive y squared is equal to 2 times x squared positive 2 times x y dy over dx. I can keep the y squared here, move the x squared to the other side. So that would give me y squared is equal to 2x squared negative x squared will give me x squared followed by positive 2 times x times y dy over dx. So depending upon the requirement, you can afford to stop. So either over here or over here. If you find this to be as a choice in the MCQ, you opt for this. If you find this to be as a choice, you opt for this. Students, we are given this question. The differential equation whose solution is ax squared positive by squared is equal to 1, where a and b are arbitrary constant. Now we are expected to find the order of this differential equation as well as the degree. Now the order can easily be obtained from here. You see that it has got the presence of 2 arbitrary constants. So if the constant is 2, the arbitrary constant is 2, then the order should be 2. But the only point here is how are we going to obtain the degree? So that is critical. So now that is our objective. So let us just start off by saying consider a times x squared positive b times y squared is equal to 1. So what I will do is I will be differentiating this with respect to x. So when I do that, this is going to be 2 times x times a positive 2 times y. Of course, differential of y is going to be y dash times b is equal to 0. Now clearly I can get rid of this 2 that you see here. So that would mean I would have, say, x times a positive y times y dash times b is equal to 0. Now what I would like to do is I would like to divide by b throughout. So this would give me a over b, right, times x positive y into y dash is equal to 0. So let me take this as 2. Now from here, okay, let me have this as 1. Now I'm going to be differentiating 1 with respect to x again. Why am I differentiating it again? Because I've got presence of 2 arbitrary constants. So that's the reason, simple fact. Now when I do that, differential, I'm not choosing this, I am using this, or in other words, I have formulated this because I would like to get rid of this a over b. So that's the reason I have written it like this. But for all other purposes of differentiation, I would be using 1. So if I were to differentiate a times x, I would get a positive. Now y into y dash into b. B is an arbitrary constant that is holding on to y into y dash. So now I will have to differentiate y times y dash by ub method. So u times differential of y dash, that's going to be y double dash, plus v times differential of u, that's going to be differentiation of y, which is going to be y dash, is equal to 0. Now I can rewrite this as a positive b times of y into y double dash positive y dash raised to the power of 2 is equal to 0. Now I will be dividing by b, so this is going to give me a over b positive y into y double dash positive y dash raised to the power of 2 is equal to 0. Now from here I can clearly write a over b. Now a over b is equal to negative times of y into y double dash positive y dash raised to the power of 2. So this is what I've got. So clearly I can rename this as 3. So what I'm going to do is I'm going to use 3 in 2. So if I take the value of a over b and substitute here, then we have obtained what is really required. That is exactly what I'm going to do. Probably I can use the space over here. Let me just draw this off. So I'm going to say using 3 into, right? So that's exactly what I'm going to do. So I'm going to use 3 into, in place of a over b, I'm going to substitute this. So that would mean I can say therefore 2 can be rewritten as x times, in place of a over b, I need to substitute this. It's going to be negative y into y double dash positive y dash raised to the power of 2 positive y into y dash is equal to 0. So this is what I've got. Now the requirement is find the order and the degree. Now clearly I know the order is 2, right? So I can clearly see that. You see y double dash, the order. Probably what I can do is I can place one more parenthesis because of the fact that this is actually negative sign, though it doesn't matter in case if they trip, or I should say if they require something else additional to that, then we will have to take those things also into account. However, in this case it isn't required, but yet if in case the choice is featuring this, then we will have to be careful. So clearly this negative sign is outside of this entire quantity. Okay, coming back to the order. What is the order here? Clearly I can see is equal. What is the degree? What is the highest power raised here for the highest order? So in other words, what is the power of the highest order? That is what is required. That is going to give me the degree, right? So what is the degree here? Degree is going to be 1. Students, we are given this question: the differential equation representing the family of curves y squared is equal to 2 times c of x positive root of c with c greater than 0 is of dash order and dash degree. So you are expected to find the order and degree in this case. So let me start out by writing the given quantity. So we are given y squared is equal to 2 times c times x positive 2 times c times the root of c. Now what I would do is I will first differentiate this entire thing with reference to or with respect to x, and we would be getting the following. Differentiation of y squared is going to be 2 times y times dy over dx. So what I will do, I will place y dash there is equal to 2 times differentiation of x will give me 1. So I got just 2c there. So now what I can do, I can cancel the 2's there. So therefore I will have c is equal to y into y dash. So clearly, since there is a presence of one arbitrary constant, I can zero it as the order being equal to 1. But that is not going to be enough for us to find the degree. So for getting the degree, what I'm going to do is I'm going to be taking the value of c and I'm going to substituting it into this system that we have got. So what I will do is I will take this as 1. Therefore 1 can be rewritten as, I'm going to take the value of c and place it here. So it's going to be y squared is equal to 2 times c is y into y dash times x positive 2 times my c is y into y dash times, again this is going to be root of c, right? So it's going to be y into y dash raised to the power of 1 over 2. Now I got a 1 over 2 and I got a 1, so I can add them down. So that's going to be 2 times x times y into y dash positive 2 times y into y dash raised to the power of 3 over 2. Of course I got here y squared. Now from here I wouldn't be in a position to find out what exactly the degree is. It's not possible. So for that I will have to convert this entire thing into polynomial form. So let's do that. So foremost what I would like to do, I would like to push this 2 times x y into y dash to the left hand side, and that would give me y squared negative 2 times x into y dash, and this is equal to 2 times y into y dash raised to the power of 3 over 2. Now I want to get rid of this 3 over 2, so what I would do is I would be squaring both sides. Now when I square both sides, what do I get? I get y squared negative 2 times x times y into y dash raised to the power of 2 is equal to 2 times y into y dash raised to the power of 3 over 2. This is raised to the power of 2. Now this is going to give me 4. The 2 that you see here would be cancelled, so that in turn would give me y into y dash raised to the power of 3. On the left side I get a y squared negative 2 times x into y dash raised to the power of 2. So this is what I've got. Okay, now y dash is the differential which we are looking for, so clearly the order is equal to 1. Now when it comes to the degree, now clearly you can see that you have a 2 here but you got a 3 here. So degree is nothing but the highest power of the highest order differential. So the highest power in this case is going to be equal to 3. So the solution here is 3. So that would be our conclusive reply or answer for this question, student. Students, we are given this question. Consider the family of circles whose center lie on the straight line y is equal to x. If this family of circles is represented by the differential equation p times y double dash positive q times y dash positive 1 is equal to 0, where p and q are functions of x, y and y dash, then we are expected to find the coefficient of y double dash, which is actually p in this case. We have to obtain the value for p and the value of p positive q. So what I would do is I will start off, since it is a family of circles, what I will do is I will take a point. Let C of a comma a be the center, okay, for the circle, and I'm going to take the radius to be equal to some r. So therefore the required equation of the family of circles is going to be x negative a raised to the power of 2 positive y negative a raised to the power of 2 is equal to r squared. So I've got this. What I wish to do is I will have to differentiate. So let me just differentiate this with respect to x. So there's going to be 2 times of x negative a times differentiation of x, that's 1, positive 2 times of y negative a times differential of y is going to be y dash. R squared is going to give me 0. So from here I can rewrite this as 2 times x negative 2 times a positive 2 times y dash negative 2 times a times y dash is equal to 0. So what I would do is I would, in fact, I can get rid of the 2 all through here. So if I were to get rid of this 2, I am going to have x positive y times y dash. I'm going to push this to the other side. It's going to give me a times y dash, positive sign, and then followed by a positive a. Okay, so I've got a and a, and my intention is to get rid of this a. Right, so let me have this system 2. This is going to be system 2, this is my system 1. So now I would like to differentiate this again one more time. So let me state that differentiating this with respect to x again, differential of x is 1. Now UV formula should be applied. So y into y double dash positive y dash into y dash differentiation of y is equal to a times y double dash. So differential of this a is going to be constant. Now clearly from here I can isolate a. So I can rewrite this as 1 positive y times y double dash positive y dash. So that's going to be y dash raised to the power of 2 divided by y double dash is equal to my a. Now from here what I can do is I can actually make the substitution for a in 2. So if I were to take this as 3, using 3 in 2 we get. So now what is this? This is actually, I can rewrite this. I'm going to rewrite this. I'm going to rewrite this as x positive y into y dash is equal to a times of y dash positive 1. Right? So all I need to do is take this a and substitute it there. So that's exactly what I'm going to do. So clearly I can state here. So 2 can be rewritten as x positive y times y dash is equal to this quantity 1 positive y into y double dash positive y dash raised to the power of 2, that's my a, divided by y double dash times y dash positive 1. So I can rewrite it as 1 positive y dash. If I were to cross multiply, this is going to give me y double dash times x positive y into y dash is equal to, now I can use the distributive property and remove everything off because that is what is required. I would take 1 positive y dash and I multiply it with 1 and take 1 positive y dash, multiply it with y into y double dash and take one positive y dash and then multiply it with y dash raised to the power of 2. This is what I'm going to be doing. Now what I will do is I will have to turn a fresh page for our calculation. So this is equal to, on the left side I got y double dash times x positive y into y dash. On the right side I'm going to rewrite it as 1 positive y dash, positive y into y double dash, positive y double dash times y dash times y, positive y dash raised to the power of 2, positive y dash raised to the power of 3. So this is what I've got. So now the requirement is we have to do some class. We should actually extract p times y double dash positive q times y dash positive 1 is equal to 0. So we will have to achieve this form. Now on the left hand side we have got y double dash times x positive y double dash times y dash times y is equal to this entire component. Now clearly you can see that I got a y double dash, y dash and y, so I can cancel these two things and that would give me 1 positive y dash, positive y into y double dash, positive y dash raised to the power of 2, positive y dash raised to the power of 3. So this is what I've got. Now clearly what I'm going to do is I'm going to take y double dash out. If I take y double dash out, I get a y and I would get x over here. In fact, if this thing comes over here, this is not going to be positive, it's going to be negative, right? So I need to place the negative sign there. And then I would like to take y dash. So y dash, if I were to take y dash, now there is a y dash here and followed by a y dash and then followed by a y dash raised to the power of 2, right? So what have we done? We have got rid of this, we have got rid of this, we have got rid of this, we have actually got rid of this also, right? But there is a positive 1 there, so let's place that positive 1 there, and on this side it's going to be equal to 0. Now we can rewrite this. Rewriting, we get, so what do we get? We get, I'll start with y double dash of y negative x positive y dash of 1 positive y dash raised to the power of 2 positive 1 is equal to 0. So this is what is required. Clearly the value of p is y negative x, and we can also obtain the value of q, probably p positive q, whatever that is required. Now clearly we can see the value of q is 1 positive y dash raised to the power of 2. Now from here, if they are asking p positive q, my p is y negative x, positive q is 1 positive y dash raised to the power of 2. If you want to rewrite this, you can rewrite this as 1 followed by negative x and then a y and then a y dash and then a y dash raised to the power of 2. So this is my p positive q. So this is a beautiful question. We have achieved it. And we'll move on to the next question. Students were asked this question: the degree and order of a differential equation of the family of parabolas with the axis being given to be present on the x-axis. So this is the axis of the parabola, right? The axis of the parabola is found to be lying on the x-axis. So if you were to draw the parabola, then the parabola's shape would be something of this fashion, and the coordinates present here over here, this is going to be p comma some 0. So this is the parabola we are talking about. So the equation of the parabola in this case is going to be y negative 0 raised to the power of 2 is equal to some 4 times a x negative p. Okay, so using this we will have to get rid of the constants. So this is going to be y squared is equal to 4 times ax negative 4 times a times b. I'm going to differentiate this with reference to x. This is going to give me 2 times y times differential of y is going to be y dash is equal to 4 times a, differential of x is 1. This will vanish. So from here I can clearly get rid of this 2, and I would hence y into y dash is equal to 2a. I will have to apply UV formula, and this is going to be y times y double dash positive y dash times differential of y is going to be y dash is equal to, this is a constant, I get a 0, so I get y into y double dash positive y dash raised to the power of 2 is equal to 0. They wanted us to get the degree first and then the order for this question. So clearly the degree is the highest quantity or the highest number that is present on the highest order differential. So in this case the degree is 1. So place 1 here and the order is 2. So make sure to observe what is required first. In this question they wanted the degree to be placed first and followed by the order. So that is the conclusion for this question, students. Students, we are given this question. The question is, we are expected to form the differential equation which is representing the family of parabolas with the axis parallel to y-axis and whose lactus rectum, in fact whose length of the lactus rectum is the distance of the point 2, negative 3 from the line 3x positive 4y is equal to 5 is given by. So we are expected to form the differential equation. Now there are a few things that we will have to know. Now the first thing is the shape of the parabola where the axis is parallel to the y-axis. So this is case 1. I'm going to give you 2 important cases. Axis parallel to y-axis. So that parabola would look something of this nature. Okay, so this is x-axis, this is y-axis, and if you were to draw the parabola, then the axis is parallel to y-axis. So this would be the axis of the parabola. So if this is going to be the shape of the parabola and these two are the axes, but the major axis that we are talking about is this one. This is the major axis because that would be the axis of the parabola. Now the equation for this would be of this fashion: x negative alpha. Now when we say alpha comma beta to be the vertex, so that's exactly what we have to be represented here. So there's going to be x negative alpha raised to the power of 2 is equal to 4a times y negative beta. So this is going to be one family of parabola whose axis is parallel to y-axis. So this is very important. Now 4a, this is the lactus rectum. Now I'm going to show you how to calculate the lactus rectum in the following section. Now after this we will have to go for the case 2. Now what is case 2? Now case 2 is the axis parallel to x-axis, right? So what would the parabola look like? Suppose we are talking about a parabola which has its axis parallel to the x-axis. So let me just draw that here. So this is going to be my x-axis and y-axis. So I'm basically talking about an axis parallel to the x-axis. So this is the axis of the parabola. Now since it is parallel to x-axis, the shape of the parabola in this case would look something like this. Okay, this will be the shape, and probably you can take this point as some p comma q. Now if this point is some p comma q, then the equation for this parabola would be y negative q raised to the power of 2 is equal to 4 times a x negative p. Alright, if you remember the previous question, in previous question we add a parabola of this form and we add y negative 0 raised to the power of 2 is equal to 4a times x negative p. This to be the equation because p has been the coordinate, p comma 0 is the point on the x-axis. In this case it's on the x-axis, but in this case this is actually the axis of the parabola is parallel to x-axis, so this would be the shape, right? And the coordinates would be p comma q, and that is the reason instead of 0 being here we got a q here, because this is the vertex of the parabola. So y negative q raised to the power of 2 is equal to 4a times x negative p, where the latus rectum is 4a. So we got two families of parabolas, which is very critical and very important as far as problem solving is concerned. So we will move on to the next. This question we would be using x negative alpha raised to the power of 2 is equal to 4a times y negative beta. So this will be the required family of curves. Apparently we will have to find out the latus rectum. Now it is given in the question that the length of the latus rectum is the distance of the point 2 comma negative 3 from the line 3x positive 4y is equal to 5. So what I would like to do, I would like to find the magnitude. So in this case all I need to do is to take the value for x as 2 and y as negative 3 and substitute it in this equation. 3x positive 4y negative 5 is equal to 0. So, and then I need to find the magnitude. So this is how we need to do that. So the latus rectum is equal to 3 of 2 positive 4 of negative 3 negative 5 divided by 5, and this is going to give me 11 over 5. Now take the latus rectum 11 over 5 and substitute it over here. So that's exactly what we're going to do. So this is going to be x negative alpha raised to the power of 2 is equal to 11 over 5 times y negative beta. Now I will be differentiating this with reference to x or with respect to x. So differentiating this with respect to x, we would get 2 times of x negative alpha into differential of x, that's 1. 11 over 5 is a constant, so I differentiate y, it's going to give me y dash. So now I have got 2 times x negative 2 times alpha negative, it is equal to 11 over 5 times y dash. Now I need to get rid of this alpha, which I can do by differentiating this again with respect to x, and that would give me 2 is equal to 11 over 5 times y double dash. So you can either write it like this or you can write it like this. 10 is, you can cross multiply and write it as 10 is equal to 11 times y double dash, or you can write it like this, 11 times d squared y over dx squared is equal to 10. So both these things are okay, but however depending upon what is present in the choice. So that is the end of the solution for this question. Welcome students, in this class we are expected to find the order of the differential equation of the given family of curves. Now of course you will be thinking that, well, the number of arbitrary constants would give us the order. First and foremost technique that we need to adopt here to find the order of the differential equation is that we will have to first simplify the given system, and then we will be able to see the true picture. So that is exactly what I'm going to do. I'm going to rewrite this as C1 times e raised to the power of C2 times e raised to the power of x positive C3 times e raised to the power of x positive C4 times e raised to the power of x. Now from here what I would do is I would rewrite by taking e raised to the power of x out. So if I were to do that, I would get C1 times e raised to the power of C2 positive C3 positive C4 times e raised to the power of x. Now you can clearly see that I can always replace this entire quantity by means of a single arbitrary constant. So in other words, I am just left with a system which has just one parameter in place. So the order in this case will be equal to 1. As we are given the question, we are expected to find the order of the differential equation of the family of circles touching the x-axis. Now let us visualize this question. So we got the x-axis here. Now we are talking about all circles which are touching the x-axis. So we can have a circle like this, it touches the x-axis. We can have a circle like this, it touches the x-axis, and we can also have circles like this which is touching the x-axis. Now we can draw infinite number of circles. Now what is the most important point that we will have to observe here is, say for example, if this point is say some a comma 0 and the point over here, the radius is say 3 units, right? Now clearly if you want to know the coordinate of the y-axis, in this case it is going to be a comma 3, right? The point over here is going to be a comma 3. Now if you were to draw the equation of the circle touching the x-axis, what would be the equation in this case? Now clearly we know that if a comma b be the center of a circle, then the equation of the circle would be x negative a raised to the power of 2 positive y negative b raised to the power of 2 is equal to r squared, right? Because a comma b is the center of the circle. So in this case, what would be the equation of the circle? So that's going to be x negative a raised to the power of 2 positive y negative 3 raised to the power of 2 is equal to r squared. Now what is my r squared? My r squared is going to be my 3 squared. So in other words, what are we talking about here? The center for any circle which touches the x-axis would always be, the equation of the circle would always be x negative a raised to the power of 2 positive y negative r raised to the power of 2 is equal to r squared. This is going to be the equation of the circle touching the x-axis. So what is the number of parameters that you can see here? So the number of parameters that you can see here is 1 and 1, 2, and that would mean the order of the differential equation is going to be equal to 2. So that is the end of the solution for this question. We will start off this class by performing problems on variables separable. Now it is important for us to understand the concept of variable separable by means of a definition. So this is the definition we will have to understand. So if in an equation, if it is possible to collect all functions of x and dx on one side and all functions of y and dy on the other side, then we say the variables are separable. And the general form of such equation is some function. Then you to get the output, you will have to integrate the left side and the right side, and you will receive an arbitrary constant. And this will be the solution. This is the solution. So to start off with, we will do a question. Probably after understanding the question, we will be in a position to proceed further with other questions. So we are asked to solve the dy over dx is equal to x times 2 times log x positive 1 divided by sin y positive y times cos y. So our objective is to take all the x on one side and the y on the other side. So probably what I will do is I will have, it's up to you, you can have y on the left and x on the right. So since I've got sin y positive y times cos y over here featured as a denominator, probably I will have y on the left side. So this is going to be sin y positive y times cos y times dy is equal to x times 2 times log x positive 1 times dx. So this is what we've got. So now what we have to do is we can clearly integrate this. So I'm going to rewrite this as 2 times x times log x positive x, and you got that dx there. On the left side I can write this as sin y. Now let me just have one more step. Sin y plus y times cos y times dy. Now if I were to remove the parenthesis, this is going to be sin y times dy positive y times cos y times dy is equal to 2 times x times log x times dx positive x times dx. So I will be performing the integration like this. Now this can be rewritten as 2 times integral x times log x dx positive integral x times dx. Over here it's integral sin y dy positive integral y times cos y dy. So this is what I've got. Now I will use this space over here. First I will integrate that. It's x times log x dx. So we will use a Liate concept, Liate. So if I were to use Liate, I get u is equal to log x. So du is equal to 1 over x. So it's going to be dx over x, and my dv is x times dx. So if I were to get the v, this is going to be x squared over 2. So uv negative integral v du, that's going to give me log x, and my v is x squared over 2. So I'm going to place it over here, minus my v is x squared over 2 times du is dx over x. I can cancel a x out. So if I were to cancel a x out, so this is going to give me x squared over 2 times log x, and this is going to be 1 over 2. If I were to integrate, this is going to give me x squared over 2. So I can rewrite this as x squared times log x negative x to the power of 2 divided by 4. So that's okay. I can take that and substitute it into the equation, or I should say in the integral present here. So this is going to be 2 times, we have integrated this, so this is going to be x squared over 2 times log x negative x squared over 4. Integration of this is going to be x squared over 2. So if I were to bring the 2 inside, so this is going to be 2 and 2 can be cancelled, so I get x squared times log x. So that's one particular term, and then this is going to give me x squared over 2, right, and followed by x squared over 2. So this is what I've got. Now clearly you can see that negative x squared and positive x squared can be cancelled, giving me x squared times log x. This is for one term on the right hand side. So now I need to obtain the value for this. Now you can clearly see that this is integral y times cos y dy. So let me perform that over here. So using the Liet, what I would do is you got logarithmic inverse algebraic, right? So this is algebraic, so I'm going to take u is equal to y, and du is equal to dy, and dv is cos y dy, and my v will give me, when I integrate this is going to give me sin y, right? So uv minus integral v du, that's the formula. My u is y, my v is sin y, and followed by my v is sin y, my du is dy. I integrate sin y, I get negative, 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 that will be a cos y, and this is going to give me y times sin y. So all I need to do is substitute this over here. So integrating sin y, this is going to give me negative cos y, followed by my quantity y times sin y plus cos y. You see that negative cos y, positive cos y gets cancelled, giving me y times sin y. So this is going to be y times sin y. We need to have an arbitrary constant, so I place the arbitrary constant. So this is the outcome that we have got. So probably you can rewrite this as, say, x squared times log x negative y times sin y is equal to c. This is also possible, you can also write it like this, because this is an arbitrary constant c, right? I know what you are thinking, why have I not placed it as negative c? It doesn't matter. So this is just a constant, so you can also represent the solution like this or like this. So based on your requirement, what is expected. Now let us move on to do another question. We are asked to solve this. Solve, say, dy over dx is e raised to the power of, so 3x negative 2y positive x squared e raised to the power of negative 2y. So this is what we've got. So as usual, we will have to get rid of, in other words, place y in one side and x in the other side. I can rewrite this as e raised to the power of 3x times e raised to the power of negative 2y positive x squared times e raised to the power of negative 2y. I can take e raised to the power of negative 2y out. This will give me e raised to the power of 3x positive x squared. So this is what I've got. Now this is completely x, this is y. What I can do is I can push this guy down. So this is actually dy over dx, right? dy over dx. So if you were to push it down, this is dy divided by e raised to the power of negative 2y is equal to e raised to the power of 3x positive x squared times dx. So this is what I've got. Now I can push it to the, I can push this guy to the numerator. So this is going to be e raised to the power of 2y times dy is equal to e raised to the power of 3x positive x squared times the dx. So if I were to integrate both sides, this is going to be e raised to the power of 2y divided by 2 is equal to e raised to the power of 3x divided by 3 positive x to the power of 3 divided by 3 positive c. So this is what we have got. Now of course you can rewrite this based on your requirements, and what I would do is I would actually multiply both, or throughout I would multiply by 6. If I were to multiply by 6, let me write that down. So this is going to be 6 times e raised to the power of 2y divided by 2. So that's going to be 6. 2 divided 6 3 times, right? So let me just write that 3 down. So 3 raised to the power of e raised to the power of y is equal to, this is going to be 2 and 2, so I will just place 2 e raised to the power of 3x positive x cubed. Now there is a 6c, right, because I'm multiplying the entire component, entire equation by 6, so this is going to be 6c. So you can also have it like this, or you can replace the 6c with a capital C. So it still means the same, because this c is arbitrary constant. Students, we are given this question, dy over dx is equal to sine of x positive y, positive cos of x positive y. Now it's challenging to separate x from y because they are clubbed with the operator addition, but there is a technique. Now what we got to do in situations like this, you will have to make a substitution. So you got to say let x positive y be equal to t. Now when you differentiate this is going to be 1 positive dy over dx is equal to dt over dx. So from here I can write dy over dx to be equal to dt over dx negative 1. So this will be the substitution. So if I were to take this as 1, so what I'm going to do is, therefore I can write 1 to be as, in place of dy over dx I need to substitute dt over dx negative 1 is equal to, in place of x positive y it's sine t, x positive y is going to be cos t. So we've got a nice bit of equation which is actually separated. So what I'm going to do is I'm going to take 1 on that side. So this is going to be dt over dx is equal to 1 positive sine t positive cos t. So this is what I've got. Now if I were to take the dx onto the right and bring this down, this is going to give me dt over 1 positive sine t positive cos t is equal to dx. So this is what I've got. Now you can either write it like this also, dx is equal to dt divided by 1 positive cos t positive sine t. It still means the same. Now I would be integrating both sides, right? Now for integration to happen I'm going to make this slight alteration. So that is, let my t be equal to say some 2 theta. So from here dt is equal to 2 times d theta. So this is equal to, in place of dt it's d theta with a 2 there. This is going to be 1 plus cos t. T is 2 theta, so it's going to be cos of 2 theta positive sine t. Sine t is sine of 2 theta. Now why did I place cos t? Because you would be in a position to see that there is a formula there. What is the formula? The formula is 1 plus cos 2 theta divided by 2 is equal to cos squared theta. So I exactly wanted you to see that. So if I were to substitute, replace 1 plus cos 2 theta divided by 2 as 1 plus cos 2 theta to be equal to 2 times cos squared theta, then this is going to be 2 times d theta divided by, so this is 2 times cos squared theta positive. Now sine 2 theta, sine 2 theta is 2 times sine theta cos theta. Okay, so this is 2 times sine theta and cos theta. You can write it like that. You can just take cos squared out. Now clearly you can see that you got a 2 here, you have a 2 here, you have a 2 here. So all these 3 2's can be cancelled. So I can now take cos squared out, cos square theta out. That will give me 1 positive sin theta divided by cos theta, right? Cos square theta multiplied with sin theta over cos theta will produce me this sin theta cos theta. Now we know that sin theta over cos theta is tan theta, and 1 over cos square theta is secant square theta. So this is going to be equal to integral secant square theta d theta divided by 1 positive tan theta. Now what I wish to do, I would like to use this space here. Okay, so I'm going to say let 1 positive tan theta be equal to some p. So differential of tan theta is going to be secant square theta d theta is equal to dp. So if I were to substitute, this is equal to, in place of secant square theta d theta, this is going to be my dp. In place of 1 plus tan theta, this is going to be my p. If I were to integrate this is going to be my log p, which is nothing but my log of 1 positive tan theta. So this is what I have got. Now you will have to understand that theta, since t is equal to 2 theta, so therefore theta is equal to t over 2. So this is equal to log of 1 positive tan of t over 2. This is what I've got. But t is equal to x positive y, right? So you take that x positive y and you substitute it here. So let me use the space here. So this is going to be equal to log of 1 positive tan, my t is x positive y divided by 2. So this is what I've got. Now this looks nice, but on the left side we will have to take note of this. When you integrate, you are actually getting x here, and x here. That x is coming here, okay, because integral of dx is going to be x. So on the left hand side I get an x, and to complete the equation I need to add an arbitrary constant. Probably if you're not happy with x positive y over 2, you can rewrite this as log of 1 positive tan of 1 over 2 times x positive y. You can write it like this, plus arbitrary constant c. So that on the left hand side, make sure to place the x. So this is the solution for the question. Students, we are given this question: solve dy over dx is equal to 4 times x positive y positive 1 raised to the power of 2, given that at x is equal to 0, y of 0 is equal to 1. Now what I wish to do is I would like to take this substitution. Let 4 times x positive y positive 1 be equal to some t. This would mean I get 4 positive dy over dx is equal to dt over dx. So from here I will have dy over dx is equal to dt over dx negative 4. So now what I can do is I can substitute this in place of this. So let me take that as 1. I take that as 1. Then I can say, therefore I can rewrite 1 as, in place of dy over dx, this is dt over dx negative 4. In place of 4x positive y positive 1, I substitute t squared. So I push this 4 to the other side. So I get dt over dx is equal to t squared positive 4. I move this t squared positive 4 down. So this is dt over t squared positive 4 is equal to dx. Now integrating both sides, this is going to be integral dt. I'm going to rewrite this as 2 squared positive t squared is equal to, I'm not going to integrate it now on the right side. So this is equal to integral dx. Now by formula this is going to be, now this is nothing but 1 over a tan inverse of x over a. So t over 2 Integration of this is going to give me x positive c. Now I would take this 2 to the right side, so that would mean I can rewrite it as tan inverse of t over 2 is equal to 2 times of x positive c. But in fact I can push this tan inverse to the other side, so there's going to be t over 2 is equal to tan of 2. In fact I can rewrite it like this, 2x positive 2 times c, right? I take the 2 inside, but my t is actually 4x positive y positive 1, right? So I substitute here, so what do I get? I get 4 times x positive y positive 1 divided by 2 is equal to tan of 2x positive 2 times c. Now I can move this 2 to this side, so that would give me 4x positive y positive 1 is equal to 2 times of tan of 2x positive 2c. So fair enough. Now we are given, what are we given? When x is equal to 0, y of 0 is equal to 1. This is the value that is given, right? So that would mean x is equal to 0, this vanishes, and y value is 1 is equal to 2 times. I have a tan of x is equal to 0 plus 2 times of c. This is what I've got. So I can rewrite this as 2 is equal to 2 times of tan of 2c. 2 divides 2 once, so it's going to be 1 is equal to tan of 2c. I can move this tan to the other side, so this is going to be tan inverse of 1 is equal to 2 times c. But what is tan inverse of 1? That's pi over 4 is equal to 2c. So this means I got c is equal to pi over 8. So I've got the value for c, right? Pi over 8 is a value. Now I wish to substitute it in this, say I'm going to take this as 2. So therefore 2 can be rewritten as 4 times x plus y plus 1 is equal to 2 times tan of 2x plus 2 times, my c is pi over 8. I substitute that. So this is going to be 4 times x plus y plus 1 is equal to 2 times tan of 2x positive pi over 4. So this is the final answer for the question, students. So we will move on to the next one. Students, we have a question. It's given that there is a function defined from R to R, and that with f of 0 is equal to 0, and it is stating that y is equal to f of x satisfies this differential equation. Now, having given this information, they want us to find what happens to the function as x is tending towards negative infinity. So foremost, what I wish to do is I would like to start by saying consider dy over dx to be equal to, now 2 positive 5y times 5y negative 2. Now what I wish to do is I would like to rewrite this as 5y positive 2 times 5y negative 2 is equal to dy over dx. Now move all the y to one side and the x to the other side. So the most comfortable way to do that is keep the y on the left and bring 5y positive 2 times 5y negative 2, and on the right hand side I got dx. Now we can integrate this, but to make integration possible we will have to use partial fractions. But it is imperative to understand that not always that you need to apply partial fractions. Some of the times you can use straightforward techniques. For example, on the left hand side I can rewrite this as 5y positive 2 negative of 5y negative 2 divided by 5y positive 2 times 5y negative 2 is equal to integral dx and this has to be integrated with reference to dy. Now clearly you can, there's a parenthesis there. Clearly if you can see that 5y negative 5y, they get cancelled. 2 negative of negative 2 will give me 4. I need to get a 1 there, so I'm going to multiply by 1 over 4. Now clearly you can see that this is easily solvable, and for the simple fact that whenever I use the concept of algebraic law, say writing a positive b divided by c as a over c positive b over c, then I can easily integrate those terms. So that is the basic idea for this. So if I were to rewrite this, this is going to be 1 over 4 integral. The numerator is 5y positive 2 divided by the denominator 5y positive 2 times 5y negative 2 times dy. Of course, maybe I can place a huge parenthesis there, followed by integral 5y negative 2 times dy divided by 5y positive 2 times 5y negative 2. Now clearly you can see that 5y negative 2, 5y negative 2, 5y positive 2, 5y positive 2, they can be cancelled. Of course, let me place the parenthesis. This is integral dx. Now this is going to be integral dy divided by 5y negative 2 followed by integral dy divided by 5y positive 2. This is equal to x. Now what is this? This is going to be integral dy over 5y negative 2. This is going to be my log, right? Log. Now let me show you what happens if you have a quantity like this. Now you got a quantity like this, say integral dx divided by, say, some 7x minus 2. You naturally you will say let 7x minus 2 be equal to some t. This is going to be 7 times dx is equal to dt. So if you have to substitute in place of dx, you have to substitute dt over 7 divided by t. So this is going to be ln of t. My t is going to be 7x negative 2. Of course there is a coefficient, so that has to be multiplied. Of course we need to place the arbitrary constant. So all these things, they follow, right? I'm just going to apply the same principle what you see here over here. So this is going to be 1 over 5 times ln. I need to use the modulus. I wanted to have a defined function, so that's the reason. So it's going to be 5y negative 2 followed by negative 1 over 5 times ln 5y positive 2, which is equal to x. Now we know a law. What is a law? We know that ln of a negative ln of b is equal to ln of a over b. So by this, what I can do is I can rewrite this as 1 over 4 times, this is actually 1 over 5, right? I can take 1 over 5 out and rewrite this as ln of 5y negative 2 divided by 5y positive 2 is equal to x. So this is what I have got now. Now clearly you can see that 4 times 5, 20, that can be multiplied. And let me place in one more step. So this is going to be 1 over 20 times ln of 5y negative 2 divided by 5y positive 2. This is equal to x. I can cross multiply. Now if I write a cross multiply, let me use this space here. So that would give me ln of 5y negative 2 divided by 5y positive 2 is equal to 20 times x. Now we know there is a property in logarithms. So what is that? You have something like this. Ln a to the base e is equal to some y. Then you can write a is equal to e power y, because this is base natural logarithm. So I can use that concept and rewrite this as 5y negative 2 divided by 5y positive 2 is equal to e raised to the power of 20x. Now the question wants us, the question says when x is, this is what we have got, Now the question wants us to find the functional value when x is tending to negative infinity. So that is the most important thing. Now if you were to substitute here e raised to the power of 20 times negative infinity, as x is tending to negative infinity, this quantity, this is e raised to the power of negative times infinity times 20. This will be tending towards 0. So we have got, what have we got? We got 5y negative 2 divided by 5y positive 2 is equal to 0. You cross multiply, you get 5y negative 2 is equal to 0. Move the 2 to the other end, you get 5y is equal to 2. So therefore y is equal to 2 over 5, which means y is equal to 0.4. So this is what is the requirement, and we have got that solution. Students, we are given this question: if 2 positive sin x of dy over dx positive y positive 1 of cos x is equal to 0 and that y of 0 is equal to 1, we are expected to find y of pi over 2. Now this is a competitive examination question, so let's do that. Now foremost what we need to do is, I'm going to say consider 2 positive sin x times dy over dx positive y positive 1 times cos x is equal to 0. So I will move this to the other side. So this is going to be 2 positive sin x times dy over dx is equal to negative of y positive 1 times cos x. Now what we can do is we can pull in the cos x and the y terms to, you know what I mean, keep the y terms on the left and cos x terms and the x terms on the right hand side. So I will have a cos x here. I'm going to push this term 2 positive sin x down, and then I will push up this dx. But we got a negative sign. Probably we can place the negative sign along with the x term. And on the left hand side, you only have dy. So this is what you got. Along with that, I would have to make sure that this y term comes down. So this is going to be y positive 1. Right? So this is the slight rearrangements we have got. Now we need to integrate. So integrating both sides. Of course the left hand side is going to be ln of y positive 1. Not much of an issue. But for the right side, what I'm going to do is I'm going to say let me make the following substitution. Let 2 positive sin x be equal to t. This is cos x dx is equal to dt. So if I were to make the substitution, this is equal to, I have a negative sign, cos x dx is going to be dt, this is going to be t. Now when I integrate this is going to be negative ln of t. Now my t is 2 positive, so it's going to be negative ln of 2 positive sin x. So this is what I have got. Now we need to place the left hand side, which is ln of y positive 1, and that has to be accompanied with an arbitrary constant. So I can place an arbitrary constant, say some c. Now if you were to move this negative term to the left hand side, this is going to be ln of y positive 1 positive ln of 2 positive sin x is equal to c. Now there is a law which says that ln of a positive ln of b is going to be ln of ab. So using this formula, this can be rewritten as ln of y positive 1 times of 2 positive sin x. Right. Now this c, what I wish to do is, I've got a c here, I want to rewrite this as ln c, because you got logarithmic quantities on the left hand side. You can very well use logarithm to represent this c. Now removing log on both sides, you can, in fact if you want, you can just state that removing log on both sides. Don't cancel them, just use the word removing log from both sides. So when you do that, when you remove log from both sides, you would get y positive 1 times 2 positive sine x. This is what you get. And of course the log gets dropped and you can have the c there. Now the question says when x is equal to 0, the value of y is equal to 1. You can clearly see that. This is what the question says. Let me show that to you. Okay, so we are going to use that concept. So when x is equal to 0, y is equal to 1. So sine 0, this goes away. So you get 1 positive 1 times of 2 is equal to c. Therefore the value of c is 4. Now if I were to take this as, say, sum 2, therefore I can rewrite 2 now with the elimination of the constant. Therefore 2 can be rewritten with the elimination of the constant. Elimination of constant. I can do that. So that is going to be y positive 1 times 2 positive sine x is equal to 4. Now the question comes is we are expected to find when x is equal to pi over 2, what is y? So let's do that. So this is going to be y positive 1 times of 2 positive sine pi over 2 is equal to 4. Sine pi over 2 is 1, so 2 positive 1 will give me 3 times of y positive 1 is equal to 4. I can push this down, so I get y positive 1 is 4 over 3. I can move the 1 to the other side. I get y is equal to 4 over 3 negative 1, which means y is 1 over 3. So this is the solution to the question. Students, we have been given this question: y over x times dy over dx, positive x squared positive y squared negative 1 divided by 2 times of x squared positive y squared followed by a positive 1, and that is equated to 0. What we would do foremost is to make the following substitution. So I'm going to say let x squared positive y squared be equal to t. Now when I take this, I will be differentiating both sides. Differentiating with respect to x, we get, this is going to be 2 times x. This is going to be 2 times y times dy over dx. This is going to be dt over dx. Now what I would do is I would just retain dt over dx on one side, and I will try to move the quantities of x the other side. So this is going to be 2 times y dy over dx is equal to dt over dx. I am going to move this 2x to the right, and that's going to be negative 2 times x. Now I will divide throughout by 2x. So that would give me, this is going to be 2y over 2x dy over dx is equal to 1 over 2x dt over dx negative 2x over 2x. Now clearly the 2 that you see can be cancelled, the 2x can be cancelled, and that would in turn give us y over x dy over dx is equal to 1 over 2x times dt over dx negative 1. So what we will have to do is we will have to make use of this substitution for our question. So if I were to take this as 1, I can clearly say that therefore 1 can now be rewritten as in place of y over x times dy over dx, I'm going to replace it with this. So that's going to be 1 over 2x dt over dx negative 1 positive. Now x squared positive y squared. Now we have taken the substitution that x squared positive y squared is equal to t. So I'm going to place t there. So this is going to be t negative 1 divided by 2 times t positive 1 is equal to 0. Probably I will rewrite it again. So I will just keep this term on the left and I will move all other terms to the right. So that would mean I get 1 over 2x times dt over dx is equal to, this is going to be 1 followed by negative of t. So let me just place a parenthesis like this. So I don't need to place a parenthesis, but I have started. So this is going to be t negative 1 divided by t positive 1, and we will have to use the LCM and rewrite it. So if I were to use the LCM, now what I'm going to do is I'm going to use the LCM here. So 2t positive 1, so this is going to be 2t positive 1 negative t positive 1. 2t added with t would give me t, positive 1 added with positive 1 will give me 2. This is going to be 2t positive 1, right? So we got a quantity going, and on the left side I got 1 over 2x dt over dx. Now what I wish to do, I would like to make the separation here. So probably I can use this space here. So this one I'm going to rewrite it like having dt. I'm going to push this t positive 1 down, I mean t positive 2 down, and I'm going to take 2t positive 1 up. So this is going to be 2t positive 1 up. This is going to be equal to, I'm going to take 2x up, and along with 2x I will have a dx also. So this is what I've got. Now rewriting, let me rewrite this. So I get 2t positive 1 divided by t positive 2 times dt is equal to 2 times x dx. I can rewrite this as 2t over t positive 2 positive 1 over t positive 2 times dt. This is equal to 2 times x dx. Now clearly you can see the degree of the numerator is same as the degree of the denominator, right? So in that case we will have to defragment it. Now you can use many different ways to defragment this, but what I would do is I would like to defragment this in this following fashion. So I would like to rewrite this entire thing as t positive 2. Now this has got a 2 there, so let me place a 2 over here. So 2 times of this would give me 2t along with the 4. So I need to have a positive 1 here, because if you were to see this quantity, it's 2t positive 1. But I would get, if I were to use this component, I would get a positive 4. So I need to get rid of the additional 3. So I will place a 3 like this, and then this has to be multiplied with dt, right? So this is equal to 2 times x dx. Now this is clearly the quantity that we have over here. So what I wish to do is I would like to integrate this now. So this is return as, let me rewrite this, 2 times dt negative 3 times of dt divided by t positive 2 is equal to 2 times integral x times dx. Now this is going to give me 2 times t followed by negative 3 times. This is going to give me ln of t positive 2,
and this is going to give me 2 times of x squared divided by 2 positive c. Now I can cancel this, and then I will have to make some changes. So I need to get rid of this x squared, which I can, in fact I need to get rid of this t. So let me write that down. Since t is equal to x squared positive y squared, if I were to take this as 2, therefore 2 can be rewritten as 2 times of x squared positive y squared negative 3 times of ln. Now our t is x squared positive y squared, so substitute that x squared positive y squared followed by a positive 2, that's fine, and I have a x squared here on the right hand side, and that has to be placed with an arbitrary constant. Now what we can do is we can still simplify this. This is going to be 2 times x squared. I can bring this x squared here followed by 2 times y squared negative 3 times ln of x squared positive y squared positive 2 is equal to c. I can club these two together, and that would give me x squared positive 2 times y squared negative 3 times ln of x squared positive y squared positive 2 is equal to c. So this is a beautiful question, students. Now what I wish to do is I would like to give you all a few questions to try out. So try these questions. Okay, these will not only improve your power in differential equations, but it will prepare you for greater challenges. So question number 1, all of these things are solved. Okay, you got to solve this. So it's going to be y times square root of 1 negative x squared times dy positive x times root of 1 negative y squared times dx is equal to 0. That's question 1. My question 2 is going to be y over x dy over dx is equal to square root of 1. All these questions are based on whatever I have worked, so it's not something that I'm giving you all to try it afresh, but they're all which we have worked already. So dy over dx is equal to x times e raised to the power of y negative x squared if y is equal to 0 when x is equal to 0. So 1, 2, 3, just 3 questions you can solve, and probably you can, let me give you the 4th one. This is really a beautiful question. E raised to the power of x times tan y times dx positive 1 negative e raised to the power of x times secant squared y times dy is equal to 0. This is a lovely question. Probably I'll stop with number 5. This is dy over dx is equal to e raised to the power of 2x negative 3y positive 4 times x squared e raised to the power of negative 3y. So 5 questions, and you can put your solutions in the comment box. Thank you, students. Enjoy your night.
Welcome students, in this class we will be learning how to use the technique of reducible variable separable methods. Now if you remember, we have already studied about variable separable. They were all straightforward ones. Now this category of variable separable is often denoted as type 2, and the form that we would be looking here is dy over dx is equal to a1 times x positive b1 times y positive c1 divided by a2 times x positive b2 times y positive c2, and the required condition for applying this technique is that b1 positive a2 should be equal to 0. So have that in mind. Now having mentioned that, let me start out with an illustration. So I've got this question: solve the differential equation which is of the form dy over dx is equal to x negative 2y positive 5 divided by 2x positive 3y negative 1. Now I would be able to apply type 2 only if the coefficient of y, which is b1, and that has to be added with the coefficient of x, or I should say in this case it is 2. This sum should produce me 0. Now if it produces me 0, then I would be able to add, or I would say I would be able to apply this technique. So what exactly is this technique? This technique is simply cross multiplying. That's it. So this is going to be 2 times x positive 3y negative 1 times dy is equal to x negative 2y positive 5 times dx. So this is going to be 2 times x dy positive 3 times y dy negative dy is equal to x times dx negative 2 times y times dx positive 5 times dx. So this is what we have got. Now what we are going to do is we will add to club x times dy. Remember this, x times dy with y times dx. So this is the next step we should do. Always make sure to club x times dy with y times dx. So when this comes, this is going to become positive, and after that you can either move everything to the left or right, it's not going to matter. So I'm just going to rewrite as it is. So 3 times dy negative dy is equal to x times dx positive 5 times dx. So this is what I've got. Now this can be rewritten as 2 times of x times dy positive y times dx. I'm rewriting everything. 3y times dy negative y is equal to x times dx positive 5 times dx. Now what is this? This is nothing but differentiation of x times y, right? Because when you differentiate xy, you're going to apply UV method. If you're going to be applying UV method, this is exactly what you will get. Followed by 3 times y dy negative dy is equal to x times dx positive 5 times dx. Now it is imperative for us to know that if I were to integrate dx, I would get x. Of course there is arbitrary constant c. If I were to integrate y, I would get y with an arbitrary constant c. And if I were to integrate d of xy, I will get xy with an arbitrary constant c. So that is what we have to remember. So if I were to be integrating both sides, so what happens when we integrate both sides? So this is going to be 2 times integral d of xy, 3 times y times dy, integral dy is equal to integral x times dx positive 5 times integral dx. Now this is going to give me 2 times xy, this is going to give me y squared, this is going to give me y, this is going to give me x squared over 2, and this is going to give me 5x. Of course there should be an arbitrary constant positive c. Now this is going to be y squared over 2, so that is critical. We need to make sure that we divide, because of the fact integral x power n dx is x to the power of n positive 1 divided by n positive 1 positive c. So this would be the final solution to the question. So this completes our solution, students. We'll move on to the next question. Students, in type 3 we will be using polar coordinates. Now I'm sure that you all are aware of the polar coordinates. The most popular one is the substitution, that x is equal to r times cos theta and y is equal to r times sin theta. Now if I were to take this substitution, then clearly I know that x squared positive y squared will be equal to r squared. You can substitute it here. I can show that over here. R times cos theta raised to the power of 2 positive r times sin theta raised to the power of 2, which is rewritten as r squared cos square theta positive sin square theta, which is equal to 1, and so I get r squared. So this is just for your understanding. So clearly we know that x squared positive y squared is equal to r squared. Now if I were to differentiate this, then I would get 2 times x positive 2 times y. Differentiation is with reference to x, so it's going to be 2 times y times dy over dx is equal to 2 times r times dr over dx. So this is what we would be getting. Now I can clearly cancel the 2 that you see here, and that would give me x positive y times dy over dx is equal to r times dr over dx. Now if I were to multiply both sides by dx, right, then I would get, this is going to be x times dx positive y times dy is equal to r times dr. So this is a very important differential equation result that we would be using, so have that in mind. This is a very important result. Now also, this is case 1. Now if I were to take case 2, okay, let me just take case 2. Now in case 2, what I'm going to do, I'm going to take y over x. So that would mean my y is r times sin theta, my x is r times cos theta, so my r can be cancelled, giving me tan theta. Now if I were to differentiate both sides with respect to x, then I would get u over v form, right? So d of u over v is equal to v times u dash minus u times v dash divided by v squared. So this is just the formula that we have studied. So by this is going to be x times y dash minus y times x dash is 1 divided by x squared, right? Of course, in this case what we can do is we can, in fact, we can just say d over dx, right? So we can rewrite this. Of course, differential of tan theta is going to be secant squared theta times d theta. So this is what we have got. Now I can rewrite this as x times dy negative y times dx is equal to x squared times secant squared theta times d theta, because now since x is equal to r times cos theta, if I were to substitute here, it's going to be r squared cos squared theta times secant squared theta times d theta. Now secant squared theta cos squared theta can be cancelled, giving me r squared times d theta. On the left hand side is going to be x times dy negative y times dx. So this is another important result which we will be using for our work. So using polar coordinates we have achieved 2 results. Now we would be employing these results to solve the questions. So we've been given this question, we are expected to solve. We have got x times dx positive y times dy is equal to x times of x dy negative y times of dx. Now we have used polar coordinates and we know the following results. So what are the results we know? We know that x times dx positive y times dy is equal to r times dr. This is one result which we just obtained. And the next result, x times dy minus y times dx is equal to r squared times d theta. So this is the next result we have obtained. Now if I were to take this as 1, therefore 1 can be rewritten x dx positive y dy. I can rewrite this as r times dr, and then I can rewrite this x is equal to r cos theta, so I can just substitute r cos theta, but I can rewrite x dy minus y dx as r squared times d theta. So this is what I can do. So this is equal to r cubed times cos theta times d theta and r dr. So this is already in variable separable mode. So this can be rewritten as dr is equal to, I can cancel, I can get rid of an r and an r here. So this is going to give me r squared times cos theta d theta. I can integrate, but prior to integration, the best thing is to have brought this r down, right? But of course I will bring it in the next step. So this is going to be dr over r squared is equal to integral cos theta times d theta. I can rewrite this as integral r to the power of negative 2 times dr is equal to integral cos theta d theta. Now if I were to integrate this, this is going to be r raised to the power of negative 2 positive 1 divided by negative 2 positive 1. Integral of cos theta will give me sin theta. Of course I need to add the arbitrary constant c. So if I were to simplify this, this is going to give me r raised to the power of negative 1 divided by negative 1 is equal to sin theta positive c. I can rewrite this as 1 over r with a negative sign, which is equal to sin theta positive c. So this is going to be my solution. Now if the question has got a choice featuring in polar coordinates, then this is the right place to stop. If it is given in Cartesian coordinates, then it is imperative to know that r is equal to root of x squared positive y squared. We have already seen this because of the fact that x squared positive y squared is equal to r squared. So therefore I can write r to be as root of x squared positive y squared. Now coming to sin theta, we need to know that y over x is equal to tan theta. So if you were to draw the triangle, the right triangle, and if this is going to be theta, and if you are going to be placing, this is opposite side, this is adjacent side, this is hypotenuse side, and tan theta is opposite side divided by adjacent side. But this is nothing but y over x. So this is going to be my y, this is going to be my x. If this is y, this is x, this is going to be r. So my r is going to be root of x squared positive y squared. Okay, so much so for that. But we are expected to find sin theta. So therefore sin theta is opposite side divided by hypotenuse side. So which is equal to opposite side is y, my hypotenuse side is x squared positive y squared. This is my sin theta. So taking these values, and if I were to take this as 2, so therefore I can rewrite 2 to be as negative 1 over root of x squared positive y squared is equal to y over root of x squared positive y squared positive arbitrary constant c. So this is the solution in Cartesian coordinates. Thank you, students. We'll move on to the next question. Students, we are given this question: x positive y times dy over dx divided by x times dy over dx negative y is equal to square root of 1 negative x squared negative y squared over x squared positive y squared. Now clearly, whenever they give problems of this nature, we are not going to be approaching this question using the normal variable separable technique. So the best bet to solve this question is to use the polar form. Now with polar coordinates that we have just exposed to, this question is easily solvable. Now all I need to do is to take the LCM. So if I were to take the LCM, I can rewrite this as x times dx positive y times dy divided by dx And similarly, this is divided by, if I were to take the LCM, this is going to be x times dy negative y times dx divided by dx. Now clearly you can see the dx and the dx can be cancelled, so that would be equal to square root of, I'm going to rewrite this as 1 negative of x squared positive y squared divided by x squared positive y squared. Now I clearly know that, let me write that down, since r squared is equal to x squared positive y squared, we have already studied this, and x times dx positive y times dy, what is that equal to? Now this one we already know, this is equal to r dr, and we also know this is equal to r squared, also x times dy negative y times dx is equal to r squared d theta. So we can box these things. We know this, and we also know this. So if I were to take this as 2, therefore I can rewrite 2 as, in place of this x dx y dy, I'm going to substitute this r dr. In place of this, I'm going to substitute r squared d theta is equal to square root of, this is going to be 1 negative r squared, and this is going to be r squared, right? So clearly I can cancel a r and a r here, so this is going to give me dr over r times d theta. This is equal to root of 1 negative r squared divided by root of r squared. I'm going to use this space here, so I can rewrite this as dr over r times d theta is equal to root of 1 negative r squared. Now root of r squared is going to be r, so I can clearly cancel these two and now apply variable separable. So this is going to be dr over 1 negative r squared is equal to d theta. So integrating both sides, we get, so what happens when you integrate both sides? This is integral, so when you integrate this, this is going to be sine inverse of r, this is going to be theta positive c. But sine inverse of r, now r squared is x squared positive y squared, so therefore r is root of x squared positive y squared. So this is going to be sine inverse of square root of x squared positive y squared is equal to theta. Now let me write that down here. Now since y over x is equal to tan theta, therefore theta is tan inverse of y over x, right? So just take this value and substitute it here. This is tan inverse of y over x positive c, and this is the final solution for the question. So we are given this question, we are expected to solve x dx positive y dy divided by root of x squared positive y squared is equal to y dx negative x dy divided by x squared. Now the left hand side is simple, but in the right hand side we need to do some alterations. So I'm going to take this as 1 and then I'm going to state it. We know that x times dy negative y times dx is equal to r squared d theta. So if I were to take a negative sign out, then I can rewrite this as y times dx followed by x times dy is equal to r squared d theta. Now pushing the negative sign, in fact multiplying throughout by negative sign, I can now rewrite this as y times dx negative x times dy is equal to negative r squared d theta. Now why did I do all this? I did all these things because of the fact that there is a y dx negative x dy present in the given question. So I want to make sure that I got a polar substitution for that particular term. Now we know that x dy positive y dx, maybe I can state that also we know that x dx positive y dy is equal to r times dr. We know that. And what else we know? We know that x squared positive y squared is equal to r squared. So using all this, so we are going to be using all this, and then we are going to be rewriting. Therefore one can be rewritten as, in place of x dx positive y dy, I'm going to substitute r times dr divided by square root of x squared positive y squared is r squared. In place of this is going to be negative r squared d theta divided by x. X is nothing but r times cos theta. So this can be rewritten as r times dr. Root of r squared will give me r, and I get a negative. Now I can cancel a r and a r there, giving me negative r times d theta divided by cos theta. Now an observation, this is actually x squared, right? So that would mean I have a 2 here. So this one would get cancelled off because of the fact that there is 2 there, which I am noticing now. So that one will get cancelled off and then leaving me 2 there. So I can also cancel the r terms that are present here. So giving me dr is equal to negative d theta divided by cos square theta. Now this is nothing but secant square theta, right? 1 over cos squared, you can write that down, since 1 over cos theta is secant theta, so 1 over cos square theta will be secant square theta. So this is secant square theta d theta, and this is my dr. So I will integrate both sides. Integral of dr will give me r, integral of secant square theta would give me my tan theta, and of course arbitrary constant c. Now we know that y over x is equal to tan theta, so I would be using that over here. So that's going to be negative y over x positive c. On the left hand side, x squared positive y squared is equal to r squared. Therefore r is equal to root of x squared positive y squared. So I will be using these two things. So this is going to give me root of x squared positive y squared. So this is my final solution to this question. Thank you, students. Students, in this class we will be learning how to solve homogeneous equations. Now imagine you are given this question, say solve x squared negative y squared times dx negative x times y dy is equal to 0. Now foremost, what you have to do is you will have to write this entire equation with dy over dx being featured on the left hand side. So what I would do is, first I will try to move this onto the right hand side. So this is going to give me x squared negative y squared times dx is equal to x times y dy. Now since I'm looking for dy over dx, what I wish to do is I would bring this dx down and move this xy to the left hand side. Now when I do that, I get x squared negative y squared divided by xy is equal to dy over dx, and now I can represent dy over dx as x squared negative y squared over xy. Now this step is very critical, because it allows us to find if the given equation is homogeneous or not. Now when we talk about homogeneous, the main check should be the degree of the numerator should be the same as the degree of the denominator. Now what is the meaning of this? The meaning is, just go to the numerator and find out what exactly is the degree here. You can see the degree of x squared is 2, degree of y squared is 2, so the total degree of the numerator is 2. And go down to the denominator and find out the degree of the denominator. The degree of the denominator for x is 1 here, the degree of y is 1, so the total degree is going to be 1 plus 1, which is equal to 2. So when the degree of the numerator is same as the degree of the denominator, we can safely conclude that we are dealing with a homogeneous equation. Why is it so important? Because for homogeneous equation, we will make the substitution as y is equal to v times x. Because this substitution will allow us to solve this equation. And this substitution will only be valid and it will give us the required result if it is substituted into a homogeneous equation. So that is why we have to make sure that that check, or in other words this check, holds good. So having mentioned this, let us move on. Now we take y is equal to vx and then we differentiate with respect to x. So when I do that, I get dy over dx is equal to uv formula. V times differentiation of x is 1 positive, x times differentiation of v is dv over dx. So we have got this. Now if I were to take this as 2, I can rewrite 2 as, therefore 2 is rewritten as, in place of dy over dx, I'm going to be substituting v positive x times dv over dx. In place of x squared, I will retain it as it is. In place of y, I will be substituting v times x raised to the power of 2 divided by x times v times x. Now this is equal to x squared negative v squared x squared divided by x squared times v. Now if I were to take an x squared out, this is going to be 1 negative v squared divided by x squared times v. I can clearly cancel out the x squared and x squared, giving me 1 negative v squared divided by v. On the left hand side, I got a v positive x into dv over dx. Now what I wish to do is I would like to move this v to the other side. So if I were to do that, this would give me x times dv over dx is equal to 1 negative v squared divided by v negative v. I can take the LCM for this as v. This will give me 1 negative v squared, which is going to be 1 negative 2 times v squared divided by v. So what I've got x times dv over dx is equal to 1 negative 2 times v squared over v. Now what we got to do is we will have to use variable separable. So using variable separable, so I'm going to use the short form. We will now have dv, and moving this down, 1 negative 2 times v squared. I'm moving this up, so I get a v. I'm moving this to the right, so it's going to be dx. I'm moving x bottom, so I get something like this. So I get a v and 1 negative 2v squared. So first what I will do, this is easily integrable, right? So first what I will do is I will just say consider integral v times dv divided by 1 negative 2 times v squared. So what I would do is I would say let 1 negative 2 times v squared be equal to some t. You differentiate this, you get negative 4 times v dv is equal to dt. So from here you can say v dv is equal to 1 over 4 times dt. Of course you have a negative sign. So if you were to use this substitution, this is going to be negative integral dt of course you got a 4 there. I'll write a 4 in this fashion, divided by 1 negative 2v squared is going to be t. This is negative 1 over 4 times ln t, which can be rewritten as negative 1 over 4 times ln of 1 negative 2v squared. This is what I got. So I can place them in modulus. So I have shown you all these things just to make sure that what we would be getting when we integrate. So now I would start off by saying integrating both sides, we get, so what do we get? Integral of this, when we integrate this we get this. So I would place that negative 1 over 4 times ln modulus 1 negative 2 times v squared is equal to ln of x. Of course there is a constant c that is involved. Probably we can place that constant c there. Now what I wish to do is I would like to do some rearrangements. So that is very critical. So I will want to get rid of this 4. So to get rid of this 4, you will have to multiply by 4 throughout. Now if you were to do that, this is going to be negative ln of 1 negative 2v squared. You don't have to place the absolute value, but if you insist you can do that. It's nothing wrong. So this is going to be 4 times ln x positive 4 times c. So this is what you have got. Now if you choose to get rid of this negative sign, then you will have to multiply by negative 4. That would make this as positive, this as negative, and this as negative. Now what you can do is you can move this negative 4 times ln x to this end. So that would mean you get 4 times ln x positive ln of 1 negative 2v squared is equal to negative 4 times c. So this is what you've got. Now you know that there is a formula which states that ln of a positive ln b is equal to ln of a times b. By using this formula, I can always rewrite this in this following fashion. However, I can also use this formula. Say you have something like this, 4 times ln a. I can rewrite this as ln of a raised to the power of 4. So this is another formula. So if I were to club these things, this is going to give me ln x to the power of 4 times 1 negative 2 times v squared is equal to negative 4 times c. So this is what I've got. Now what you can do is, if you want to get rid of this logarithm, you can use this formula. You got something like this, ln a to the base e is equal to y. You can write a is equal to e raised to the power of y. So by using this formula, I can always write this as x to the power of 4 times 1 negative v squared is equal to e raised to the power of negative 4 times c. So that's always possible. Now having obtained this, what we have to do is we started with y is equal to v times x. So this would mean my v is equal to y over x. So if I were to take this as 3, therefore I can rewrite 3 as the following. So what I need to do is I need to just make the substitution, v is equal to y over x. So if I do this, this is going to be 1 negative 2 times y over x. It's a square there. It's going to be 2. It's going to be 2 is equal to e raised to the power of negative 4 times c. And you can make the simplification. This is going to be x to the power of 4 times x squared negative 2 times y squared divided by x squared is equal to e raised to the power of negative 4 times c. I can always cancel this x squared against this quantity, thereby giving me x raised to the power of 2 times x squared negative 2 times y squared is equal to e raised to the power of negative 4c. But of course this can be rewritten as a constant, so this would mean I can rewrite this entire quantity as x squared x squared of x squared negative 2 times y squared is equal to a huge C. You can either place a C like this, or you can put a C dash. It doesn't matter because it's an arbitrary constant. So this is the required solution, students. We will move on to the next question. Students, we have been given this question: 1 positive e raised to the power of x over y times dx, positive e raised to the power of x over y times 1 negative x over y times dy is equal to 0. We expected to solve this. Well, along the different note, if you haven't subscribed to my channel and if you are interested in upgrading yourself and learning concepts of mathematics and improving your life, I would request you all to stay subscribed, or in other words, subscribe. So, having got that out of the way, let's move on. So, foremost, what we would like to do is we would like to represent this as dy over dx on the left hand side. So, for that, I would like to move this dx onto the other side. So, this is going to be e raised to the power of x over y times 1 negative x divided by y times dy is equal to, this is going to be negative of 1 positive e raised to the power of x over y times dx. So if I were to move dx down, this is dy over dx is equal to negative of 1 positive e raised to the power of x over y divided by, I'm moving this down, so this is e raised to the power of x over y times 1 negative x over y. So this is what we have got. Now we will have to check with the degree of the numerator. I see the degree of x is 1 and degree of y is 1. And then coming here to the denominator, the degree is 1 for x, the degree is 1 for y, and it is also 1 and 1. So clearly we can see that the total degree of the numerator versus the denominator remains the same. So we are basically having a homogeneous system which we will have to solve. Now there is a slight change you will have to apply here. Instead of substituting y is equal to vx, we will have to reform this in this fashion. So what I would like to do is, instead of taking it as dy over dx, I would like to have it as dx over dy. So the best way is to rearranging. So this is going to be e raised to the power of x over y times 1 negative x over y divided by 1 positive e raised to the power of x over y, because the quantities are all x over y. Of course, there's a negative sign, we can place the negative sign, so this is going to be dx over dy. So now, usually we start off with this substitution. We would say y is equal to vx, so, but we are not going to be using this. Instead of this, we are going to say let x be equal to, so this is the substitution we would be making. So in this case, we would be differentiating with respect to y. So on the left hand side, this is going to be dx over dy, and on the right hand side, y u into v form. So it's going to be y times, I have to differentiate v, so it's going to be dv over dy positive, since the differentiation is with reference to y, so we are going to get v. So if I were to take this as 2, so I can state that therefore 2 can be rewritten as, I'll start with this quantity. So in place of dx over dy, I would be substituting v positive y times dv over dy is equal to negative e raised to the power of, so x is equal to y times v, right? So clearly x over y is equal to v, so this is going to be v there and a v here and 1 positive e raised to the power of v. So that is the reason I have made this substitution, x is equal to y times v, because that would prevent us from complicating the substitution process. So what we will have to do is we will have to do some rearrangement and solving. So what I will have to do is I will have to move this v to the other side, and that would give me 1 is equal to negative e raised to the power of v of 1 negative v divided by 1 positive e raised to the power of v. This is going to be negative v. Now simplify by taking 1 positive e raised to the power of v as the LCM. This is going to be, I'm just using distributive property, e raised to the power of v positive v times e raised to the power of v, and this is going to be negative v times of 1 positive e raised to the power of v. So this is what I've got. So this is equal to negative e raised to the power of v positive v times e raised to the power of v negative v times e raised to the power of v divided by 1 positive e raised to the power of v. Now I got a positive v times e raised to the power of v, negative v times e raised to the power of v. They both get cancelled, giving me negative e raised to the power of v followed by negative v divided by 1 positive e raised to the power of v on the left hand side, right? So it's y times dv over dy. So now on the left hand side we have got y times dv over dy. Now we will have to make some rearrangement. So if I were to move them, so this is going to be 1 positive e raised to the power of v divided by, if I were to take a negative sign out, this is going to be e raised to the power of v positive v is equal to dy over y, right? Of course there should be a presence of dv there. I place that dv. Now I can integrate them. Now what I would do is, instead of placing the negative sign here, I would like to place the negative sign over here, change it to positive, and then I will integrate these quantities. Now for integrating these quantities, what I wish to do is I will say consider integral of 1 positive e raised to the power of v times dv divided by e raised to the power of v positive v. Now I would like to make a substitution. Let e raised to the power of v positive v be equal to sum t. If I differentiate this, I get e raised to the power of v times dv positive, differential of v is 1. Of course I need to have a dv there. This is equal to dt. So I can always rewrite this as 1 positive e raised to the power of v times dv is equal to dt, right? So this can be rewritten as, this is equal to integral 1 positive e raised to the power of v times dv is dt, e raised to the power of v positive v is t, and this is going to give me ln t, but my t is e raised to the power of v positive v, right? Of course we got arbitrary constant c, but we will include it there. So this is going to give me ln of e raised to the power of v positive v is equal to negative, this is going to give me ln of y, positive arbitrary constant c. You can always place it there. Now what I can do is I can actually move this to the left hand side. So that would give me ln of e raised to the power of v positive v positive ln y is equal to c. This can be rewritten as ln of y times e raised to the power of v positive v is equal to c. I can rewrite this as y times e raised to the power of v positive v is equal to e raised to the power of c. By properties of logarithm I am able to do this. But my v is, since x is equal to y times v and my v is x over y, I can use this v is equal to x over y over here. So if I were to do that, this can be rewritten as y times e raised to the power of x over y positive x over y is equal to e raised to the power of c. Of course when y comes inside, this is going to be y times e raised to the power of x over y positive x is equal to e raised to the power of c. Of course, based on your requirement, you can afford to stop here, or you can rewrite this as the following: x positive y into e raised to the power of x over y is equal to capital C dash. So this is a good place to stop for this solution. Students, we are given this question: dy over dx is equal to negative of y times of x positive y divided by x squared. Now, foremost, let us perform the homogeneous check. The degree of y is 1. That is taken as a product with x, so its degree is 1. So the cumulative degree of y and x is 2. And then on y is taken with y. As I mentioned to you, the degree of y is 1. This degree is 1. So the cumulative degree is 2. So in all, the degree of the numerator is 2. Now we have to compare it with the degree of the denominator. Clearly the degree of the denominator in this case is 2. So since the degree of the numerator and the degree of the denominator are one and the same, this is a homogeneous equation, and we can make the substitution: let y be equal to v times x. So we will be differentiating this with respect to x. When we do that, we get dy over dx is equal to v positive x times dv over dx. Now what I wish to do is, I would like to take this as 1. So I can rewrite 1 as follows. So 1 can be rewritten as, in place of dy over dx, I would be placing v positive x times dv over dx is equal to, so as a negative sign there, in place of y we substitute vx, x is retained as it is, and then we substitute vx followed by x squared. Now this is equal to, I can take a x out from here, so I would get negative of v times x squared of 1 positive v divided by x squared. So clearly I can cancel the x squared, and that is giving me negative of v of 1 positive v. Now there is a v positive x into dv over dx, so this v can be pushed to the right hand side. So if I were to do that, I would get x times dv over dx is equal to negative times 1 is, in fact negative v times 1 would give me negative v followed by negative v squared. This comes, I get a negative v, so I now have negative 2 times v and negative v squared. Now we can do some rearrangements, so I can rewrite dv divided by negative 2 times v negative v squared is equal to dx divided by x. I can take the negative sign out, and if I were to do that, this will become positive. In fact, I can take this negative sign and place it over here, and this will become positive. So just rearrangements. Now I can clearly integrate these two things, and we would be able to solve and simplify. So let's get it done. Now to integrate this, I got a dv divided by v squared positive 2 times v. Now this is a perfect square. Say for example, if I were to expand this, say v positive 1 raised to the power of 2, I get a v squared positive 2 times v and positive 1. But I will have to get rid of this 1. So if I were to place a negative sign, in other words negative 1 here, that would be same as v squared positive 2 times v, right? That's exactly what I wish to do. So I would rewrite this quantity as integral dv divided by v positive 1 raised to the power of 2 negative 1, which is equal to integral dx over x. Now negative 1 is same as rewriting it as negative 1 squared, right? And thereby I can use the formula now. Now there is a formula which we can use. Integral dx divided by x squared negative a squared is equal to 1 over 2 times a ln modulus of x minus a divided by x positive a positive arbitrary constant c. So I can use this formula. This is a very important formula. You can remember this and it will come in handy. Now instead of x I got v positive 1 and for a I got 1. So this entire thing is going to be rewritten as 1 over 2 times of a is 1 and ln of x is v positive 1 negative 1 divided by v positive 1 positive 1, and in this case it's going to be negative ln of x positive arbitrary constant c. Now clearly I can get rid of this positive 1 negative 1 and I can rewrite this as 1 over 2 times ln, I don't have to place the modulus sign, you can just simply rewrite it as v over v positive 2 negative, I can bring the negative sign to this side, so that's going to give me x is equal to c. So this is what I've got. Now what I wish to do is now I've got a 2 here, right? So I will have to get rid of this 2. So just taking that into account, what I will do is, this is actually ln x, this cannot be x, because when negative ln x comes to this side, this has to be ln x. So what I will have to do is I will have to get rid of this 2. So to get rid of this 2, what I will do is I will multiply by 2 both sides. So when I do that, this is going to give me ln v over v positive 2 positive 2 times ln x is equal to 2 times c. So this is what we have got. Now there is a formula which says that if I have got something like this, b times ln a, I can write this as ln of a raised to the power of b. So by this formula I can rewrite this as ln of v over v positive 2 positive, I can move this 2 over here, writing it as ln of x squared is equal to 2 times c. Now there is another formula which is ln of a positive ln of b is equal to ln of ab. So by this formula I can rewrite this as ln of x squared times b over v positive 2 is equal to 2 times c. I'm going to use this formula, ln a to the base e, if it is equal to y, then I can write a is equal to e raised to the power of y. So by that formula, this is going to be x squared times v over v positive 2 is equal to e raised to the power of 2 times c. But my y is equal to v times x and my v is y over x. So if I were to substitute that, this is going to give me x squared times y over x divided by y over x positive 2 is equal to e raised to the power of 2c. Now x and x can be cancelled, so that is going to give me x times y. If I were to take the LCM, I get y positive 2 times x divided by x is equal to e raised to the power of 2 times c. Now I can flip it. If I flip it, I get x squared times y divided by y positive 2x is equal to e raised to the power of 2 times c. I can cross multiply. If I cross multiply, I get x squared times y is equal to e raised to the power of 2c times y positive 2x. If you don't want this e raised to the power of 2c, you can write that as x squared times y is equal to some constant times of y positive 2 times x. So this is my final solution to this question. Students, we're given this question and we are expected to solve, and we will have to first ascertain if it is a homogeneous equation or not. So for that, what I wish to do is I would like to move my dy over dx to the left and club all other terms on the right hand side. So this is going to be y times sine of y over x negative x divided by x times sine y over x. Now clearly the degree of y is 1, the degree of x is 1, the degree of this y is 1, this x is 1, and comparing it to the denominator, we see the degree of y here is 1, the degree of x is 1, and the degree of this x is 1. So clearly this is a homogeneous equation. So as a first step, what we will do is we will just take, let y be equal to v times x, and then dy over dx is going to be v positive x times dv over dx. So if I were to take this as 2, then I will be substituting this in 2. So therefore I can rewrite 2 as, in place of dy over dx, it's going to be v positive x times dv over dx is equal to, in place of y I will substitute vx. So it's going to be sine of vx over x negative x divided by x times sine of vx over x. So I can cancel the x that I see here, and that subsequently would give me v times x sine v negative x divided by x times sine v. Now I can move this v to the right, and that would give me v times x sine v negative x negative v. Of course I have a denominator as x times sine v. I can rewrite this as v times x sine v. I take the LCM, I would get v times x sine v over x times sine v. Now clearly I have to have one more x here. I think I missed that out. So let me place that x. Now clearly vx sine v and vx sine v can be cancelled, and that would leave me with negative x times x into sine v. Of course on the left hand side I got x times dv over dx. I will move all the x to the one side and v to the other side. So this is going to be sine times v dv is equal to negative x. And probably what I should have done here is, I can clearly see that there is a presence of a x here and a x there. So what I can do is I should have cancelled these two x's, and that would leave me with sine v dv. Of course that's right, and I can push this dx here, so this is going to be a dx. That's fine. I got a negative sign, I can place that negative sign, I can move the x down. Fair enough, right? So we have to integrate this. So if I were to integrate sine v, I get negative cos v. I integrate this, I get ln of x. Of course we got a constant positive c there, we have to place that. Now I can rewrite, I know that y is equal to v times x, so therefore v is equal to y over x. So what I can do is I can substitute that term y over x over here, and if I were to do that I would get negative cos of y over x is equal to negative ln x positive arbitrary constant. See, now what I can do is I can get rid of this negative sign. So if I were to get rid of this negative sign, I need to just multiply by negative, right? So multiply by negative 1 all through. So this is going to be cos of y over x is equal to ln x negative c. Now I can rewrite this negative c as positive of negative c, and then rewrite this entire thing as cos y over x is equal to ln x positive arbitrary constant c prime. That's it. This can be anything. You want to name it as k, you can name it as k. You want to name it as some L, you name it as some L. So the final solution for this question is this. Thank you, students. We'll move on to the next question. Students, we're given this question. We are expected to solve x times dy over dx is equal to y positive 2 times the root of y squared negative x squared. Now, what I wish to do is I would like to move this x down. So I would have dy over dx is equal to y positive 2 times root of y squared negative x squared divided by x. So this is what I've got. Now you can clearly see the degree of y is 1. Now we got a square root, so that would mean we are talking about the degree of y to be equal to 1, because once you apply the square root, you got a 2. Upon applying the square root, this would be reduced to degree 1. So we got a 1 here, we got a 1 here, we got a 1 here, and we got a 1 here. So clearly this is a homogeneous equation, and so what I would do is I will say let y be equal to v times x, and then I will differentiate this with respect to x. When I do that, I get dy over dx is equal to v positive x times dv over dx. So this is what I've got. Now what I wish to do is I would like to take this as 2, and I will be rewriting 2 using this. So this in turn was going to give me v positive x times dv over dx is equal to, in place of y, I'm going to substitute vx followed by v squared x squared negative x squared divided by x. This is vx positive 2 times. I'm going to take x squared out, so that is going to give me v squared negative 1 divided by x. Once the x squared comes out, this is going to give me x there. So 2 times x root of v squared negative 1 divided by x. I can cancel the x's out. So now continuing on, I can move this v to the other side. So that would give me v positive 2 times the root of v squared negative 1 negative v. I got a positive v and a negative v. They can be cancelled, and that in turn would give me 2 times root of v squared negative 1. And on the left I got a dv over dx. Of course there is an x there. Now rearranging, this is going to be dv over 2 times of root of v squared negative 1 is equal to dx over x. Integrating both sides, I would have something like this. Now for this I would like to use the formula. Now since integral dx over root of x squared negative 1 is equal to, there is a formula, so that is going to be ln of x positive root of x squared negative 1. So we can use this formula. Of course there is an arbitrary constant c. So in place of x I've got v. So this can be rewritten as equal to, in fact I need to use implies because I got a equal to already. So this is going to be 1 over 2 times ln of, in place of x I will have to use v positive square root of v squared negative 1 is equal to ln of x positive c. So this is what I've got. Now I would multiply by 2 both sides. Now when I do that, I would get
ln of v positive root of v squared negative 1 is equal to 2 times ln x positive 2 times c. I can move this 2 over here, so this is going to be ln of x squared positive 2 times c. On the left side it's going to be ln of v positive root of v squared negative 1. Now I can move this ln x squared to the left, so this is going to be ln of v positive root of v squared negative 1 negative ln x squared is equal to 2 times c. Now there is a formula which we know, ln of a negative ln b is equal to ln of a over b. So by this is going to be rewritten as ln of v positive root of v squared negative 1 over x squared is equal to 2 times c. There is also another formula which is ln a to the base e if it is equal to y. A is equal to e raised to the power of y. So by this formula I can write v positive root of v squared negative 1 over x squared is equal to e raised to the power of 2 times c, but my y is equal to v times x, so therefore v is equal to y over x. So this is going to be y over x positive root of y squared over x squared negative 1 divided by x squared is equal to e raised to the power of 2c. I'm going to use the space here, so this is going to be y over x positive root of y squared negative x squared divided by x squared is equal to e raised to the power of 2c. Now we can rewrite this as y over x positive root of y squared negative x squared. Root of x squared gives me x divided by x squared is equal to e raised to the power of 2c. Now this can be rewritten as y positive root of y squared negative x squared divided by LCM is x, and I got a x squared here. I can flip it, so this is going to be x cubed. This is going to be e raised to the power of 2 times c. I can cross multiply this and write this as y positive root of y squared negative x squared is equal to e raised to the power of 2 times c times x cubed. I can replace this e raised to the power of 2 times c by means of an arbitrary constant. So I can write this as y positive root of y squared negative x squared is equal to sum c prime times x to the power of 3. So this is my final solution to this question, students.
Students, we are going to be looking into reducible homogeneous equations, and the type we are going to look into two important types. So one is dy over dx is equal to a times x positive b times y positive c. The denominator is say a dash x positive b dash y positive some c dash. Now for case 1, if you were to take the ratio, say a divided by a dash, clearly a divided by a dash will not be equal to b divided by b dash. So this is very important, have that in mind. Now for case 2, okay, for case 2, a divided by a dash will be equal to b divided by b dash, probably some constant times. Okay, this is going to be case 2. So in case 2, h value and k value are going to be undefined or indeterminate. Now you will understand what exactly is the meaning of h and k within a few minutes. Now I will be doing questions related to case 1, and then I will follow it up by doing questions related to case 2. So foremost, let us just start off by performing a question related to case 1. So first, let me give you this question. Solve, say dy over dx is equal to y positive x negative 2 divided by y negative x negative 4. Now you can clearly see that from here the value of a is 1, a dash is negative 1, value of b is 1, and b dash is 1. So just find out what is a over a dash. A over a dash is 1 over negative 1, which is clearly not equal to b over b dash. B over b dash is 1 over 1. So this is actually, we are looking at case 1 homogeneous system. So to solve case 1 homogeneous system, what should we do? We need to make the following assignment. We need to take x is equal to capital X positive H and lowercase y is equal to capital Y positive K. This is the substitution we will have to make. Now when we make this substitution, if I were to take this as 1, I can rewrite 1 to be as, say, take this value, put it here. So we are going to have, no, before I could do that, I need to find what is dx. Now dx is equal to capital Dx and my dy is equal to capital Dy. That's also critical. So I can replace dy, which is capital Dy, and dx, which is capital Dx, to be equal to, in place of y, I'll substitute capital Y positive K. In place of x, I'll substitute capital X positive H followed by negative 2 divided by capital Y positive K negative of capital X followed by negative H negative 4. I can rewrite this as, I'm going to write it like this: X positive Y positive H positive K negative 2 divided by, this is actually negative x, so we can't run away from that negative sign, followed by a y, and I'm going to rewrite this as probably, let me just have it like this, so negative h positive k negative 4. So this is what I've got. Now what I wish to do is, I would like to take h positive k negative 2 to be equal to 0 and negative h positive k negative 4 is equal to 0. So if I were to take this as 2, so therefore I can rewrite 2 as x positive y, this is 0, divided by negative x positive y, this is 0, and on the left I got capital dy divided by dx. So now the degree of the numerator is same as the degree of the denominator, so it is homogeneous in nature. So having obtained that, what I'm going to do is, I'm going to say let capital Y be equal to v times x. So this would mean dy over dx is equal to v positive x times dv over dx. Okay, so differentiation. So if I were to take this as 3, so therefore I can rewrite 3 as, in place of dy over dx, I'm going to substitute this, so it's going to be v positive x times dv over dx is equal to x. In place of y, it's going to be vx, negative x, in place of y is going to be vx. So I can take a x out, that will give me 1 positive v divided by, I can take a x out, I don't have to take negative x out, so let it be positive. So this is going to be negative 1 positive v. So this is what I've got. So clearly the x's gets cancelled, and I'm going to write this as v positive 1 divided by v negative 1. So this is what I've got. And on the left hand side I've got a negative, I should say a positive v. So I'm going to push that positive v to this end. That will become negative. So I've got x times dv over dx is equal to v positive 1 divided by v negative 1 followed by a negative v. That is equal to, taking the LCM as v negative 1, I get v positive 1 negative v squared negative negative positive v. This is what I've got. So this can be rewritten as
my negative v squared followed by 2 times v followed by 1 divided by v negative 1. This is what I've got. So now the question remains is we will have to solve it, and before we could solve it we need to use variable separable, right? So we need to take the dv's together and the x's together. So this is going to be v negative 1 divided by negative v squared positive 2 times v positive 1. This entire thing is times dv is equal to dx divided by x. So this is what I've got. So now the question comes is we will have to make some substitution. So let's substitute. So I'm going to solve this first. So integrating both sides. So let me make the substitution. So what I'm going to do is I'm going to say let negative v squared positive 2v positive 1 be equal to some t. This is going to be negative 2v positive 2 times dv is equal to dt. Now if I were to take negative 2 out, this would give me a v negative 1 times dv, right? Negative 2 times v would give me negative 2v, negative 2 times negative 1 would give me positive. So that's fair enough. So this is going to be dt. So I can make the substitution. So this is going to be dt 1 over 2 with the negative sign divided by this entire thing is going to be my t is equal to integral dx over x. So this is going to be ln of t, okay, of course there's a negative 1 over 2 there, is equal to ln of x positive. I can just place a ln c. Okay, so it depends on you. Since I've got ln everywhere, I can place ln c. Now the question comes is I will have to get rid of this negative 1 over 2. So to get rid of negative 1 over 2, either you can multiply every quantity by negative 1 over, by 2. So if I were to multiply by negative 2, so I would be getting ln t is equal to negative 2 times ln of x, and this is going to be negative 2 times ln of c, and I can actually I can bring this quantity to this side. So this is going to be ln my t. My t is actually this entire quantity, right? So let me make that resubstitution back again. So this is going to be 1 positive 2v negative v squared, and if I were to bring this to this side, this is going to be positive 2 times ln x, and I've got negative 2 times ln c. That's fine. So now what we will have to do, we can take this 2 onto this end, so that would mean I get a ln x squared positive ln of 1 positive 2 times v. Now let's go back to the substitution. What is the substitution we had? We took y is equal to capital V times x. So from here v is equal to capital Y over x. So I need to place it that place these values back. So it's going to be 1 positive 2 times capital Y over x negative y squared over x squared is equal to, now I can actually take this as c squared, right? It's negative times c squared, that's going to be 1 over c. Probably you can either use it as some constant, so you can place some constant k. It's not going to matter, so you can do that. Now what I wish to do is I will have to club these two quantities together, and now before I could use this as some k, let me just retain, because I need to get rid of this logarithm. So let me just retain ln, this is going to be c negative 2, because this 2 goes over here, it's going to be c negative 2. So let me just retain it as it is.
So now the time comes to clubbing these two together. So I would have to use some space. So what I will do, I will use the space here. So ln, we know that ln of A positive ln of B is equal to ln of A times B. So I would like to club these two things together. So that would give me so that's going to be ln of x squared times 1 positive 2 times y over x negative y squared over x squared is equal to ln of c negative 2. Now clearly you can see that this quantity can be pushed inside because of the distributive property. So I'm going to take this inside, x squared inside, that will become x squared positive 2 times x will get cancelled, giving me xy, and then followed by y squared. So this looks really neat. And of course on this side it's going to be ln of c raised to the power of negative 2. Now I can drop log both sides, so that would mean I get x squared positive 2 times xy negative y squared is equal to c raised to the power of negative 2, or that's fine, it's not going to impact us in any way. Now the much important point is we will have to make the substitution. So what is the substitution we started with? We started with the substitution that x is equal to capital X positive h and y is equal to capital Y positive k. This is a substitution we add, but the much important point is that we will have to, clearly you can see here, we add h positive k negative 2 is equal to 0, negative h positive k negative 4 is equal to 0. So from here I can clearly find out by cancelling h with negative h, I can get 2 times k, I'm just adding it, is followed by negative 6 is equal to 0. So from here 2 times k is equal to 6, so from here k is equal to 3. Now if k is equal to 3, I can just take it and substitute it here. So if I were to do that, I'm just going to substitute k is equal to 3 here. So that means h positive 3 negative 2 is equal to 0. So that means h is equal to negative 1. So clearly you see everything is working out. H is equal to negative 1 and my k is equal to 3. I'm just going to substitute it here. So if I were to say x is equal to capital H negative 1 and capital X has to be substituted. So capital X is equal to x positive 1. That is one substitution. And my k is equal to 3. So that's going to be y is equal to capital Y positive 3. So that means capital Y is equal to y negative 3. So everything is working out perfectly. So all I need to do is take the values of capital Y, substitute here, take the value of capital X and make the substitution here. So let me do that. So this is going to be, if I were to substitute it, so let me just take this as sum 4. So therefore I can say 4 can be rewritten. I'm going to use the space here. So that's going to be x positive 1 raised to the power of 2 positive 2 times x positive 1 times my y is y negative 3 negative y negative 3 raised to the power of 2 is equal to some constant k. I can just put that as some constant k. So this is what we have got, and the perfect answer to the solution. So this is the exact answer to the solution for that particular question. If you want, you can distribute it and place the final answer, but I think this is the exact right spot to stop. So thank you, students. We can see another example. Welcome, students. In this class, the topic is reducible homogeneous equations. So this is probably the next varieties of homogeneous equations that we will have to focus on. It is very critical that we understand this. Now, the general form is dy over dx is equal to ax positive by positive c divided by px positive qy positive r. Now, you can clearly see the numerator is a linear equation and the denominator is also a linear equation. Now, if you were to see the degree of x, it is 1, the degree of y is 1, but the degree of constant, this is a constant present here and its degree is 0. So clearly it isn't a homogeneous equation. And if you were to compare the numerator with the denominator, you can see the same picture. The degree is 1 here for x, the degree is 1 here for y, but r is a constant, its degree is 0. But we are talking about the degree of the numerator being equal to the degree of the denominator for homogeneous equations, which totally fails here. So having got that, what we are going to do is we are going to be making sure that we can adopt the concept of some level of manipulation in converting the linear type into a homogeneous equation type. So that is our objective. So having got that, so let me just place this in a box. So this is the pattern that we will be looking forward. So now we are given a question. Say solve, say the question is dy over dx is equal to x positive 2y negative 3 divided by 2x positive y negative 3. Now, if you would remember, in variable separable, we took the coefficient that is present here, added with the coefficient that was present here. So we were looking for b1 added with a2, and if we got it to be equal to 0, then we multiplied the quantities and then we simply integrated and we got the result. So when we're talking about b1, I'm talking about the coefficient of y here. When I'm talking about a2, I'm talking about the coefficient of x here. So the coefficient of y added with the coefficient of x, if it produces 0, then we wouldn't have the requirement to handle or requirement to do the process which I'm going to show you now. That is not really required. You can directly integrate it by cross multiplication. I'm going to show you an illustration for that. But in the meantime, clearly we can see that the coefficient of y added with the coefficient of x is not equal to 0. So that is the reason we are trying to convert this system into a homogeneous equation. So for that, the first thing that we will have to do is we will have to take a substitution that x is equal to capital X positive h. So we are going to do that, and then let me write that. Let x be equal to capital X plus h and y be equal to capital Y positive k. Now capital X, capital Y, they are variables, but h and k are constants. So maybe you can write that h and k are constants. So having set this, we will have to rewrite the given system. So foremost, I will differentiate this. So differential of x would give me dx. Differentiation of capital X is going to be capital dx. So this is going to be dy. This is going to give me capital dy. So let me rewrite equation 2 or system 2. So 2 can be rewritten as, in place of dy, I'm going to say capital dy divided by, in place of dx is going to be capital dx, is equal to, in place of x is going to be capital X positive h positive 2 times capital Y positive k negative 3 divided by 2 times of capital X positive h positive capital Y positive k negative 3. I'm going to rewrite this. So this can be rewritten as x 2 times y, and then I've got a h and a 2k and a 3.
and this has to be followed by 2 times x, positive y, positive, I have a 2 times h, and a k and a 3. So what I'm going to do is I'm going to take, let h positive 2k negative 3 be equal to 0, and 2 times h positive k negative 3 is equal to 0. So if I were to take this as 3, so therefore I can rewrite 3 as x positive 2 times h. This entire thing is going to be 0, so probably you can place that 0, divided by 2 times x positive y positive, this entire thing is 0. On the left you got capital dy and capital dx. So this is actually x positive, in fact 2 times y, this should be 2 times y, it's not h there, it's 2 times y, and this is equal to 2 times x positive y. So this is clearly homogeneous, which is homogeneous in nature. Okay, now because it is homogeneous in nature, what I can do is let y be equal to capital V times x. So differentiating this, I get dy over capital dx is equal to v positive x times dv over dx. So if I were to take this as 4, I can rewrite 4 to be as, in place of dy over dx, it's going to be v positive capital X dv over dx is equal to x positive y is vx divided by 2 times x positive v times x. I take a x out, I get 1 positive 2 times v divided by, take a x out, I get 2 positive v. Now clearly the x and x can be cancelled, so this is equal to 1 positive 2 times v divided by 2 positive v. I can move this v to the other side, so this is going to give me x times dv over dx. Now if I were to take the LCM, I get 1 positive 2v negative v times 2 positive v over 2 positive v, which is equal to 1 positive 2 times v negative 2v negative v squared divided by 2 positive v. Now clearly positive 2v negative 2v can be cancelled, so that's going to give me 1 negative v squared divided by 2 positive v. On the left I get x times dv over dx. Now we can always use variable separable, so I'm going to do that here. So this is going to be dv over 1 negative v squared, and I can push this, so it's going to be 2 positive v is equal to dx over x. So I can integrate both sides. So if I were to integrate both sides, now I can make some substitutions for this. So what I would do is I would like to rewrite this quantity as 1 positive v positive 1 times dv divided by 1 negative v squared is equal to integral dx over x. Now this can be rewritten as integral 1 over 1 negative v squared. That's fine, probably that's the best way to write it. So followed by, I have to take in 1 positive v divided by 1 negative v squared. Okay, like that. dv is equal to integral dx over x. So that's fair enough. So we got that. So now what we will do is we will have to use this formula. So what is the formula I'm going to use? We know that I've already mentioned this formula. We know that
integral dx divided by x squared. In this case, it's a squared negative x squared. So a squared negative x squared is equal to 1 over 2 times a ln of modulus of, is going to be a positive x divided by a negative x. So this is the formula plus constant c that we will be using. So if I were to use this, this can be rewritten as 1 over my a is 1 times ln of 1 positive v divided by 1 negative v. Okay, now I got this 1 positive v times dv divided by 1 negative v squared. So let me write that down, 1 positive v. Now this one, 1 negative v squared, I can rewrite 1 negative v squared as 1 squared negative v squared, which is nothing but 1 negative v times 1 positive v, right? So if I were to do that, this is going to be 1 negative v times 1 positive v times dv. So in fact I should place implies because this is all left hand side. So this is equal to integral dx. So let me just retain it like that just for time being. Now I can clearly cancel 1 positive v, 1 positive v, and then this would imply I get 1 over 2 ln of 1 positive v divided by 1 negative v positive integral of dv over 1 negative v. Now integral of dv over 1 negative v, we can make some substitution using log. So what I'm going to do is I'm going to say let 1 negative v be equal to say some t. So negative dv is equal to dt. So this is going to be negative dt over t, which is nothing but negative ln t, which is nothing but ln of t is 1 negative v. Of course I got a negative sign, probably I'll just place a negative sign here. So what I would do is I will just substitute, in place of this I will substitute this. So this is going to be negative times ln of 1 negative v is equal to ln of x positive c. So this is what I've got. So now I can actually rewrite this with this negative sign being removed. In fact, by distributive property we can get rid of that. So this is going to be 1 over 2 times ln of 1 positive v divided by 1 negative v negative ln of 1 negative v is equal to ln of x positive c. In fact, I don't have to place this modulus sign, I can just place a parenthesis. Now if I were to multiply by 2 throughout, so this is going to give me ln of 1 positive v divided by 1 negative v, and then this is going to be 2 times of ln of 1 negative v. I'm multiplying by 2, so it's going to be 2 times ln of x positive 2 times of c. Now I can make the substitution. What is the substitution? We know that capital Y is equal to v times x, so my capital V is equal to y over x. So I will have to take this value and substitute it here. So if I were to do this, I would get ln of 1 positive capital Y over x divided by 1 negative capital Y over x negative 2 times ln of 1 negative capital Y over x is equal to 2 times ln x positive 2 times c. So we will have to do some simplification. So for that I will have to move over to the next page. So we can perform the simplification. So this is going to be ln of x positive y divided by x, and this is going to be x negative y divided by x, right? Negative 2 times ln of x negative y divided by x is equal to 2 times ln of x positive. You can either write it as 2 times c, or you can write it as ln c, 2 times ln c, because you have logarithmic being present everywhere, so that doesn't matter because it's still going to be an arbitrary constant. So you got these two terms. Now what we can do is we can actually rewrite this. Now in this case the x and x can be cancelled here, right? So that would mean I get ln of x positive y divided by x negative y, negative 2 times. I can rewrite this as ln of x negative y negative ln of x, right? So this is what I've got. On the right hand side it's going to be 2 times ln x positive 2 times ln c. I can rewrite this as ln of x positive y divided by x negative y minus 2 times ln of x negative y positive 2 times ln of x is equal to 2 times ln of x positive 2 times ln of c. Now these two things can be cancelled. Now I can rewrite this as ln of x positive y divided by x negative y. I can push this 2 to the other end, so it's going to be ln of x negative y raised to the power of 2 is equal to 2 times ln c. Now I've got ln a minus ln b, which can be written as ln of a over b. So if I were to rewrite this, this is going to be ln of a x positive y divided by x negative y divided by my b. My b is x negative y raised to the power of 2, right? So this is actually spreading all through this region. So this is equal to 2 times ln of c. Now if I'm going to simplify this, so this is actually over 1. So if I were to rewrite this, I can rewrite this as ln of x positive y divided by x minus y raised to the power, this is 2 and this is 1, so this is going to be 3. So this is going to be ln 2 times ln c. I can write it as c squared. Now we got ln on the left, ln on the right, so removing ln both sides we get, so you get x positive y divided by x negative y raised to the power of 3 is equal to c squared. Now from here you get x positive y is equal to c squared times x negative y raised to the power of 3. Okay, now we have almost reached a solution, but if you were to notice, all of these are all capital X capital Y, and we have executed the entire solution using capital X and capital Y. So now it's time for us to resubstitute the values that we took, because we started with let x be equal to capital X positive h and y be equal to capital Y positive k, and we also took h positive 2k negative 3 equal to 0, if you would remember, and followed by 2h positive k negative 3 is equal to 0. Now I can make the substitution back here, but the only thing that prevents me is the value of h and value of k. So we need to obtain the value of h and value of k. Now if you remember, I have taken h positive 2k negative 3 is equal to 0 and 2h positive k negative 3 is equal to 0. So what I'm going to do is I'm going to multiply this by 2. So this is going to be 2 times h, and this is going to be 4, and this is going to be 6. So now I'm going to add them both. In fact, I'm going to subtract. So that means I have to change the sign. Plus is the minus, minus is the plus. So if I were to do this, 2h and 2h, they get cancelled. I get 4k, negative k, that means 3k. Now negative 6k and positive 3k, that's going to give me negative 6 added with positive 3 would give me negative 3 is equal to 0. So 3k is equal to 3, therefore my value of k is 1.
So I've got the value of k. Now to get the value of h, all you need to do is to substitute it here. So just go and substitute the value of k over here, because I have not changed this system at all. So this is going to be 2 times h plus 1 negative 3 is equal to 0. This is going to be 2 times h minus 2 is equal to 0. So 2 times h is equal to 2, so h is equal to 1. So I've got the value of h and k. So from here, if I were to substitute, x is equal to capital X positive 1. So that means x minus 1 will be my capital X, and over here I get y is equal to capital Y plus 1. So capital Y is going to be y negative 1. So this is the substitution we will have to make here. So all these things are for your understanding. You don't have to show them. All you need to do is to just ensure that you have achieved the value of h and k, and then re-engineer to get the capital value, or in other words to get the value for capital X and capital Y. So if I were to take this as sum 5, so I can state here, therefore I can rewrite 5 to be as, in place of capital X, I'm going to say x negative 1 positive capital Y, y negative 1 is equal to, say, sum c squared, and x minus h. So capital X, that's going to be x minus 1 negative capital Y, y negative 1, and that has to be raised to the power of 3. So I can rewrite this as x positive y negative 2 is equal to c squared. I can substitute some k, and this one is going to be x negative 1 negative y, and negative 1 with positive 1, it will get vanished, right? Because this is negative 1 and this is going to be positive 1. So this is going to be raised to the power of 3. So you've got a system in this fashion, and if you want, you can push this 2 to the other side and write this as x positive y is equal to some k times x negative y raised to the power of 3, say some positive 2. Either this, or you can stop here. Depends on your requirement. So that completes the solution to this question, students. Yes, I understand this is a bit lengthy, but it doesn't mean that you can skip this, because knowledge is power. So students, we are given this question. First, let us find out what is dy over dx. So I will move this to the other end. So that would mean 4 times x positive 8y positive 5 of dy, and on this end it's going to be 3 times y positive 2 times x positive 4. This is dx. So dy over dx is going to give me, this is going to give me 3 times just one issue here. This is actually not 8. This is, just for the sake of this illustration, we will have to take this as 6, so that I can demonstrate to you the case. So having obtained that, so we will have 3 times y positive 2x positive 4 divided by 4 times x positive 6y positive 5. So this is what we have got. Now I can rewrite this as 2x positive 3y positive 4 divided by, now the denominator is going to be 2 times of 2x positive 3y positive 5. Okay, that's fine. Now just compare this to our a over a dash and just get the value of a over a dash. Now my a is 2 and my a dash is 4, so I'm getting 1 over 2 for this. Okay, that's fine. Now connect, or I should say compare it with b over b dash. My b is 3 and my b dash is 6. So what do I get? I get 1 over 2. So clearly you can see that a over a dash is equal to b over b dash. So that means h and k are undetermined or indeterminate or undefined. Okay, so we will not be able to use the same principle which we have seen in case 1. That is the reason I have taken the value of y to be as 6, so that I can demonstrate to you how exactly this works. Now we will be using this, so I would be taking dy over dx to be equal to 2 times x positive 3y positive 4 divided by 2 times of 2x positive 3y positive 5. So this is the required equation or system, I would say, that we would take. Now what I would do is I will let 2x positive 3y be equal to some v. I differentiate this, I get 2 positive 3 times dy over dx is equal to dv over dx. So from here, what do we get from here? So 3 times dy over dx is equal to dv over dx. I can move the 2, so I get negative 2 there, and it can be further rewritten. Dy over dx is equal to 1 over 3 times dv over dx negative 2. So why do I do all these things? I did all this so that I can actually substitute in place of dy over dx. I can make this substitution. So let me just take this as 2. So therefore I can rewrite 2 as, so in place of dy over dx, I'm going to substitute 1 over 3 of dv over dx negative 2, and that is equal to 2 times of x positive 2y. 2 times of x positive 2y is going to be my v. So let me place that v followed by a 4 and 2 of 2x positive 3y. That's going to be my v again. So it's going to be 2v positive 5. Now what I can do is I can cross multiply. If I do that, I get 3v positive 12 divided by 2v positive 5. I got a negative 2, so I push it, I get positive 2. So now I take the LCM as 2v positive 5. That would give me 3v positive 12 positive 4v positive 10. I can rewrite that by adding this and that, 7v, by adding this with this, that's 22 divided by 2v positive 5. On the left I get dv over dx. Now it's all lowercase, so I need to cross multiply. So that would mean I get 2v positive 5 divided by, when I say cross multiply, I'm actually connecting this with this. Okay, I hope you're following it. So 2v positive 5 divided by 7v positive 22 times dv is equal to, so I just got a dx there. That's it. I have a dx. So now I need to integrate these two quantities. Now you can clearly see the degree of the numerator and the denominator are same. So that would mean I will have to divide 2v positive 5 by 7v positive 22. Now I need to get a 2v there. So the only possibility is multiplied by 2 over 7. So when I do that, that gives me 2v followed by 2 over 7 multiplied by 22. That's going to be 44 over 7. So I need to subtract. So that gives me 5 negative 44 over 7. So if I were to simplify, it's going to be 35 negative 44 over 7. So that has to be subtracted, and that would give us, so this is going to give me negative 9 over 7. So the quotient is 2 over 7. Place that 2 over 7 followed by negative 9 over 7 divided by the denominator 7v positive 22. This has to be integrated, right? So this can be rewritten as 2 over 7 times dv negative 9 over 7 times dv over 7v positive 22 is equal to integral dx. So upon integration I would get 2 over 7 times v negative 9 over 7 times the ln of 7v positive 22. Quotient of v is 7, so it's going to be 7 squared is equal to, when I integrate dx, I get x positive c. Now I can get rid of the 7 squared, so that means I will be multiplying by 7 squared throughout, and that would give me a 7 here, so it's going to be 14v followed by negative 9 times ln of 7v positive 22 is equal to 49x positive 49c. But my v is 2x positive 3y, right? So substitute it here. So if I were to take it as 3, so therefore 3 can be rewritten as, so it's going to be 14 of 2x positive 3y negative 9 times ln of 7 times of 2x positive 3y positive 22. Of course, the right hand side stays as it is. Now you can either bring these things down or simplify them, depends on your requirement. So what I would do is I would just retain it as it is, 14 times of 2x positive 3y negative 9 times, at least in this case 7 times 2 is 14x, and this is going to be 21y and positive 22. So that's the best we can think about it now. So this is a good place to stop, students, and this is a beautiful solution. If you want, you can always get rid of the parenthesis and then club 49x with this quantity, but that wouldn't be necessary for now, and this is a good place for us to stop. Students, we're given the question, solve dy over dx is equal to x positive y positive 3 divided by 2x positive 2y positive 1. This is a linear form in the numerator and a linear form in the denominator, and hence I would be attempting to reduce this into a homogeneous equation. So first what I will do is I will just take, let capital X be equal to let small x be equal to capital X positive h, and then y is equal to capital Y positive k, where h and k are constants. So if I were to differentiate, this is going to give me dx is equal to capital Dx and dy is equal to capital Dy. So I'm going to take this as 1, and I'm going to rewrite 1 as, in place of dy it's going to be capital Dy, in place of dx it's going to be capital Dx, in place of x it's going to be capital X positive h, in place of y it's capital Y positive k positive 3 divided by 2 times of capital X positive h positive 2 times of capital Y positive k positive 1. I can rewrite this as capital X positive capital Y positive h positive k positive 3 divided by 2 times of x positive 2 times of y positive 2 times h positive 2 times k positive 1. Now what I'm going to do is I'm going to take, let h positive k positive 3 is equal to 0 and 2h positive 2k positive 1 is equal to 0. Now you can solve it and find the value of h and k. Probably I will just do that. So I will multiply this by 2. So this is going to give me 2h positive 2 times k positive 6. This is 2h positive 2k positive 1 is equal to 0. Now if I were to subtract 6 negative 1, that's 5 is equal to 0. So which is basically contradiction to our number theory concepts. So what is the understanding here? The understanding here is that we cannot adopt this technique to solve this question. So what is the technique that we need to adopt? So I'm going to show you the technique here. So we got dy over dx to be equal to x positive y positive 3
divided by 2 times x positive 2y positive 1. Now I can rewrite the denominator as 2 times of x positive y positive 1 and the numerator stays as it is. Now instead of making this substitution, small x is equal to capital X positive h and small y is equal to capital Y positive k, I'm going to say let x positive y be equal to v. Right? So if I differentiate, I get 1 positive dy over dx. Dx is equal to dv over dx. So therefore dy over dx is dv over dx negative 1. So this is the substitution which we will use. So if I were to take this as 2, right, therefore I can rewrite 2 as, in place of dy over dx, I'm going to use dv over dx negative 1 is equal to, in place of x positive y, is going to be v positive 3 divided by 2 times of v positive 1. Now I can move this negative 1, so that would give me dv over dx is equal to v positive 3 divided by 2 times of v positive 1 positive 1. I can take the LCM as 2 times v positive 1 and that would give me v positive 3 positive 2 times v positive 1, which can be added giving me 3v positive 4 over 2v positive 1. So now we have got dv over dx to be equal to 3v positive 4 divided by 2v positive 1. So now I would like to use variable separable. So that would mean I got 2v positive 1 divided by 3v positive 4 on one side times dv is equal to dx on the other hand. Now the degree of the numerator and the denominator are one and the same, so we will have to do some manipulation in this case. So the manipulation is divide 2v positive 1 by 3v positive 4. Now clearly I need to get a 2v. So how do I get it? Clearly if I were to multiply 3v by 2 divided by 3, that would cure my requirements, right? So this would give me this, followed by a positive 8 over 2 over 3 multiplied with 4 would give me 8 over 3. So now if I were to subtract, I will have to subtract 1 followed by a negative sign and 8 over 3. That's going to give me negative 5 over 3. So all these things are all working column for your understanding. So you don't have to do these things, but just for your understanding. So this is actually the quotient is 2 over 3 followed by 5 over 3 the remainder and divided by 3v positive 4. This is with dv and this is with dx. Now what I can do is I can rewrite this as 2 over 3 times dv followed by a negative 5 over 3 times dv divided by 3v positive 4 is equal to dx. Now I would like to integrate. So this is integration. So this is going to give me 2 over 3 times v. This is going to give me 5 over 3. This is going to be ln of 3v positive 4. And I need to divide by this coefficient, which is going to be 3. And this is going to be x positive constant c. So I can rewrite this as 2v over 3 negative 5 over 9 ln of 3v positive 4 is equal to x positive c. But what is my v? But my v is x positive y. So I will have to substitute it here. Probably I will use this space here. So that would mean I have
2 times of 2 over 3 of x positive y negative 5 over 9 of ln of x positive y. So it's going to be 3x positive 3y, 3x positive 3y positive 4 is equal to x positive c. I think this is the right place to stop for the solution. Maybe if you want you can simplify it, because there's an x here, you can simplify this, but I think this is fine. Thank you students, enjoy your day and make sure to practice these questions. The most important point is that practice makes perfect. In fact, they say that without practice it isn't easy to get hold of these questions, for the fact that these questions require multiple stages of operation. So having mentioned that, students, we are producing new content every day on all areas of mathematics. We are also producing content on competitive mathematics, Math Olympiad, and mathematics for various entrance examinations. If all these things are of interest to you and you are excited, and if you would like to receive our content, please subscribe and come on board. Thank you students, and I wish you all good night.
Welcome students. Today's class we will be starting off in learning linear differential equations. Now the first and foremost thing that you will have to know is the definition. So let me write that down. Differential equation is said to be linear if the dependent variable and its differential coefficients occur only in the first degree and not, this is very important, and not multiplied together. Now what exactly does it mean? Now the meaning is, we are looking at a system in this fashion: dy over dx positive p times y is equal to q, where p comma q are the functions of x. Now when we talk about dependent variable, let me write that down, dependent variable, and there is also what is called as independent variable. Now if I were to take dy over dx, the dependent variable is y and the independent variable is x. So have that in mind. So that means what they are saying is, it's purely acceptable if you have something like this, say d squared y over dx squared positive something, say p times y is equal to some q. Now this has an order and it has a degree. Now the degree should always be 1. So this is a differential equation. Now if someone were to ask you, say, what can you say about this one? Say y times dy over dx positive p times, say, y squared is equal to q. Is this a differential equation? The answer is no. No. Why? From the definition, you cannot have y multiplied with dy over dx. Have it in mind. On the contrary, if someone were to ask you x times dy over dx positive some p times y is equal to q, is this a differential equation? Yes, because x is an independent variable. Now we are going to look into some illustrations and we will further our studies with sufficient examples. Okay, the first example is, say you got something like this, say y squared dy over dx is equal to x to the power of 3y positive x to the power of 5. The question is this a differential equation or is this a linear differential equation? Yes or no? Can we say that this is a linear differential equation? True or false? Tell me. The answer is false. This is not a linear differential equation for the given fact that you got y squared being multiplied with dy over dx. So this is false. So let me go on and give you example number 2. Say you got say x to the power of 5. Say dy over dx is equal to 2 times x to the power of 3y negative 1 5. Is this a linear differential equation? Can you say true or false? What would you say? Of course, the answer is true. I can always have x to the power of 5 multiplied with dy over dx. That isn't the issue. But I cannot have y squared multiplied with dy over dx. This is a very big issue. So have that in mind. Now, coming to example number 3. Say for example you got something like this. Say x times d squared y over dx squared negative x to the power of 3 dy over dx is equal to 5 times y positive sum 81. Is this LDE, a linear differential equation? Of course, the answer is going to be true. Okay, it doesn't matter if I have x or x cubed, but I should not have any y term. So having mentioned this, now you might be wondering what sort of linear differential equation this is. So this is linear, let me write that down, linear differential equation of order equal to 2. Just to give you some information on this particular example. Other examples are straightforward and I'm sure that you are well aware of it. So let us move on. Students, we are going to learn the standard form of linear differential equation. So what exactly is the standard form? Now have it in mind. This standard form is also called as Leibniz. Leibniz. Leibniz is one of the inventors of calculus. So this is also called as Leibniz linear equation. So that's important. Some details of these great people are very critical in understanding the subject, because people like Leibniz, Newton, Euler, Fermat, they're all great people who have dedicated their entire life in the discovery of the concepts of mathematics. In fact, there are scores of people who are worthy of mention, but apparently we will learn about them as we progress in this particular journey. So Leibniz, as I mentioned to you, Leibniz and Newton, Sir Newton and Sir Leibniz, both of them are credited with the invention of calculus. Well, most of the concepts of calculus that we are seeing is from Leibniz, right? So this standard form of linear differential equation is also known as Leibniz linear equation. Now the form, it is important that we understand the form of the LDE. Now what is the form of LDE? So how does the LDE look? It is given to be as dy over dx positive p times y is equal to q. As I mentioned to you in the very beginning, where p comma q are functions, okay, are functions of x. Now the question is, how are we going to solve it? Solving is very critical, right? This is a system and we have to solve them. Solving it is very critical. Now why is it critical? Only when we solve it, we know the answer. Just as in life, every complex situation or a complex case or a complex scenario is associated with a problem, right? And just as in life, we need solutions to them, right? And the mathematics develops our mind and our ability to think to achieve such solutions. So imagine that we have a system, okay? This system is connected with certain real life problem and it has a representation in this fashion. The question comes, how are we going to solve it? Now to solve this, what we have to do is we will have to multiply. Let me just take this as 1. We will have to multiply 1 by e raised to the power of integral p dx. So this is a very important component. So we will have to multiply 1 by this. So what happens when we do that? So I get, let me write that down, dy over dx multiplied with e raised to the power of integral p dx positive. I'm going to write this as y times of e raised to the power of integral p dx times, I got a p there, so I'm writing the p like this, is equal to, now I got a q there, and then I will follow it as e raised to the power of integral p dx. So this is what we have got. Now clearly, if you were to observe this, this is nothing but UV form. So I can clearly rewrite this as d over dx of, I'm going to represent this as y times e raised to the power of integral p dx. This is equal to q times e raised to the power of integral p dx. Now let me just show you what happens with this. So I'm going to use this space here. Now I'm differentiating this term, right? So if you have d of uv, what is the differentiation? U times v dash positive v times u dash, right? So this is going to be y times, you're going to differentiate e raised to the power of integral p dx. So now if you were to differentiate a quantity like this, what would happen to this quantity? This quantity would actually be as retained, because this is going to be exactly e raised to the power of integral p dx. So I just place p there. Positive, I need to now differentiate y term. So that is going to be e raised to the power of integral p dx times dy over dx. So this is exactly what we've got, right? Dy over dx times e raised to the power of integral p dx positive y times, so differential of this, so when we differentiate this, this is going to be resulting in e raised to the power of whatever quantity we've got times the quantity that is acting as a coefficient. So we got to multiply that. So this is what we have got now. So having got this, what I'm going to do, I'm going to cross multiply. If I were to cross multiply, this is going to be d of y times e raised to the power of integral p dx is equal to q times e raised to the power of integral p times dx times dx. So this is what we've got. Now I want to get rid of this d. So what I wish to do, I wish to integrate both sides. So this integral and the d will get neutralized. So thereby giving me y times e raised to the power of integral p dx is equal to integral q times e raised to the power of integral p dx times dx. Since I am integrating, there will be a presence of an arbitrary constant. So the solution of a linear differential equation is this. And understanding this is of much importance. So we will move on to do other related questions. Students, we are expected to solve this linear differential equation, and foremost thing is we would love to convert this into standard linear differential equation. So what is that? Which is nothing but dy over dx positive p times y is equal to q, where p comma q are functions of x, right? So let us see if we can get the problem in this fashion. So first what I would do is, if I were to take this as 1, therefore I can rewrite 1 as x positive 1 times dy over dx negative y is equal to e raised to the power of 3x times x positive 1 raised to the power of 2. I wanted to have q, this is my q term, because q is a function of x. And now I need to have p times y, and there shouldn't be any coefficient with dy over dx. So what I will do is divide by x positive 1 throughout. So if I were to do this, I would get dy over dx negative y times 1 over x positive 1 is equal to e raised to the power of 3x. Now x positive 1, raised to the power of 2 divided by x positive 1. That is going to give me x positive 1, right? So now this is exactly in this standard form. So where p is equal to negative 1 over x positive 1 and my q is e raised to the power of 3x times x positive 1. So this is fair enough. Now the solution, excuse me, the solution for the LDE. What is the solution for the LDE? We achieved a solution as y times e raised to the power of, we have already deduced the solution. Integral p dx is equal to integral q times e raised to the power of integral p dx, of course, times dx positive c. Now this is the integrating factor, right? So we call this quantity as integrating factor. So we write it as integrating factor, and we abbreviate it as IF. Okay. So we will have to obtain the integrating factor. So how are we going to obtain the integrating factor? This is nothing but e raised to the power of integral p dx. This is the integrating factor, which is nothing but e raised to the power of integral. My p is negative 1 over x positive 1. So I'm going to write it as dx over x positive 1. So this is nothing but e raised to the power of integral of this. What would you get if you were to integrate this particular quantity? This is going to give me ln of x positive 1 with a negative sign. I know that there is a law. So what is the logarithmic law? Let me just write that down. A times ln b is equal to ln of b over a. This is the property I will be using. So I can move this over here. So this is going to be e raised to the power of ln of x positive 1 raised to the power of negative 1. So let it be like this. Now you can see that you got e here and you have a natural logarithm here. So both of them will get neutralized, giving me x positive 1 raised to the power of negative 1. I can rewrite that as 1 over x positive 1. This is my integrating factor. So fair enough. So now we will have to calculate. So let us consider this quantity. So we will have to integrate this. Consider integral q times e raised to the power of integral p dx, which is nothing but integral. My q, I have already taken my q as e raised to the power of 3x times x positive 1 times e raised to the power of integral p dx. What is that? E raised to the power of integral p dx is nothing but 1 over x positive 1. Of course there is a dx here. We should always have that. Without that the integration cannot be performed. So clearly what happens here, x positive 1 can be cancelled, giving me integral e raised to the power of 3x times dx, which is nothing but e raised to the power of 3x, coefficient of x is 3, and we have to place the arbitrary constant c. So now the solution. So we call it as general solution, or depends on whatever you wanted to specify. Either you can say general solution or solution. So what is the solution? We know that integral this is on the right hand side, integral q times e raised to the power of integral p dx positive c. On the left hand side it's going to be y times e raised to the power of integral p dx. So this is the solution. So according to this, now y times e raised to the power of integral p dx, e raised to the power of integral p dx is going to be y over, this is actually 1 over x positive 1, is equal to this quantity. We have already evaluated this quantity to be as e raised to the power of 3x divided by 3 positive arbitrary constant c. So this is the solution that we have got. If you want to have only y here, you can always write this as y is equal to e raised to the power of 3x divided by 3 positive c times, you can cross multiply, so it's going to be x positive 1. So this can be taken to be the solution. If you're happy about this, there is no harm even to stop at this particular point. If you are given an MCQ And if you can only spot this to be the choice, then you will have to bring it all the way to here. So we'll move on to the next question, students. Students, we are given a beautiful question. Solve is a linear differential equation. And the question is e raised to the power of negative 2 times root of x divided by root of x negative y times root of x times dx over dy is equal to 1. Now, this is solvable owing to the fact that we got dx over dy. And that is an added advantage. So what I wish to do is I would like to move dx over dy down. So this would mean I now have e raised to the power of negative 2 times root of x divided by root of x negative y times root of x is equal to 1 over dx over dy. Now I flip this dx over dy. So what do I get? I get e raised to the power of negative 2 times root of x divided by root of x negative y divided by root of x is equal to dy over dx. So this is what I've got now. Now I need to bring it in the required form. The required standard linear differential equation form is, so what is the required linear differential equation form? Dy over dx positive p times y is equal to q, where p comma q are functions of x, right? So I need to get that. So dy over dx is going to be there. I'm going to push y over root x to the other side. So that would mean I got positive y over root of x. And I'm going to retain e raised to the power of negative 2 times root of x divided by root of x. Now this is clearly in the standard form. So I can specify here where my p is 1 over root of x. So that's my p, and my q is e raised to the power of negative 2 times root of x divided by root of x. Now we need to get the integrating factor. So what is the integrating factor? Which is nothing but e raised to the power of integral p dx. This is what is the integrating factor. From here I can say this is nothing but e raised to the power of integral. My p is 1 over root of x times dx. Right? This is what I've got. So what I wish to do is I will first consider integral dx divided by root of x. So this integration, this is rewritten as dx divided by x raised to the power of 1 over 2, which is nothing but x raised to the power of negative 1 over 2 times dx, which is nothing but x raised to the power of negative 1 over 2 positive 1 divided by negative 1 over 2 positive 1, which is x raised to the power of positive 1 over 2 divided by 1 over 2, which is nothing but 2 times root of x. Of course, there is a positive constant c. I don't have to specify it right now. So hence the integrating factor is e raised to the power of integral p dx is equal to, in place of integral p dx, I will have to specify 2 times root of x. Probably I will just say consider integral p dx. Okay, so I've got this integrating factor. So now I will have to consider integral q times e raised to the power of integral p dx times dx. Now what is my q? My q is e raised to the power of negative 2 times root of x divided by root of x. What is my e raised to the power of integral p dx? This is going to be e raised to the power of 2 times root of x times dx. Now, do you see what I see? You have e raised to the power of negative 2 times root of x, and you got e raised to the power of positive 2 times root of x. So we got a favorable outcome. So I can simply cancel these two. If I were to cancel these two, I would get dx divided by root of x. Now this is going to be, this is actually x raised to the power of half, right? So this is going to be x raised to the power of negative half times dx. If I were to integrate this, I would get the same thing, 2 times root of x. This is what I'm going to get. So I can directly substitute that value, 2 times root of x. So now the solution part comes. So therefore, the solution. So all of these things are our working. So the solution is y times e raised to the power of integral p dx. That's a solution, right? So let me show you the solution, general solution that we are looking for. This is the general solution that we are looking for. So I will just substitute it, probably because of the lack of space. So y times e raised to the power of integral p dx, where is our integrating factor, is going to be y times e raised to the power of 2 times root of x, is equal to this quantity. This quantity is nothing but 2 times root of x. So just substitute that 2 times root of x. Finally, we will have to place the arbitrary constant. That is very much important. So without the arbitrary constant, the solution is not correct. Of course, there may be people who might argue, oh, it's okay, we can just simply drop this. But no, we cannot drop it. Arbitrary constants are very, very important. So we need to place it. Okay, so this is the solution for this particular beautiful question. So we will move on to the next question. Students, we are given a question, 3 times x of 1 negative x squared times y squared times dy over dx, positive 2 times x squared negative 1 times y raised to the power of 3 is equal to ax cubed. Now in this original fashion, if someone were to ask you, is this LDE, a linear differential equation? Obviously your answer would be no. Why? Because we got y squared as a product multiple with the differential coefficient, right? So this is the exact definition that we started off with. Now we should not lose heart. In other words, we shouldn't outrightly condemn this system and ignore it and move on. We shouldn't do that. So what we have to do here is to try some certain principles and manipulation in changing this. So that's exactly what we're going to do. So what I will do is I will say, let say y cube be equal to some z. I'm going to take this. Next, I'm going to be differentiating this, okay, with respect to x. So this is going to be 3 times y squared times dy over dx is equal to dz over dx. So this is what I've got. So now, wherever I have 3 times y squared dy over dx, I can substitute dz over dx. So if I were to take this as 1, I can rewrite 1 to be as, foremost, let me just bring it in this fashion. So this is x times 1 negative x squared times 3 times y squared times dy over dx positive 2 times x squared negative 1 times y cubed is equal to a times x cubed. Now, as I mentioned to you, you got 3 times y squared dy over dx. So I can substitute. So this is going to be x times 1 negative x squared. This entire thing which you see here can be substituted with dz over dx positive. This is going to be 2x squared negative 1. Now y cube, I am taking it as z, so this is going to be a times x cubed. Now what I wish to do, I would want to get rid of this entire coefficient. So what I will do is I will be doing, in other words, I will be dividing throughout by x times 1 negative x squared. So when I perform the division, I would get dz over dx positive 2 times x squared negative 1 times z divided by x negative 1 negative x squared is equal to a times x cubed divided by x times 1 negative x squared. This is what I've got. So now the question comes here is the integrating factor. So this is clearly of the form. This is of the form dy over dx positive p times y is equal to q, right? Where p and q are functions of x. So clearly I can see that, so if I were to take this as 2, so I can state that from 2, my p is 2 times x squared negative 1 divided by x times 1 negative x squared. So therefore the integrating factor, so what is the integrating factor? E raised to the power of integral p dx, which is equal to e raised to the power of integral 2 times x squared negative 1 divided by x times 1 negative x squared times dx. So I need to integrate this. So to have this integrated, we need to adopt some techniques of partial fraction. So we can do that. So I'm just going to take this first and I will integrate this. So what I'm going to do is I'm going to be rewriting, of course you got to have a dx there. I'm going to be rewriting this as 2x squared negative 1 times dx divided by x times 1 negative x squared. I can write it as 1 negative x times 1 positive x. Now I need to use partial fractions as I just mentioned to you. So I would just say consider 2 times x squared negative 1 divided by x times 1 negative x times 1 positive x, which can be rewritten as a over x, positive b over 1 negative x, positive c over 1 positive x. If I cross multiply, this is going to be a times of 1 negative x times 1 positive x, positive b times of x times 1 positive x, positive c times of x times 1 negative x. On the left hand side you get 2x squared negative 1. Now if I were to take x is equal to 1, this goes off, the first term goes off, x is equal to 1. If I were to take x is equal to 1, this one also goes off. So I am left with b of 1 times 1 positive 1, which is going to give me 2 times b. On the left hand side, x is equal to 1, 2 minus 1. So I would have the value of b is 1 over 2. Okay. Now next, let me use the space over here. I'm going to take x is equal to negative 1. If I were to take negative 1, this goes off. X is equal to negative 1, b goes off, a goes off, negative 1, that's going to be positive. So it's going to be 2c, but there's going to be a negative 1, so it's going to be negative 2 times c. Negative 1, this is going to be positive because of the presence of the square. So this is going to give me c is equal to negative 1 over 2. Okay, that's fine. So we got a, I would say we got b and c, we need to get a. So what I'm going to do now, I'm going to take x to be equal to 0. If I take x is equal to 0, this is down, this is down. This is going to give me 0, positive 1, and that's going to give me a times of 1, 1. So that's going to be fine. Over here, this is going to be 0, and I get minus 1. So therefore the value of a is negative 1. This is what I've got. Now what I can do is, hence, from all these partial fractions, what I can write is integral 2 times of x squared negative 1 times dx divided by x times of 1 negative x times 1 positive x is rewritten as negative 1 over x positive 1 over 2 times 1 negative x, and my c is negative, so it's going to be 1 over 2 times 1 positive x times dx, right? So this is going to be integral negative 1 times dx over x positive 1 over times dx over 1 negative x negative 1 over 2 times integral dx over 1 positive x. Now this is going to give me negative ln x positive 1 over 2 times. This is going to give me ln of 1 negative x. Of course there is a negative sign with x, so it's going to be negative 1 there, followed by negative 1 over 2 times ln of 1 positive x. Now I want to rewrite it one more time just to avoid any confusion. So negative ln x, negative 1 over 2 ln of 1 negative x, negative 1 over 2 ln of 1 positive x. Now I got a negative negative, so I'm going to take the negative sign out. So if I were to take a negative sign out, this is going to be ln of 1 positive x, I'm writing this term first, followed by positive ln of 1 negative x. So these two can be added. Why it can be added? Because ln a plus ln b is equal to ln of a times b. We know this property. So this is going to be negative ln x negative 1 over 2 times ln of 1 positive x times 1 negative x. It's going to be 1 negative x squared. So probably I can, first I want to take this half over here. So if you want to take the half, it's up to you. If you you can do that, but before you can, okay, let me just do that. So it's going to be negative ln of x. So negative is going to be ln of 1 negative x squared. Okay, 1 negative x squared raised to the power of, this half can be rewritten. This can be further rewritten as negative ln of x, negative ln of 1 negative x squared raised to the power of half. That's going to be root of 1 negative x squared. So that's what we have got. We got two negatives here. I'm going to take a negative sign out. So it's going to be ln of x positive ln of root of 1 negative x squared. Ln a plus ln b, that's going to be ln of x times root of 1 negative x squared. So I've got a quantity. What is all this about? This is all about finding the integrating factor. In fact, it is actually not even integrating factor. All I have done is to find e raised to the power of it's just integral p dx. It is not even e raised to the power of integral p dx. It is just integral p dx. Now we have achieved all this. So now we have to obtain the integral factor. So let me just write it down. So therefore, the integrating factor is e raised to the power of integral p dx, which is equal to e raised to the power of negative ln of x times root of 1 negative x squared. So this is what I've got. Now I can throw this negative sign over here, okay, to the whole of this. So that's going to be e raised to the power of ln of x times root of 1 negative x squared. This is raised to the power of negative 1. E and ln, they get neutralized. So that is going to give me x times root of 1 negative x squared raised to the power of negative 1. I can rewrite this by bringing it down. So that's going to be if is equal to 1 over x times root of 1 negative x squared. So this is what is my integrating factor. Now we have got the integrating factor, but the question now is we will have to obtain the solution. So in fact, before we can obtain the solution, we will have to find out the integration of, now consider integral of q times e raised to the power of integral p dx times dx. We have to do this, right? Of course, this is achievable, and the only thing is that we will have to get our q. So from the question, we know that the q is, we have got the q to be as ax cubed divided by x negative x cubed. This is our q. So that is exactly what I have just written here for my q. So I have to take this and substitute here. So this is going to be a times x cubed divided by x negative x cubed times my e raised to the power of integral p dx. That is achieved. So that's going to be 1 over x times root of 1 negative x squared, and this has to be multiplied by dx. So we will have to simplify and get the output. So now I'm going to take a out, it's constant. So let me retain x cubed there. I take x out, so it's going to be 1 negative x squared. I have a x here, so this is going to be root of 1 negative x squared. Of course there is a dx here. Now I can clearly take down this x with this, so that's going to give me a times integral x squared times. Now what is this? This is actually a x, and in fact I got a one more x. I can cancel this x, and this is going to give me x, so x times dx, just one x there. Okay, that's fine. Now coming back, so what is this? If this is x and this is root of x, what is this? This is x raised to the power of 1 positive 1 over 2, which is nothing but x raised to the power of 3 over 2, right? So that is exactly what we've got. So this is going to be 1 negative x squared raised to the power of 3 over 2. Now we can bring it to the numerator and we can evaluate it, or we can just evaluate it from here. So what I'm going to do, I'm going to use substitution. So I'm going to say let 1 negative x squared. Now this is okay, let me just take it as 1 negative x squared. Let 1 negative x squared be equal to some t squared. So when I differentiate, I get negative 2 times x dx is equal to 2 times dt. So clearly the 2 can be cancelled. So this is going to give me negative x times dx is equal to t times dt. So if I were to replace that, x times dx is going to be negative t times dt divided by 1 negative x squared is t squared. So it's going to be t squared raised to the power of 3 over 2. Right, 3 over 2. So what happens here? This 2 and this 2 gets cancelled. So I know I have negative a times integral t dt divided by t raised to the power of 3. So I can get rid of this t with the t cube there. So that means this is going to be equal to a times integral dt divided by t squared. So it's all rough side. So I can push this up. So that's going to be negative a times t raised to the power of negative 2 times dt. If I were to integrate that, I get negative 2 positive 1 divided by negative 2 positive 1, which is negative a times t raised to the power of negative 1 divided by negative 1, which can be made to be as positive, positive, positive. So it's going to be a over t. But my t is what? T is going to be root of this, right? So it's going to be a times root of 1 negative x squared. What is all this? This is nothing but my q times, integral of q times e raised to the power of integral p dx. So this is what we have got. So now we got to take this and substitute it here and then give the solution. So let's do that. Now it's time for us to get the solution. So what is the solution? We started with z, right? Z times e raised to the integrating factor. I'll just write it like this. Integrating factor is equal to this quantity q, right? Integral q times e raised to the power of integral p dx times dx. We have got this value. So that's going to be over here. So a over root of 1 negative x squared. Of course, we need to place the arbitrary constant. But now it's time for us to make the substitution. So let me use this space that I can see here. Now z is actually taken to be as y cubed. So I'm going to revert it back, reverse engineering. And the integrating factor is what? Integrating factor is going to be x, substitute x times root of 1 negative x squared. So that's going to be the case is equal to a over root of 1 negative x squared positive c. Now what we can do is we can cross multiply. We can cross multiply all these things. Now if I were to cross multiply all these things, what happens? This and this will get cancelled, giving me x. So let me use the space here. So I'm using the space here. So that means I get y cubed is equal to a times x, because of the fact that I got a root of 1 negative x squared and a root of 1 negative x squared. Both of them gets cancelled, leaving me with x positive c times, c has got the denominator 1. So that would mean the entire term will be present here. It's going to be x times root of 1 negative x squared. So this is our final solution for this beautiful question. Thank you, students. Students, we are given this question. 1 positive y squared times dx is equal to tan inverse of y negative x times dy. Clearly, this is not a linear differential equation that we've been exposed to. So, where is the catch? The catch is, first and foremost thing, let us try to find, or in other words, let us try to write this system in dx over dy form. Probably if we were to able to do that, then some insights might arise. So that is what we are going to do. So I am going to divide by dy. So if I were to do that, I am going to get 1 positive y squared times dx over dy is equal to tan inverse of y negative x, because if I were to divide by dy, this is going to get lost, or in other words, this is going to get neutralized. Now what I wish to do, I would like to move this x to this end, to the left hand side. So this is going to be 1 positive y squared times dx over dy positive x is equal to tan inverse of y. Now this is something similar to what we have seen, but still not yet what we really needed. Now I'm going to divide by 1 positive y squared throughout. So if I were to do it, I'm going to get dx over dy positive x times 1 over 1 positive y squared is equal to tan inverse of y divided by 1 positive y squared. Now the form that we know, the form of linear differential equation, which we called it as a standard form, is actually dy over dx positive p times y is equal to q. Now do you see anything? In this case we got an x here, and then we got a q present over here. So my p and my q are not functions of x. It's totally changed in this case. So we have to write that. We are looking at a system which is of the form, when I say I'm talking about LDE, linear differential equation, which is of the form dx over dy positive p times x is equal to q, where my p and q are functions of not x but y, right? So the integrating factor will be e raised to the power of not integral p dx but integral p dy, right? And my solution, it's not going to start with y, it's going to be starting with x. So x times e raised to the power of integral p dy is equal to integral q times e raised to the power of integral p dy times, it's not dx, it's going to be dy positive c. So this is what we are looking for, and we will have to achieve this. In getting that done, so I need a new page, so I will work the things over here. So now I need to obtain, consider integral p dy. So what is my p? My p in this case is going to be 1 over 1 positive y squared times dy. So if you were to integrate this, this is going to give me tan inverse of y. So therefore the integrating factor, which is e raised to the power of, not p dx, is going to be p dy, is going to be e raised to the power of integral p dy is going to be tan inverse of y, tan inverse of y. So this is my integrating factor. So we have got that. Now let us now consider integral q times e raised to the power of integral p dy, which is nothing but integral. My q is tan inverse of y divided by 1 positive y squared. My e raised to the power of integral p dy is going to be e raised to the power of tan inverse of y. So we will have to substitute that. So let me just substitute it like this. So it's going to be e raised to the power of tan inverse of y times dy, right? I need to give the integrating factor there. So now the question comes, how are we going to integrate? So what I wish to do is, I will just say let tan inverse of y be equal to some t, and I differentiate that, I get dy divided by 1 positive y squared is equal to dt. So this is going to be integral tan inverse of y is t, tan inverse of y is t, and dy over 1 positive y squared is going to be dt. So this is what I've got, right? So now we can use UV technique. So if I were to use UV negative VDU form, okay, I can rewrite this with this form. This is going to be t times e raised to the power of t negative integral 1 times e raised to the power of t times dt. Okay, you can try this out. This will work out in the same fashion. So now I need to make the substitution. So this is going to be, my t is tan inverse of y times e raised to the power of tan inverse of y negative integral e raised to the power of t. This is going to be e power t. Of course, positive constant c is there. So this is going to be e raised to the power of tan inverse of y. Of course, there is a tan inverse of y that has to be placed here. So followed by negative e raised to the power of tan inverse of y. Now I can take e raised to the power of tan inverse of y out. So that's going to give me tan inverse of y negative 1 positive constant c. So this is what I have got for my q. integral q times e raised to the power of integral p dy. So therefore the solution, we need to write the solution, right? So what is the solution? We started with x times e raised to the power of integral p dy is equal to q times e raised to the power of integral p dy positive constant c. Now I will write the right hand side, which is nothing but e raised to the power of tan inverse of y times tan inverse of y negative 1 positive arbitrary constant c. For the left hand side, x times e raised to the power of integral p dy. So we need to have the integrating factor, which is this, right? So substitute that. So x times e raised to the power of tan inverse of y. All I'm doing is just substituting it. Now if you want, you can simplify, but I think this is the right place to stop. Now if you want, you can divide throughout by e raised to the power of tan inverse of y. Now if you were to do that, you will get x is equal to tan inverse of y negative 1 positive. You are actually dividing, right, by e raised to the power of tan inverse of y. So this is going to give me c times e raised to the power of negative tan inverse of y. So this will be my final solution to the question. Thank you, students. I hope you enjoyed today's class, and if you like to see more content on university level mathematics, college level mathematics, engineering mathematics, competitive mathematics, math olympiad, and other math related topics, I would request you all to subscribe. Thank you and enjoy your day. Bye bye. Welcome, students. In this class we will be learning the concept of reducible linear differential equations. So the form that we are looking is dy over dx positive p times y is equal to q times y raised to the power of n. Now this is the form we will be coming across, and we will have to convert this into dy over dx positive p times y is equal to q, where p comma q are functions of x. So this is what we are trying to achieve. Now let us just solve a question. So we given a problem, say solve x times dy over dx positive y is equal to x to the power of 3 times y raised to the power of 6. So this is the question we will be attempting to solve. So foremost, what I'm going to do is I'm going to take this as 1, and I'm going to be dividing. I don't want to have a coefficient here, dividing by x throughout. So when we do that, I will get dy over dx positive y over x is equal to, when I divide by x, this is going to be x squared times y raised to the power of 6. Now this is 2. Now what I'm going to do is I'm going to be dividing by y raised to the power of 6 throughout. So when we do that, this is going to be 1 over y raised to the power of 6 dy over dx positive. This is going to give me, because the y and y raised to the power of 6, they get cancelled. So this is going to be 1 over y raised to the power of 5 times x is equal to x squared. Of course, y raised to the power of 6 goes away. Now I'm going to rewrite this as y raised to the power of negative 6 dy over dx positive y raised to the power of negative 5 divided by x is equal to x squared. So now I will take it as 3. Now I'm planning to make a substitution. So what is a substitution? This is a very important substitution. Okay, substitution. This is very important. So what I'm going to do is I'm going to say let z be equal to y raised to the power of 5. Then I'm going to be differentiating with respect to x. So when I do that, I get dz over dx is equal to negative 5 times y raised to the power of negative 6 times dy over dx. I can rewrite this, probably I can just keep it like this. So The substitution is in place of dy over dx times y raised to the power of negative 6, which is present here, I have to substitute dz over dx. But the only thing is that I want to bring this 5 over here, and then I will have dy over dx times y raised to the power of negative 6. So this is a substitution that I would be making. So I can say therefore equation 3 can be rewritten as, in place of y raised to the power of 6 dy over dx, I would be substituting negative 1 over 5 times dz over dx positive y raised to the power of 5, that's going to be z times 1 over x is equal to x squared. Now I can get rid of this negative 1 over 5, so I'm going to be multiplying by negative 5 throughout. So when I do that, this goes away, so I get dz over dx, so negative 5, so this is going to be positive of z times negative 5 over x is equal to negative 5 times x squared. Now this is typically of the form, this is of the form dy over dx positive p times y is equal to q, where p and q are functions of x. But the only thing is that in place of y, I've got a z. So the general solution for this, so the solution, so what would be the state of the solution? We have already seen the solution for the differential equations of this fashion, right? But for this, the solution is going to be z times integrating factor is equal to integral q times, of course, integrating factor times dx, right? So positive constant c. So this is going to be the solution that we are trying to achieve. So now the integrating factor, so if is equal to e raised to the power of, is actually integral p dx, right? So we will have to use this now. So clearly in place of the required y, or I would say the coefficient of p is going to be negative 5 times x times dx, which is equal to e raised to the power of negative 5 times integral dx over x, which is equal to e raised to the power of negative 5 times, this is ln x, which is equal to e raised to the power of ln of x to the power of negative 5. E and ln gets cancelled, giving me x raised to the power of negative 5. So this is my integrating factor. So now I need to consider integrating q. My q is negative 5 times x squared times e raised to the power of integral p dx. So that's going to be x raised to the power of negative 5 times dx. So this is what I've got. So if I were to push this down, this is going to be negative 5 times x squared divided by x raised to the power of 5 times dx, which is nothing but negative 5 times, this is x squared, and x squared term gets cancelled. This will give me x power 3, but I need to integrate this, so I need to push this up in the numerator. So this is how I get it. But of course I don't have to do all these things, I could have got it here itself, but just for the sake of explanation I have brought this in this fashion. If I were to integrate this, I get x to the power of negative 3 positive 1 divided by negative 3 positive 1. I can rewrite it as negative 5 times x raised to the power of negative 2 divided by negative 2. I can push this down, two negatives will become positive, so this is 5 over 2 times x squared, right? 5 over 2 times x squared, positive arbitrary constant c. So this is what I have got. Now the solution, so let me just probably I can use this space because all I need is to write the solution. So as I mentioned to you, the solution is going to be z times integrating factor is equal to integral q times e raised to the power of integral p dx times dx positive c. Now I have found this value, right? I have found this value to be as 5 over 2 x squared, so I need to substitute that. So it's going to be 5 over 2 x squared comes in the denominator, so I'm taking it to the numerator. That's going to be minus 2. Okay, positive arbitrary constancy. Now z, I have taken z to be as, let me show that to you. What is the value of z? I have taken z to be as y raised to the power of negative 5. So I substitute here y raised to the power of negative 5. My integrating factor that we have obtained is x raised to the power of negative 5. So this is the integrating factor. So I need to substitute x raised to the power of negative 5 there. So that is the solution. Probably you can, if you want, and then if you were to cross multiply, probably I can just show that to you. If you were to cross multiply, this is going to be 1 is equal to 5 over 2 times x raised to the power of negative 2 positive c times x raised to the power of 5 times y raised to the power of 5. So this would be the solution for this. So it depends on what you want and what you like. In fact, you can still simplify this. If you're interested, you can just push this inside. So if you were to push it inside, this is going to be 5 over 2 x raised to the power of 2 times x raised to the power of 5. That will be x cubed times y raised to the power of 5 positive t c times x raised to the power of 5 y raised to the power of 5. Of course, on the left hand side you got a 1. So this is a solution. Of course, having said that, what is your requirement? Based on that you can handle it. Students, we are given this question: dx over dy negative y times x is equal to y cubed x squared. Now foremost, to solve this, what I wish to do is I would like to divide by x squared throughout. Now when I do that, I get 1 over x squared dx over dy negative yx divided by x squared is equal to yx cubed x squared divided by x squared. Now clearly we can cancel the x squared and the x squared. We can cancel a x and the x here. So this can be rewritten as x raised to the power of negative 2 dx over dy negative y over x is equal to y cubed. Now what I wish to do is I would like to make a substitution. So that substitution would be as follows. So before that, I would rewrite this as x raised to the power of negative 2 dx over dy negative y times x raised to the power of negative 1 is equal to y cubed. So I'm going to say let x raised to the power of negative 1 be equal to z. I need dx over dy. So if I were to differentiate, let me write that down. Differentiating with respect to y, so it's going to be negative 1 times x raised to the power of negative 2 times the differentiation of x is going to be with reference to y, dx over dy. This is going to be dz over dy. I can rewrite this as x raised to the power of negative 2 dx over dy is equal to negative dz over dy. So this is what I have got, and I can now take this and make the substitution. So what I would do is I would just take this as 2 and rewrite this. So therefore I can rewrite 2 to be as, in place of x raised to the power of negative 2 dx over dy, I would be substituting negative dz over dy followed by negative y times, in place of x power minus 1, this is going to be z, and that's going to be y cubed. Now I can rewrite this by multiplying throughout by negative 1. So if I do that, This is going to be dz over dy positive y times z is equal to negative y raised to the power of 3. So this is what I've got. So now what I can do is I can make from here, this is a linear differential equation, so we need to find the integrating factor and then solve it. So the integrating factor for this, usually we write integrating factor e raised to the power of integral p dx, right? But this time is going to be p dy. So that is going to be e raised to the power of, now whatever we got with z, that would be the value for p. So it's going to be y times dy, which is e raised to the power of y squared over 2. So this is what we have got. And now we consider integral q times e raised to the power of integral p dy times dy. So this is going to be integral, my q is y cubed e raised to the power of y squared over 2 times dy. This is what I've got. So now we need to make a substitution. So what is a substitution? I will just say let now there is a presence of a negative sign, so I need to place that. Now before I could make a substitution, I would like to rewrite this as negative integral y squared times e raised to the power of y squared over 2 times y times dy. And then I will take a substitution as 1 over 2 times y squared is equal to some t, and this is going to be 2 times y dy over 2 is equal to dt. So clearly I can cancel 2, and therefore I get y dy is equal to dt. I can make that substitution. So this is equal to negative integral y squared is 2 times t, and then e raised to the power of y squared over 2, that's going to be t, y dy is dt. Actually the 2 alone is getting cancelled, okay, y stays there. So this is fair enough. Now I would like to use integration by parts. So I'm going to apply Liet. If I were to apply Liet, my u is t, my dv is e raised to the power of t dt, my du is dt, my v is e raised to the power of t. So using the concept uv negative integral v du. So if I were to use that, then I would have u is t, my v is e raised to the power of t, negative my v is e raised to the power of t, my du is dt. So if I were to integrate this, this is negative t times e raised to the power of t, positive integral of e power t is e power t, but my t, I can make the substitution back. My t is y squared over 2, so this is going to be y squared over 2 times e raised to the power of y squared over 2 positive e raised to the power of y squared over 2. So all these things are nothing but integral q times e raised to the power of integral p dy times dy. So this is what we have got. Okay, so now solution. So maybe probably I can use this base over here. So therefore the solution, so when you're writing the solution, it should be z times e raised to the power of integral p dy is equal to integral q times e raised to the power of integral p dy times dy, positive arbitrary constant c. So this is z times e raised to the power of integral p dy. This is what we have got, e raised to the power of y squared. So we can substitute e raised to the power of y squared over 2 is equal to, for this we have already got this, so it's going to be negative y squared over 2 times e raised to the power of y squared over 2 positive e raised to the power of y squared over 2 positive arbitrary constant c. Now we need to take into account the presence of a 2. Probably we missed that 2 there. So if I were to place that 2 inside, so this is negative 2. If I were to place that 2, so that would mean this 2 would get removed. So probably I will place one step. So this is equal to negative y squared e raised to the power of y squared over 2 positive 2 times e raised to the power of y squared over 2. So we will have to multiply this entire thing by 2. So this is have to be rewritten. So let me just get rid of this, and I need to substitute this. So this is z raised to the power of e raised to the power of y squared over 2 is equal to, I can take e raised to the power of y squared over 2 out, and if I were to do that, this is going to be 2 negative y squared positive arbitrary constant c. But we need to make some substitution for z, since z is equal to x raised to the power of negative 1. I need to substitute that. So it's going to be x raised to the power of negative 1 e raised to the power of y squared over 2 is equal to e raised to the power of y squared over 2 times 2 negative y squared positive arbitrary constant c. So based on the requirement, you can stop here, or if you wanted to go further, you can go further by getting rid of this. So if you were to divide by this quantity e raised to the power of y squared over 2, this will get cancelled, but the term will appear over here, right? So you can do that. So you can just say 1 over x is equal to, these two terms gets cancelled, so this is going to be 2 negative y squared positive, you are dividing, so it's going to be c times e raised to the power of negative y squared over 2. So I think this is the right place for us to stop. Students, we are given this question: solve dy over dx positive x times sine 2y is equal to x cubed cos squared y. Now I would like to have the right hand side and component over here to be a function of x alone. So to achieve that, I would have to divide by cos squared y both sides. So if I do that, this is going to be 1 over cos squared y dy over dx positive x times sine 2y divided by cos squared y is equal to x cubed times cos squared y divided by cos squared y. So clearly I can cancel this. Now 1 over cos squared y is secant squared y. So if I were to take this as 2, therefore I can rewrite 2 as secant squared y dy over dx positive sine 2y. Now what is sine 2y? Sine 2a is 2 times sine a cos a, right? We know this formula. So this is 2 times sine y times cos y divided by cos squared y is equal to x cubed. Now I can cancel and rewrite this as secant squared y dy over dx positive 2 times x sine y divided by cos y is equal to x cubed. Now this is rewritten as secant squared y dy over dx positive 2 times x times tan y is equal to x cubed. So this is what we have got. Now in this case, the quantity that we will have to consider is 2 times tan y. So that is important. So foremost, what I would do is I will just make the following substitution. Let z be equal to tan y, and differentiating with respect to x, we get, so what do we get? Differentiation
This is dz over dx is equal to differential of tan y is secant squared y times dy over dx. So if I were to take this as 3, therefore I can rewrite 3 to be as dz over dx positive tan y, so it's going to be 2 times xz is equal to x to the power of 3. So this is what I've got. Now we will have to get the integrating factor. So therefore integrating factor is e raised to the power of integral p dx, which is e raised to the power of integral 2 times x dx, which is e raised to the power of 2 times x squared over 2. 2 gets cancelled, giving you e raised to the power of x squared. So this is what we have got as our integrating factor. Now we will consider integral q times e raised to the power of integral p dx times dx, which is integral, my q is x to the power of 3, so you can place that. My e is in fact integrating factor is e raised to the power of x squared times dx. So this is what I've got. So now we will have to use some techniques to obtain the solution. So we can do that. Now to integrate this, what I wish to do is I'm going to rewrite this as integral x squared times e raised to the power of x squared times x into dx, because x squared times x will give me x cubed. Now with regard to the substitution, I'm going to say let x squared be equal to t. This is the substitution that I'm going to use. Now with this substitution you get 2x dx is equal to dt. So this is going to be in place of e raised to the power of x squared is going to be t, in place of x dx. So this is going to be x dx is equal to dt over 2. So dt over 2 I can substitute, but there is x squared here. Now I can substitute that. So this is what we are going to have, e raised to the power of t times dt. So I take u to be as t and dv is e raised to the power of t dt. From here I get du is dt. From here I get v is e raised to the power of t. This is integration by parts. So this is equal to 1 over 2 times uv negative integral v du. So this is 1 over 2 times my u is t, my v is e power t, my v is e raised to the power of t times du is dt. This is what I've got. This is 1 over 2 times t e raised to the power of t negative e raised to the power of t, which can be rewritten as e raised to the power of t minus 1. Of course the 2 is over there. But my t is x squared, so this is going to be e raised to the power of x squared over 2 times x squared negative 1. This is my integral q times e raised to the power of integral p dx times dx. This is what I have got. Okay, therefore the solution, let me use this space here. So therefore the solution, you have to understand this is the Leibniz linear equation in Z. So the solution is going to be Z times e raised to the power of integral p dx is equal to integral q times e raised to the power of integral p dx times dx positive C. My Z is taken to be as tan y. So I'm going to say tan y e raised to the power of integral p dx. So that is going to be over here, e raised to the power of x squared. So I can substitute e raised to the power of x squared is equal to this entire quantity is this. So it's going to be e raised to the power of x squared over 2 times x squared negative 1 positive c. So this is what I have got. Now you can either stop here or you can push forward. Right, push forward in the sense you can get rid of this. You can say this is tan y is equal to x squared negative 1 positive. If this comes, it's going to be c times e raised to the power of negative x squared. So this is a good place to stop for this question, students. We'll move on to the next one.
Students, we are given this question: dz over dx positive z over x times log z is equal to z over x times log z raised to the power of 2. So foremost, to start off, what we will do is divide by z both sides. So if I were to do this, this is going to give me 1 over z times dz over dx positive 1 over x times log z is equal to log z raised to the power of 2 times 1 over x. So this is what I've got. Now I need to bring this into the Leibniz linear differential equation type of form. So for that, I'm going to say let log of z be equal to t. So if I were to differentiate this with respect to x, we get, so this is going to be 1 over z times dz over dx is equal to dt over dx. This is what I've got. Now what I will do is I will have to substitute in place of 1 over z dz over dx as dt over dx. So this is the substitution that will be going in. dt over dx positive 1 over x times t is equal to 1 over x times t squared. Now what I will do is I will divide both sides by t squared. So this is give me 1 over t squared times dt over dx positive 1 over x times 1 over t is equal to 1 over x. So this is what we have achieved. Now what I'm going to do is I'm going to make another substitution. Why I'm going to make another substitution? Because this is a Bernoulli equation. Okay, so this being the Bernoulli equation, I would have to, in fact it gives me the privilege of making this substitution, which is 1 over t is equal to some v. Now if I were to differentiate this, this is going to give me negative 1 over t squared times dt over dx is equal to dv over dx. So if I were to take this as 2, therefore I can rewrite 2 as, the negative sign is not there, so we will have to push the negative sign here. So that would mean I get now dv over dx followed by positive, this is going to be v over x, right, because 1 over t is equal to v, which is equal to 1 over x. Now we can get rid of the negative signs by multiplying by negative 1 throughout. So if I do that, I get dv over dx negative v over x is equal to negative 1 over x. So this is what I've got. So now we will have to obtain the integrating factor. Now clearly you can see this is a function of x, this is a function of x. So the integrating factor is e raised to the power of integral p dx, which is equal to e raised to the power of integral negative 1 over x. So I can write it like this, which is e raised to the power of negative ln x, which is nothing but e raised to the power of ln of x power negative 1, which is going to be 1 over x. So this is my if. Probably I can box this. So having obtained the if, I need to obtain the q. Okay, therefore my integral q times e raised to the power of integral p dx is equal to integral, this is going to be negative 1 over x times 1 over x times dx, which is negative integral dx over x squared, which is integral x to the power of negative 2 times dx, which is, I can write this as x power negative 2 positive 1 divided by negative 2 positive 1, which is negative x power negative 1 divided by negative 1, which is negative 1 over x. Apparently there are two negatives here, so this will become positive, right?
So this positive 1 over x, so I can write that. Now the final solution, okay, we have to start with the final solution as v times e raised to the power of integral p dx is equal to integral q times e raised to the power of integral p dx times dx positive c, which is v times e raised to the power of integral p dx is going to be 1 over x. So substitute that. That is equal to, this entire quantity has been obtained to be as 1 over x positive arbitrary constant c. Now you can rearrange it and then you can simplify this. So from here, if I were to cross multiply, I get v is equal to 1 positive c times x. This is what I've got. But my v is 1 over t, right? So if I were to take this as 4, so this would mean 4 can be rewritten as 1 over t is equal to 1 plus c times x. So from here I get 1 is equal to t positive c times t times x, but my t is log z. So if I were to take this as 5, then I can rewrite 5 to be as, probably I can use the space here, 1 is equal to log z positive c times log z. Of course there is a x there, probably I can place the x somewhere over here and place the constant c there. And this is a good place to stop. If you are not inclined to have the x, we can move this, in fact if you are not interested to have this log x here, we can get rid of this log x, because it is with the constant term, we can get rid of it. So the best way to get rid of it is to divide both sides by log x. If I were to divide both sides by, in fact log z, not log x, log z, then this would give me log z raised to the power of negative 1 is equal to 1 positive c times x. So this is a good place to stop, and that will be the solution to our question.
Welcome students, in this class we will be learning about exact differential equations. Now when exactly a differential equation is called to be an exact differential equation? So that is the very important understanding we should first acquire. Now having mentioned this, imagine that you are given a differential equation of this form, say m dx positive n dy is equal to 0. This is a differential equation. Now this differential equation will be an exact differential equation if and only if the following occurs. What is that? If you can find dou m over dou y and dou n over dou x, and more so if dou m over dou y is equal to dou n over dou x. So this is the required condition for any differential equation to be an exact differential equation. This is all you need to know. So this is the check that you will have to perform. That's it. Now having mentioned that, let me just give you some illustration. Now before we could start an illustration, it is imperative to know the form of the solution of exact differential equations. How exactly the solution is obtained. Now the first thing you need to do is, obviously you need to check. Okay, you need to check if dou m over dou y is equal to dou n over dou x. So this check has to be completed. Now after you have finished this check, you will have to find integral m dx. Now I'm going to show you how this is done. so don't worry. So number 3 is you will have to obtain integral of n negative dou over dou I of integral of m dx times dy. So you will have to get this value. Now finally, the solution is going to be of the form integral m dx positive integral n negative dou over dou I of integral m dx times dy is equal to some constant c. This is going to be the form of the solution. Of course, the best way is to understand the concept by means of an example. That is exactly what we are going to do now. Now we've been given a question: solve x squared negative 2 times xy negative y squared times dx negative of x positive y raised to the power of 2 times dy is equal to 0. This is the differential equation. Now what I wish to do is I would like to rewrite, say, given one in the form of m dx plus n dy is equal to 0. So let's do that. So this is going to be x squared negative 2 times xy negative y squared times dx. I want to place a positive sign of, I want to take the negative sign inside and write this as x positive y raised to the power of 2 times dy is equal to 0. This is fair enough. Now after we have got this clearly from 2, we observe that. So what do we observe? In place of m, I got x squared negative 2 times xy negative y squared, and in the place of n I got negative of x positive y raised to the power of 2. Now according to definition, what should we do? We need to find dou m over dou y and dou n over dou x. So that is what we are going to do. Differentiating with reference to y, this is constant and this is going to give me 0. So minus 2 times x, differential of y is 1, followed by negative 2 times y. Now n, I need to find dou n over dou x, which is nothing but negative 2 times of x positive y raised to the power of 2 negative 1 times differentiation of x is 1, differentiation of y is 0. So this is going to be rewritten as negative 2 of x positive y. 2 negative 1 is 1. So this is negative 2x, negative 2y. So what have you got here? So clearly you see that this is dou m over dou y, this is dou n over dou x. So we find that dou m over dou y is equal to dou n over dou x. So what is the meaning of this? This means one is an exact differential equation. So that is the meaning. This is an exact differential equation. And the solution will be of the form what? The solution will be of the form integral m dx positive n negative dou over dou y of integral m dx times dy is equal to c. So this is the solution that we will be looking at. So let's do that. So as I mentioned to you, foremost what we will do is we will say consider integral m times. We will have to find this dx, okay, which is equal to integral. Now my m is x squared negative 2 times xy negative y squared. I need to take it with reference to dx. So if I were to integrate this is going to be x squared times dx negative 2 times y is treated as a constant. So this is how it's going to look like. And integrating x squared will give me x to the power of 3 over 3 negative 2 times y. Integral of x dx is going to be x squared over 2. Y squared is taken as a constant, so you will only get y squared times x. Of course, you can have some simplification if you prefer, because I can get rid of this 2 and rewrite this as x to the power of 3 over 3 negative y times x squared negative y squared times x. So of course there is an arbitrary constant c, you can place that. So now we will have to evaluate. Okay, now consider integral n negative dou over dou y of integral m dx times dy. So we need to have this. Now what I would do is, first this is equal to integral. You can go in terms of steps, right? So what I will do is I will write it like this. So foremost we will obtain this value. So what is that? Dou over dou y. Okay, so this is what we are going to evaluate, dou over dou y of m dx. So which is equal to dou over dou y of integral m dx is going to be this. So it's going to be x to the power of 3 over 3 negative y times x squared negative y squared times x, positive arbitrary constant c. You don't have to specify it here, but it's okay if you want to specify. Now you are differentiating this with reference to y partially. This is going to give me 0, this is going to give me 1, this is going to give me 2 times y times x, this is going to give me 0. So I get negative x squared negative 2 times xy for dou over dou y of integral m dx. Probably you can box this result. So I have obtained this. This is done. Now I need to consider n negative dou over dou y of integral m dx, which is equal to, my n is negative of x positive y raised to the power of 2, followed by negative of this quantity, negative x squared negative 2 times xy. So this is going to be negative of x positive y raised to the power of 2. I can take a negative sign out, so it's going to be positive. So this is going to be x squared negative positive 2 times xy. If I were to expand this, this is going to be x squared positive 2 times xy positive y squared, followed by positive x squared positive 2 times xy, which can be rewritten as negative x squared negative 2 times xy negative y squared positive x squared positive 2 times xy. Now negative x squared positive x squared negative 2 times xy positive 2 times xy gets cancelled, giving me, we will have to obtain the value for integral n negative dou over dou y of integral m dx times dy. Now clearly this is nothing but negative y raised to the power of 2 times dy. This is what we have got. If I were to integrate this, this is going to be y cubed divided by 3. Of course there's a negative sign. You don't have to place the arbitrary constants here. So probably I can just box this. Therefore we got integral n negative dou over dou y of integral m dx times dy is this. So now the solution, hence the solution is actually given to be as integral m dx positive integral of n negative dou over dou y of integral m dx times dy is equal to constant c. This value we have already got, which is nothing but x to the power of 3 over 3 negative x squared times y negative y squared times x. So this is the value that we have got for integral m dx. Followed by this is going to be negative y cubed over 3. Now since every integral has got a arbitrary constant, so we include the arbitrary constant like this and we complete the solution. So students, we are given a differential equation y of 1 positive 1 over x times cos y times dx positive x of log x negative x times sin y of dy is equal to 0. We are expected to solve. Now this is the differential equation. So I'm going to take this as 1. So let me write that down. 1 is a differential equation of the form m dx positive n dy is equal to 0, where my m is y of 1 positive x times cos y and my n is x positive log x negative x times sin y. So this is what I've got. Now I need to find my dou m divided by dou y. Okay, I need to get that done. So what I'm going to do is I have to differentiate everything with reference to y partially. So this is going to give me 1 positive 1 over x. That's the first step, right? So we can apply u over, in fact there is a positive sign here, so I need to have that explicitly stated. Okay, there's a positive sign here, so that would reduce our difficulty much more. So this differentiation of y 1 positive 1 over x is going to be this, followed by differentiation of cos y, that's going to be negative sin y. So I've got that. I can rewrite this as 1 positive 1 over x negative sin y. This is my dou m over dou y. So I will place that in a box. Now I will have to differentiate this. This is differentiation with reference to x. Differentiation of x is 1. This is going to give me 1 over x negative. I need to differentiate with reference to x here. So that would mean I get a sin y. So clearly we can see that probably I can mention this as 2 and mention this as 3. So from 2 and 3 we observe that. So what is the observation we got? We observe that dou m over dou y is equal to dou n over dou x. So this would mean 1 is an exact differential equation. Okay, so its solution is of the form integral m dx positive integral n negative dou over dou y of m dx times dy is equal to constant c. So this is the solution we are trying to achieve. So now what I will do is consider integral m dx, which is nothing but m is y of 1 positive 1 over x positive cos y. This is my m. I have to integrate, right, with reference to x. I can rewrite this. Y is a constant, so it's going to be y times of 1 positive 1 over x times dx. Y is a constant, so I can take it out like this and perform the integration like that. Now this is going to give me y integral of 1 times dx. Probably if you want, I can write it like this. 1 into dx is integral dx times dx over x. This is for y. and this is for cos y. So this is going to give me y times integral dx is x, integral dx over x will give me ln x positive cos y times x. So I can place the x here. So this is nothing but integral m dx. Now we will have to obtain dou over dou y of, so therefore dou over dou y of integral m dx is equal to dou over dou y of y times x positive y times ln x positive x times cos y. I'm just distributing the value. So differentiating with reference to y partially will give me x, differentiating with reference to y partially will give me ln x, differentiating with reference to y partially will give me negative x times sin y. So this is what we have got for dou over dou y of integral m dx. So maybe I can write that dou over dou y of integral m dx. So probably I'll put a box. Now I need to evaluate this. Okay, so now n minus dou over dou y of integral m dx. What is that? This is equal to my n. We have obtained our n to be as x positive log x negative x sin y. I'm going to write that. So this is going to be x positive log x negative x sin y. Negative, this quantity is what? Negative of x positive ln x. This is positive times negative. That's going to be negative x times sin y. This is what I've got. So this is rewritten as x positive log x negative x times sin y negative x negative ln x positive x times sin y. So clearly positive x positive ln x. I know you all might be wondering why I cancel log with ln. Now in application problems, whenever we write log, it always means ln. So please have that in mind. So that is the reason I'm able to cancel this against this, and we will move on to cancel x sin y. So this is going to be equal to 0, which we have got, and that would mean we don't have to integrate this quantity, right? So hence the solution is, so we have the solution integral m dx positive integral of n negative dou over dou y of integral m dx times dy is equal to c becomes, so this one goes off, so we just have m dx is equal to c, which would mean we will have to just take the value of m dx, which we have already obtained, and that is exactly what I'm going to be using. So this is the value which we have got, and I'm going to substitute that. So it's going to be x times y positive y times ln x positive x times cos y is equal to constant c, which is the solution to this question. Students, we are given a question. Foremost, what we will have to do is we will have to rearrange this, and then we will apply the test for exact differential. So that is exactly what I'm going to do. So let me just rewrite this right hand side as a squared over x squared positive y squared times x dy negative y dx. This can be further rewritten as a squared times x over x squared positive y squared times dy, followed by negative a squared times y times dx divided by x squared positive y squared. So on the left hand side I got x times dx positive y times dy. So what I'm going to do is I'm going to club dx together. So let me move this. So I got x times dx positive a squared y over x squared positive y squared times dx. This is one quantity. Positive y times dy negative a squared x divided by x squared positive y squared times dy is equal to 0. I'm going to take dx out, so I get x positive a squared y divided by x squared positive y squared times dx. This is going to be y negative a squared x divided by x squared positive y squared times dy is equal to 0. Now this is of the form m dx positive n dy is equal to 0. So this is a differential equation. Now we will have to test if this differential equation is an exact differential equation or not. So clearly, if I were to take this as 2, from 2 we know that, so what do we know? We know that m is equal to x positive a squared y divided by x squared positive y squared, and n is y negative a squared x divided by x squared positive y squared. So we are going to find dou m over dou y. Differentiating x, we get 0. So this is going to be, now we will have to apply u over v form. So it's going to be x squared positive y squared times a squared negative a squared y times 2 times y divided by x squared positive y squared raised to the power of 2. So this is going to be a squared times x squared positive a squared times y squared negative 2 times a squared y squared divided by x squared positive y squared raised to the power of 2. So clearly we can add these two things, and that's going to give me a squared x squared negative a squared y squared divided by x squared positive y squared raised to the power of 2. This is my dou m over dou y. Now I will obtain dou n over dou x over here. So it's going to be y negative a squared x divided by x squared positive y squared. So dou n over dou x is equal to, this is going to be 0. Now this one is u over v form, so x squared positive y squared times a squared, that's fine, negative a squared times x, differentiation of x squared will be 2x. So divided by, in fact I want to, there is a negative sign, so I have to place a parenthesis. So this is x squared positive y squared raised to the power of 2. So this is what I have got. So this is negative times x squared a squared positive y squared a squared negative 2 times x squared a squared divided by x squared positive y squared raised to the power of 2 is going to be, I can add these two together. So that would mean this is going to be y squared a squared, this is negative, so negative x squared a squared divided by the denominator. I take the negative sign inside, so I get x squared a squared negative a squared y squared divided by x squared positive y squared the whole square. This is my dou n over dou x. Now just connect these two things. See, you see that this versus this, both of them are same. So if I were to take this as, say, 3, if I were to take this as 4, so clearly from 3 and 4 we can conclude, if I were to take this as 1, I can say 1 is an exact differential equation. Okay, so now the question comes the solution. So we will have to obtain the solution for the differential equation. So that's exactly what we have to do. Now we know that the solution, so let me just write that down. We know that the solution is of the form integral m dx positive integral
of n minus dou over 2y of integral m dx times dy is equal to c.
So we all know this to be the solution of the exact differential equation. So now our main objective is to find the value of integral m dx. Now we know that m is nothing but x positive a squared y divided by x squared positive y squared. This is my m. So I can rewrite this to be as integral x times dx positive integral a squared y divided by x squared positive y squared times dx. Now this is a constant, y is a constant, so this is going to give me y squared over 2 positive a squared y, I can take it out. So this is going to be dx divided by x squared positive y squared. As I mentioned to you, y squared is a constant. So if I were to integrate this, this is going to be x squared divided by 2 positive. Of course I got a squared y, that's there. Now integral dx over x squared positive y squared, that's going to be 1 over y times tan inverse of x over y. That's a formula. So y and y can be cancelled, so that's going to give me x squared divided by 2 positive a squared times tan inverse of x over y. So what is this? This is nothing but integral m dx. Now we need to obtain this quantity, so I'm going to show you how to obtain that. Now we need to obtain the value for integral n negative dou over dou y of integral m dx times of dy. So foremost what I will do is I will consider dou over dou y of integral m dx. Now this is nothing but dou over dou y. Integral m dx, that is nothing but x squared over 2 positive a squared times tan inverse of x over y. We have got that. So if I'm going to differentiate this partially, this is dou over dou y of x squared over 2 positive a squared times dou over dou y of tan inverse of x over y. Now this is going to be 0. This is going to be 1 over 1 positive x squared times y squared times differentiation of x over y. That's going to be negative x over y squared. Simplifying this, I would get a squared of the LCM is going to be y squared. So that's going to be y squared positive x squared divided by y squared times negative x over y squared. So if I were to flip this, I would get a squared times y squared divided by x squared positive y squared times negative x over y squared. So this is what I would get. So what we can do is I can cancel this y squared. So this is going to be negative x times a squared over x squared positive y squared. So this is what I've got. So this is nothing but dou over dou y of integral m dx. So now what we have to do is we obtain the value for integral n negative dou over dou y of integral m dx times dy. So this is equal to, I know the value of n, we need to substitute the value of n there. So that is going to be y negative a squared times x squared positive y squared followed by a negative sign of this entire value is this negative x times a squared divided by x squared positive y squared. This has to be product multiplied with dy. I can rewrite this as integral y negative a squared times x divided by x squared positive y squared
positive x times a squared divided by x squared positive y squared times dy. Now clearly negative and a positive gets cancelled, giving me integral y times dy, which when I integrate I get y squared over 2. So therefore the solution, substituting the value in the final solution, in place of integral m dx, we've got x squared over 2 positive a squared times tan inverse of x over y, positive. In place of this entire quantity we can substitute y squared over 2, and that is equal to constant c. So this would be the final solution for the question. Students, we are given this question. It's a differential equation, dy over dx positive y times cos x positive sin y positive y divided by sin x positive x times cos y positive x is equal to 0. Now first what I would do is I would like to push this to the other side and write this as dy over dx is equal to negative of y times cos x positive sin y positive y divided by sin x positive x times cos y positive x. I cross multiply, so this is going to be sin x positive x times cos y positive x times dy is equal to negative of y times cos x positive sin y positive y times dx. I will bring this to the other side. When I do that, I would get y times cos x positive sin y positive y times dx positive sin x positive x times cos y positive x times dy is equal to 0. Now this is of the form m dx positive n dy, where m is equal to y times cos x plus sin y positive y, and of course my n is the other side. So first we will have to check, right? So I differentiate this with reference to y, so that's going to be, this is cos x positive cos y positive differential of y is 1, and my n is sin x positive x times cos y positive x. So I find dou n over dou x. Differential of sin x is cos x, differential of x is cos y, differential of x is 1. So if I were to take this as 2 and this as 3, I can clearly see that from 2 and 3, if I were to take this as 1, I can conclude this implies that 1 is an exact differential equation. Hence, its solution is of the form integral m dx plus integral n negative dou over dou y of integral m dx times dy is equal to constant c. So this is the solution of the exact differential equation, and we will be using this. So foremost what we will do is consider integral m dx, which is nothing but integral, my m is y times cos x positive sin y positive y times dx. So this y is taken as a constant, so I get integral of cos x dx positive sin y times dx positive y times dx. This is y times integral of cos x is sin x, of course it's positive sin x, followed by x times sin y followed by xy. So this is my integral m dx. Now having obtained integral m dx, what we can do is we can consider dou over dou y of integral m dx. So which is nothing but dou over dou y of y times sine x plus x times sine y positive xy. So partial differentiation of y sine x will give me sine x, partial differentiation of x times sine y, that is going to give me positive x times cos y. Partial differentiation of x into y would give me x. So this is my dou over dou y of integral m dx. Okay, now consider n negative dou over dou y of integral m dx times dy with the integration. So that's nothing but integral. My n is sine x positive x times cos y positive x. This is my n. This quantity is sine x positive x times cos y positive x. That has to be integrated with reference to y. So removing the parenthesis is going to give me sine x positive x times cos y positive x, negative sine x negative x times cos y negative x times dy. So apparently sine x negative x times positive x times cos y negative x times cos y positive x negative x, they all get cancelled, giving me 0. Hence the solution is, we know the solution to be of the form integral m dx positive integral n negative dou over dou y of integral m dx times dy is equal to c. This vanishes, so we only have this. We have secured this to be this, so substitute that. So it's going to be y times sine x plus x times sine y plus xy is equal to c, which is my solution.
Welcome students. In this class we will be studying about those equations which are reducible to exact differential equations. So this is the key word. So what exactly does it mean? It means if we are given a differential equation and if we are able to represent this as m dx plus n dy is equal to 0, then we would attempt to obtain this condition, right? Dou m over dou y. If this condition holds good, then we would conclude the given differential equation to be an exact differential equation. Now, the question arises, what would happen if this condition fails? Obviously, though the given equation is a differential equation, it isn't an exact differential equation. So now there is a issue. Though the equation is a differential equation, it isn't an exact differential equation. So what should we do to make that given differential equation to an exact differential equation? So that is all this study is connected with. Now foremost, what you have to do is you will have to make the following check. The check is, see if this fails. That's exactly what we are going to do. So let me just start to check if dou m over dou y is equal to dou n over dou x, right? So clearly from here I can see m is x squared y negative 2 times xy squared, and my n is, this is actually negative, right? So negative of x cubed negative 3 times x squared y. So this is my n. Now we will find out what is dou m over dou y, differentiating this entire thing partially. So this is going to give me x squared, this is going to give me 4 times x times y, and coming to n, it's going to be dou n over dou x. So I'm going to differentiate this. This is going to give me 3 times x squared, this is going to give me negative positive 6xy. So if I were to box this, so clearly what do I see? Clearly, let me give this number as 2 and 3. From 2 and 3, we observe that dou m over dou I is not equal to dou n over dou x. So this would mean if I were to take this equation to be as 1 is not an exact differential equation, right? So the question comes is, how are we going to connect, or in other words, how are we going to convert it into an exact differential equation? Now, number 2. So first is we have undergone this stage. Number 2 is we will have to check if 1 is a homogeneous equation. That means the degrees should agree. So we have given this x squared y negative 2 times xy squared times dx, and then this is followed by x cubed negative 3 times x squared y times dy is equal to 0. Just check the powers. The total degree here is 2 positive ones, 3. It's 3 here. X is 1, y is 2, so 3 here. It's 3 and it's 3. So this is 1 is clearly homogeneous, right? So once we complete this check, we will have to go and find the integrating factor. Now what is the integrating factor? It's nothing but 1 over n times x positive n times y. Now from this we know the value of m, we know the value of n, so I'm going to substitute it here. So let me find out what is mx positive ny equal to. So as I mentioned to you, I know my m, which is x squared y negative 2 times xy squared. This has to be multiplied with x positive my n is negative of x cubed negative 3 times x squared y. This has to be multiplied with y. So this would give me x into x squared is going to be x cubed y negative 2 times x squared y squared. You have a negative times positive is a negative, so it's going to be x cubed y. Negative times negative is positive, so 3 times x squared y squared. So clearly x cubed y cancel, so you have negative x squared y squared, that can be added here. So we would now have x squared y squared. What is this? This is mx positive ny. Now we are expected to find the integrating factor, so therefore the integrating factor is nothing but 1 over mx positive ny, which is nothing but 1 over x squared y squared. So we have got this. Now what should we do? We have to take this, and let me just take this as say 4. We have to take this and multiply the original given equation by this 4. That is exactly what we have to do. So that is what we are going to perform now. Okay, so this is step 4. Okay, step 4, we will multiply equation 1 with equation 4. Okay, so in other words I would say we will multiply 1 with 4. That's what we have to do. So this is going to give me x squared y negative 2 times x y squared times dx. The term is x squared y squared followed by negative sign, and x cubed negative 3 times x squared y times dy divided by x squared y squared is equal to 0. So okay, now let me simplify this. I have to rewrite that. So that is going to be x squared y. I can rewrite it like this: x squared y divided by x squared, this is x squared y squared, negative 2 times x y squared divided by x squared y squared, this is with dx, and then that's followed by negative of x cubed divided by x squared y squared, negative 3 times x squared y divided by x squared y squared. So this is going to be dy is equal to 0. So now what we would do is we will cancel the terms x squared y x squared and x squared, and a y and a y, and x and a x and a y squared and a y squared, x squared and x squared gets cancelled. This is x squared, and the y gets cancelled. So this is going to be 1 over y negative 2 over x times dx, negative, this is going to be x over y squared, negative 3 over y times dy is equal to 0. So this is what we have got. Now I can rewrite this in this form, rewriting in mdx plus ndy is equal to 0 form. So it's going to be 1 over y negative 2 over x times dx, positive negative of x over y squared negative 3 over y times dy, in fact is equal to 0. So I just want to have a plus there. In fact, I should have placed the dy outside of the parenthesis, so that way we would have this form mdx plus ndy is equal to 0, but it's okay, never mind. So from here I can state that my m is equal to 1 over y negative 2 over x, and my n is negative of x over y squared negative 3 over y. So now the question comes, we will have to find dou m over dou y. So this is going to give me negative 1 over y squared, this cancels off. Now dou n over dou x, this is going to give me negative 1 over y squared, this cancels off, right? So this implies dou m over dou y is equal to dou n over dou x, which means the equation, okay, the equation is now in exact differential equation form. Okay, so that is the understanding we have achieved here, all because of this condition being true. So having obtained this, now it's time for us to solve. So I'm going to say consider integral m dx, which is equal to integral, my m is 1 over y negative 2 over x times dx. So this can be rewritten as 1 over y is a constant, so it's going to be integral dx negative 2 times integral dx over x. Now this can be rewritten as 1 over y times x negative 2 times ln x. So this is what I've got. Now I can write this as integral m dx being equal to this, so I will box this up, and after this it's time for us to consider, okay, consider integral n negative dou over dou y of integral m dx times dy. Now this is equal to integral, my n is this quantity, right? So I need to substitute that, so it's going to be negative. In fact, if I were to take the negative sign out, I can start with the positive sign. So this is going to be 3 over y negative x over y squared, okay, followed by negative dou over dou y of this quantity. What is that? X over y minus 2 times ln x. So this entire thing has to be has to carry the differential operator dy. So probably I will just change this to a parenthesis like this, and then I will have the integral sign like this. Okay, so now if you have to differentiate, so this is equal to integral, so I'm retaining as it is 3 over y negative x over y squared. If I were to differentiate this partially, dou over dou y of x over y, so this is going to give me negative x over y squared, right? And differential of 2 times ln x, this is partially differentiation with reference to y, so this will get vanished, so all it remains is this times dy, and I need to place the parenthesis there. So if I were to rewrite this, this is going to be integral 3 over y negative x over y squared positive x over y squared times dy. Now clearly negative x over y squared positive x over y squared can be cancelled, giving me 3 times integral dy over y, which is equal to 3 times ln y. So this is what I've got for this. Now we will have to give the complete solution, right? So that's exactly what we're going to do. So hence the complete solution is going to be integral m dx positive integral of n negative dou over dou y of integral m dx times dy, right, is equal to constant c. Now this one, integral m dx, is this quantity, so x over y negative 2 times ln x followed by a positive sign and 3 times ln y is equal to constant c. So this is our final solution. Of course you can take this 2 onto the head of x and 3 onto the head of y based on your requirement. So that completes this beautiful question, students. So we will move on to the next one. Students, we are continuing our study on reducible to exact differential equation, and this particular illustration is of second form or second variation. So what exactly does this particular variation mean? So I'm going to show you what exactly it means with the following understanding. Now we are given this, given that m dx plus n dy is equal to 0, and if we can represent this as f of xy times y dx positive f of course this one is some function f1, this is some function f2 of x dy is equal to 0, then the integrating factor is going to be 1 over mx negative ny. Now it is imperative to understand that the condition has already failed here. Now provided, of course, let me write that down, provided of course dou m over dou I is not equal to dou n over dou x. Because if this condition is valid, then there is no reason for us to apply this format. Now when I say f of xy, it means function involving x and y together. So in other words, x and y should be together, they should be concatenated. Now if I say f of x is equal to, say, x to the power of 3 negative 2x squared, this is solely a function of x. If I say f of y is equal to y times sine y, this is solely a function of y. Now if I say f of x times y, then the function has to be of this form. So for every x there should be a y with it. It doesn't matter what the degree or what the order that they carry, but they should be together, right? They are couples. That's the understanding that you should have, and they should be joined together. So having mentioned this, let us move on to solve this question. So foremost, we are given, what is given? We are given that x into y squared positive 2 times x squared y cubed times dx positive x squared y negative x to the power of 3 times y squared times dy is equal to 0. This is given. Now this is of the form mdx plus ndy is equal to 0. Fair enough. This is a differential equation, but it isn't yet an exact differential equation, right? So we got to do the test. So where m is equal to x into y squared positive 2x squared y cubed and n is equal to x squared y negative x cubed y squared. Now we carry out dou m over dou y, differentiation of m partially with reference to y. This is going to give me 2 times xy and positive 6 times x squared y squared, and differentiating n with reference to x partially, this is going to be 2 times xy negative 3 times x squared y squared. Now let me box this so clearly you can see that if I were to name it as 2 and 3, clearly from 2 and 3 we see that dou m over dou y is not equal to dou n over dou x. This would mean that 1, I want to take this as 1 is not an exact differential equation. That is the meaning. So now our condition is to represent this in the form that we would be able to apply this integrating factor. So that would mean I need to make sure that there is a function involving xy. I can take a y out. There is a function involving xy, another function, and I can take a x out. Okay, so rewriting x into y squared positive 2x squared y cubed times dx positive x squared times y x to the power of 3 y squared times dy is equal to 0, we get, so what do we get? So now I'm going to take a y out, so xy positive 2 times x squared y squared, I've taken a y out, so it's y dx positive, I'm going to take a x out, so it's going to be xy negative x squared times y squared times x dy is equal to 0. So this is exactly of the form f1 x and y together with y out times dx positive f2 x and y together with x out with dy is equal to 0, right? So this would mean my integrating factor would be 1 over mx negative ny, okay, Now consider mx negative ny. So what is my m? My m is this, my n is this, so let us use that. So that's going to be x into y squared positive 2 times x squared y cubed times x negative, my n is x squared y negative x cubed y squared times y. So that is nothing but x squared y squared positive 2 times x cubed y cubed negative x squared y squared negative negative positive x cubed and y squared. So is there anything we can cancel? X squared y squared gets cancelled. Now I got a 2x cubed y cubed and x, that is x cubed. Okay, this should be y cubed, right? X cubed y squared times y cubed negative negative positive. So these two can be added together, giving me 2 times, in fact 3 times x to the power of 3 y to the power of 3. So this is my mx negative and y. So therefore the integrating factor is equal to 1 over 3 times x cubed y cubed. So if I were to take this as sum 4, we will multiply 1 by 4, right? So that would give us, so this would mean 1 can now be rewritten as x y. So I can just use the original system. So x y squared positive 2 times x squared y cubed divided by 3 times x cubed y cubed times dx positive of x squared y negative x cubed y squared divided by 3 times x cubed y cubed times dy is equal to 0. This is what I've got. So this can be rewritten as x y squared divided by 3 x cubed y cubed positive 2 times x squared y cubed 3 over x cubed y cubed times dx positive x squared y divided by 3 times x cubed y cubed negative x cubed y squared divided by 3 times x cubed y cubed times dy is equal to 0. So now what we can do is we can cancel this, cancel this entirely, cancel this, and then cancel this a bit, and cancel this, 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 cancel this. So that's what we have got now. So the question is we have to rewrite this. This is going to be 1 over 3 times, I got a x squared there and a y there, positive 2 over 3 times, I got a x there times dx positive, I got a x there and a y squared there, and then 3 there and a y there and a dy there is equal to 0. So this is what we have got. So now we need to apply our check. So let's do that. So from here I get m is equal to 1 over 3x squared y positive 2 over 3x, and my n is 1 over 3x y squared negative 1 over 3y. So this is what we've got. So now I would like to use this space that you see here to perform the check. So I would like to find out what is dou m over dou y. So differentiating this is going to give me negative 1 over 3 times y squared. This is going to be 0, right, because we want to find dou m over dou y, and dou n over dou x is equal to, this is going to give me, of course one important thing, I need to get rid of this. I need to place this x squared, so that's also is important. So because it's x squared times y, so this is what we have got. So next comes, I need to differentiate n with reference to x partially. So that is going to give me negative 1 over 3 times x squared y squared. Right, so let me box this. So if I were to take this as 5 and 6, from 5 and 6 we see that dou m over dou y is equal to dou n over dou x, which means we have effectively reduced to the exact differentiable equation type. Okay, we have effectively reduced our 1. Okay, that's a parent equation. So now we need to follow the same process for exact differential equations as we have done in the earlier cases. So now we will obtain our integral m dx, which is nothing but integral of 1 over 3 times x squared y positive 2 over 3 times x times dx. I can rewrite this as 1 over 3 times y integral dx over x squared positive 2 over 3 integral dx over x. This can be rewritten as 1 over 3y x to the power of negative 2 times dx positive 2 over 3 integral dx over x. This is 1 over 3y. This is x to the power of negative 2 positive 1 divided by negative 2 positive 1. And this is going to be 2 over 3 ln of x. I can simplify this as 1 over x minus 2 plus 1. That's going to give me a negative 1. So I can write that like that. So 2 over 3 times ln x. So this is negative 1 over 3 times xy positive 2 over 3 times ln x. So this is my integral m dx. Now therefore dou over dou I of integral m dx, we need this, right, is equal to dou over dou I of negative 1 over 3 times xy positive 2 over 3 times ln x. This one is differentiating this entire thing with reference to y partially. So if I were to do that, I would get 1 over y squared, right, with the negative sign. So that one will get neutralized with the negative sign. So this is what I will have for dou y of integral m dx. So hence we need to obtain integral n negative of dou over dou y of integral m dx times dy is equal to integral, my n is this, so I substitute 1 over 3 times x y squared negative 1 over 3 times y followed by a negative sign, and then this quantity 1 over 3 times x y squared, and then multiply with dy. I can rewrite that as integral 1 over 3 times x y squared negative 1 over 3 y negative 1 over 3 times x y squared times dy, which is equal to, I can clearly cancel the positive with the negative, giving me 1 over 3 times integral dy over y, which is negative 1 over 3 ln y. Of course I can take that to the index and then I can perform it, but for now I think I will just have it as it is, so it's okay. So this is what we have got and I'm ready to settle for that. So hence the solution. Okay, so what's the solution? Solution is integral m dx positive integral n negative dou over dou y of integral m dx times dy is equal to c. This is the solution. So My integral mdx is negative 1 over 3 times xy, positive 2 over 3 times ln x, and this is nothing but this, negative 1 over 3 times ln y is equal to c. So probably I can rewrite this as 2 over 3 times ln x, negative 1 over 3 times ln y, negative 1 over 3 times xy is equal to c. I think I'll settle for this. If you want to simplify this further, you can simplify this. Students, we are now moving on to the third form. Now, when would we encounter a form of this nature? So I'm going to give you the statement. Now we are given that mdx plus ndy is equal to 0, and if we are able to represent which one? This expression, say let me call it as a. If you are able to represent a as 1 over n times dou m over dou I negative dou n over dou x to be equal to some function of x or some constant k, then the integrating factor that we would have to take should be e raised to the power of integral f of x dx if it is a function of x, or if it is a constant, then the integrating factor should be e raised to the power of integral k times dx. So this is a very important definition that we should follow. Now all these things happens because of the fact dou m over dou I is not equal to dou n over dou x. So I have that in mind. So now what I'm going to do is I'm going to solve this question. I'm going to show you how to implement the all-important form that we have in this particular lesson. So let's do that. So to start off with, I'm going to take this as 1, and then I'm going to say from 1 we know that. So what do we know from 1? We know that m is equal to 3 times xy negative 2 times a y squared, and my n is x squared negative 2 times a y x. So we find out dou m over dou I, differentiating m with reference to y partially. So that's going to give me 3 times x. This is going to give me 4 times a y. And this is dou n over dou x. Differentiation of this is going to be 2x. Differentiation of this is going to be 2ay. Now clearly, if you were to observe this, so I'm going to take this as 2 and 3. I can state that from 2 and 3 we observe that dou m over dou I is not equal to dou n over dou x. Also 1 can be represented as, so I'm trying to achieve this representation, okay? So that is very critical. So dou n, to start off with dou m over dou I. What is dou m over dou I? Okay, so let me write it. Consider 1 over n times dou m over dou I negative dou n over dou x, which is equal to 1 over my n. My n is this, so let me write that down. X squared negative 2 times a yx, right? So dou m over dou I. So dou m over dou I is this,
3x negative 4 times ay followed by a negative sign, and dou n over dou x is this 2x negative 2ay. So we are making a check. So if this is true, so this is going to be 3x negative 2x, and that would give me a x, and negative 4ay positive 2ay would give me negative 2ay. This has to be divided by x squared negative 2ay. N is 2ax. Okay, so if I were to take a x out, so this is going to be x negative 2ay divided by x of x negative 2ay. Now clearly this can be cancelled, the numerator was the denominator, giving me 1 over x, which is nothing but a function of x. So the requirement is satisfied, right? If this is equal to a function of x, then I can use the integrating factor to be as e raised to the power of integral fx times dx. Okay, so this means the integrating factor is going to be e raised to the power of integral f of x times dx. In this case, it is e raised to the power of 1 over x. So it's going to be dx over x, which is nothing but e raised to the power of ln x, and my e and ln can be cancelled, giving me x. So all these things is for your understanding. So we got the integrating factor. Now we can solve the question. Now let me take this as 4. Now what we have to do is we have to take 4 and multiply 1. So every element has to be multiplied by the integrating factor. That's exactly what we're going to do now. So now the problem can be rewritten as 3 times x, y. This is the original problem, right? 2 times followed by 2 times a y squared times the dx. I will have to multiply by the integrating factor, followed by positive x times x squared negative 2 times a y x times dy is equal to 0. So simplifying this is going to be 3 times x squared y negative 2 times a x y squared times dx, followed by x to the power of 3 negative 2 times a y x squared times dy is equal to 0. So all these things have occurred because we have multiplied the integrating factor. Now from here I get m is equal to 3 times x squared y negative 2ax y squared, and my n is x to the power of 3 negative 2 times a y x squared. So now I need to make the check. Okay, so find dou m over dou y. Differentiating this with reference to y partially, this is going to give me 3 times x squared. Differentiation of y is 1. So this is going to give me minus 4 times axy, and differentiating n with reference to x partially, this is going to give me 3 times x squared, and this is going to give me 4 times axy. So if I were to box this and probably name it as say 6 and 7, so I can state from 6 and 7 we observe that 1 has been converted or reduced to an exact differential equation, right? So therefore we will consider integral m dx. What is that? Which is equal to integral of 3 times x squared y negative 2 times ax y squared times dx, which is nothing but, I take 3 out, y out, is going to be x squared times dx,
I take 2 out, I take a out, I take y squared out, and I got x into dx. So this is going to give me 3 times y, x to the power of 3 divided by 3, negative 2 times a times y squared, x to the power of 2 divided by 2. Of course, the 3 can be cancelled, the 2 can be cancelled, giving me x cubed y negative x squared y squared. Of course, there is a there. So this is my integral m dx. So therefore, dou over dou y of integral m dx is equal to dou over dou y of x to the power of 3y negative a times x squared times y squared. Differentiating this with reference to y would give me x cubed. This differentiation would give me 2 times x squared times and y. Of course, there is a there, so I substitute that a there. So now we need to obtain, I would say, consider integral of n negative dou over dou y of integral m dx times dy, right? So this is equal to integral, my m is this quantity which you see here, so I substitute that. There's going to be x to the power of 3 negative 2 times a y x squared followed by a negative sign. This quantity is going to be x to the power of 3 negative 2 times a x squared y has to be multiplied with dy. This can be rewritten as x to the power of 3 negative 2a y x squared negative x cubed positive 2a y x squared y times dy. Now clearly positive x cubed, negative 2a x y squared, positive 2a x y squared can be cancelled, giving me, I get a 0 there. So therefore the solution is integral m dx is equal to constant c. So my integral m dx is the value that you see here. So it's going to be x cubed y negative a times x squared times y squared is equal to c. So this is what we have got for our solution, and that's a good place for us to stop with the boxing of the solution. Students, we are heading to form 4. Now this particular form is the exact opposite of the form which we have just studied. So what is the meaning of it? The meaning is, suppose we are given m dx plus n dy is equal to 0, and we can obtain an expression of the form 1 over m times dou n over dou x negative dou m over dou y to be equal to some function of y or a constant k, then the integrating factor is going to be e raised to the power of f of y times dy if it is f of y. On the contrary, the integrating factor would be e raised to the power of integral k times dy if it is k. So the entire idea lies on this act of obtaining the expression to be some function of f of y. So this is important. So this is actually 1 over m, and if we are able to achieve this, then the entire question can be reduced to an exact differential equation, and then subsequently it can be solved. So now we are given this question. The foremost what we have to do is we will have to make the check. So as usual, I'm going to take this as 1, and then I'm going to take m to be as equal to y raised to the power of 4 positive 2 times y. This is my m, and my n is x y cubed positive 2 times y raised to the power of 4 negative 4 times x. So from here I need to find dou m divided by dou y. This is going to give me 4 times y raised to the power of 3 positive 2, and dou n over dou x is going to give me y cubed, and this will become 0, this will become negative 4. So if I were to box this and take this as 2 and 3, so from 2 and 3 we observe that. So what is the observation we got? We observe that dou m over dou y is not equal to dou n over dou x. So that would mean we will have to have a mechanism by which we can convert the given differential equation into an exact differential equation, so the solution is possible. So now what we are going to do is we are going to check for this expression, or in other words check if this expression leads to a function of y. Okay, so that's exactly what we are going to do. So now consider 1 over m of dou n over dou x negative dou m over dou y, which is equal to, my m is this, so y raised to the power of 4 positive 2 times y times dou n over dou x, that's going to be y cubed negative 4 negative dou m over dou y, that's going to be negative 4y cubed followed by negative 2. So this is exactly what I've got. So from here y cubed negative 4y cubed, that's going to be negative 3y cubed. So negative 4 negative 2 is going to give me negative 6 divided by the denominator, which is, I'm just writing it as a denominator. Okay. Now what we can do is I will use the space over here. So this is equal to, I'm going to simplify this. I'm going to take negative 3 out, and that would give me y cubed positive 2 divided by, I'm going to take from the denominator a y out. If I take a y out, I would get y to the power of 3 positive 2. So clearly these two can be cancelled, giving me negative 3 over y, which is nothing but a function of y. So I now have a function of y, which is what is required, right? This is a function of y. So once this is a function of y, I can write the integrating factor. Therefore integrating factor is e raised to the power of integral f of y, which is negative 3 over y times dy. This is going to give me e raised to the power of ln of y. Of course there's a negative 3 there. I can push this negative 3 there to the index there. That'll, and then ln and e gets cancelled. So there's going to be y raised to the power of negative 3. I can subsequently rewrite this as 1 over y cubed. Right? This is my integrating factor. So I need to multiply this. I need to use this and multiply every term in equation 1, and then make the check for dou m over dou y and dou n over dou x. That's exactly what we are going to do. We have got this. As I mentioned to you, we have multiplied the equation with the integrating factor. Now I can rewrite this as y raised to the power of 4 divided by y cubed positive 2 times y divided by y cubed times dy positive xy cubed divided by y cubed positive 2 times y raised to the power of 4 divided by y cubed negative 4 times x divided by y cubed times dy is equal to 0. This is what we have got. This can be reduced. This is going to be y positive 2 over y squared times dy, and then this can be reduced. X, I can cancel this, and this can be reduced, so 2 times y, and in fact let me just cancel this and cancel this. So I got 2y, and we can't do anything about this, so it's going to be 4x over y cubed times dy is equal to 0. So clearly my m is y positive 2 over y squared, and my n is x positive 2y negative 4x divided by y cubed. This is what I've got. Now I need to find dou m over dou y. Differential of y is 1. This is going to be y squared, right? So if I were to rewrite this as, I'm just using the space, 2 times y raised to the power of negative 2. If I were to differentiate this, I would get negative 2 times y raised to the power of negative 3, which is going to be negative 2 times y cubed, with the quantity being present in the denominator. So that's exactly what's going to happen. So I got a 2 here, and probably I can rewrite this as negative 4 over y cubed, and my dou n over dou x, this is going to give me 1, this is going to give me 4 over y cubed. So that is working out really well. So clearly, if I were to take this as say 5 or 6, I can state from 5 and 6, we see that dou m over dou y is equal to dou n over dou x. So that means 1 has been reduced to an exact differential equation. So we have achieved that. So now what we will do is we will consider integral of m dx, which is nothing but integral y positive 2 over y squared times dx. I'm going to take y out as a constant, so this is going to be integral dx positive 2 over y squared integral dx, which is going to be xy over, this is followed by 2 times x over y squared. So this is going to be my integral m dx. So therefore dou over dou y of integral m dx is equal to dou over dou y of x into y positive 2x over y squared. This is differentiation with reference to y, that gives me x. This is differentiation with reference to y again. So as I mentioned to you, this is going to be y raised to the power of minus 2. So if I were to differentiate this, I would be getting negative 2 times y raised to the power of negative 3. This is what I would be getting. Okay, so I can rewrite that as x negative 4 times x divided by y cubed. So this is my dou over dou y of integral m dx value. So therefore now consider integral n negative dou over dou y of integral m dx times dy, which is equal to integral, my n is this, right? Substitute this value. So that's going to be x positive 2y negative 4 times x divided by y cubed, followed by a negative sign and a x negative 4x over y cubed times dy. So I can rewrite this as integral x positive 2y negative 4x over y cubed negative x positive 4x over y cubed times dy. So positive x, negative 4x over y cubed, positive 4x over y cubed can be cancelled, giving me 2 times integral y times dy, which is 2 times y squared over 2. So the 2 and b cancelled, giving me y squared. So this is for this, right? So hence the solution. So what's the solution? Hence the solution is integral m dx plus n negative dou over dou y of integral m dx times dy is equal to c becomes integral mdx. What is integral mdx? Integral mdx is the value that we have got. So that's going to be x, y, positive 2 times x over y squared, positive, this whole value is found to be as y squared. So y squared is equal to constant c. Now you can either leave it like this or multiply everything by y squared. So I feel this is a good place to stop, unless or until you would want it to be simplified still further. Students, this is the final form of reducible equations to the exact differential equation. Now in this case, if we are given, say, mdx plus ndy is equal to 0, of course this is a differential equation, and for sure we know that dou m over dou y is not equal to dou n over dou x. We know this situation. And since this is a differential equation, if we are able to represent this differential equation in the following fashion, say x raised to the power of a times y raised to the power of b times, say, some p times y dx followed by some q times x dy, positive x raised to the power of some c times y raised to the power of some d times r times some y dx, positive s times some x dy is equal to 0. If we are able to achieve this, then of course I need to specify that a, b, c, d, p, q, r and s are constants. Then the integrating factor that we would be using should be of the form x raised to the power of h times y raised to the power of k. So this is the integrating factor. Of course you might be asking me, what is the value of h and what is the value of k? That is exactly what we are going to do. We are going to be finding the value of h and k. So the most important point that we will have to focus here is to convert the given differential equation into the equation that I have shown you. If you are able to achieve this, then the integrating factor that we have to use should be of the form x raised to the power of h times y raised to the power of k. So we will do a simple question to understand this. So this is the question I was talking to you about. So we will achieve the expression that we are looking for, and that is going to be x raised to the power of a times y raised to the power of b times p times y times dx, positive q times x times dy, positive x raised to the power of c, y raised to the power of d times r times y times dx, positive s times x times dy is equal to 0. As I mentioned to you, a, b, c, d, p, q, r, yes, they are all constants. So what I wish to do is, as usual, I'm going to take this as 1, and then I'm going to remove the parenthesis. I'm going to distribute it. So this is going to be y cubed times dx negative 2yx squared times dx, positive 2x y squared times dy negative x cubed times dy. Now if you were to see here, for every dx there is a dy. So I will have to suitably club the terms so that for every dx I have a dy, and let's do that. So foremost, what I will do is I will just take these two together and I will club them. Of course, on the right hand side I got equal to 0, so I will write y cubed times dx, positive 2 times x y squared times dy, this is one term, and then I will club the other term. So probably I will place a positive sign and take a whole parenthesis out, and then take a negative sign out, and then rewrite the dx term and a y term, right? So that's going to be 2 times x squared y dx term followed by a positive x cubed terms times dy. So this is equal to 0. So we are trying to get the representation that we are looking forward to. So now what I'm going to do is I'm going to take y squared out. So if I were to take a y squared out, then I would get this quantity. So it's going to be y squared out, and I get a y times dx positive 2 times x times dy, and then positive I take x squared term out. So if I take x squared term out, this is going to be 2 times y dx positive x times dy is equal to 0. So I can bring this out. I just want to keep the positive sign because I want you all to see the format, the exact pattern that I've got here. Now this is nothing but, I can rewrite this as some x to the power of 0 y squared times y dx positive 2 times x dy positive. Of course I can take this x squared out, and then I have a y raised to the power of 0, and this is going to be negative of 2 times y dx positive x times dy is equal to 0. Of course you got these zeros just to make you understand that the value of a is 0, and in this case the value of d is 0, but they are still constants, right? So if you were to compare it, we have actually achieved what we wanted, right? Now after we have done this, we will have to choose the integrating factor. Now in all cases, the integrating factor for this is going to be this. The integrating factor is going to be x to the power of h y raised to the power of k in all cases for problems of this nature, because from here we will have to get the value of h and get the value of k. So that is exactly what we have to do. Now we are not going to be using this. This has been done just for you all to understand that I am able to bring the given problem into the expression that is required of, so that I am able to take the integrating factor in this fashion, right? So we will be only using this, the given question. So let me write that down. So multiply 1, say if I were to take this as say some 3, multiply 1 with 3. I can do that. Now of course I'm able to do all those things because this is going to fail the exact differentiation check. So let me just for sake of consistency, I will just show you that. Okay, clearly we see that dou m over dou y is not equal to dou n over dou x. Okay, for the fact when m is equal to y cubed negative 2yx squared and n is equal to 2x y squared negative x cubed, dou m over dou y is equal to 3 times y squared negative 2 times x squared, and dou n over dou x is equal to 2 times y squared negative 3 times x squared. So clearly we are on the right track, right? Both of them are not the same. So let me just show you. They are failed. So actually we should have mentioned this and then we should have proceeded to checking it. But never mind, the very fact that we have a pattern here, we are checking for the pattern here, is because dou m over dou y is not equal to dou n over dou x, so it has already failed. But this is just for your understanding. Okay, so now what I'm going to do is I'm going to take 1 and multiply by the integrating factor. What is that? X raised to the power of h times y raised to the power of k. So therefore 1 can be rewritten as x raised to the power of h times y raised to the power of k times y cubed negative 2 times y x squared times dx positive x raised to the power of h y raised to the power of k 2 times x y squared negative x cubed times dy is equal to 0. So from here I can state m is equal to x raised to the power of h y raised to the power of k times y cubed negative 2 times y x squared, and n is x raised to the power of h y raised to the power of k times 2 times x y squared negative x cubed. Now I can bring this inside, remove the parenthesis, so x raised to the power of h, y raised to the power of k positive 3, and 2 times, this is going to be y raised to the power of k positive 1 and x raised to the power of h positive 2. This is, excuse me, this is my m, and my n, excuse me, my n is 2 times x raised to the power of h positive 1, y raised to the power of k positive 2, negative x raised to the power of h positive 3, y raised to the power of k. So this is what we have got for m and n. So now what we have to do is we will have to find dou m over dou y. So dou m over dou y. So this is equal to, differentiating this with reference to y partially, so x power k stands as it is, so this is going to be k positive 3 times y raised to the power of k. I reduce it by 1, so it's going to be k positive 2. So negative 2 times differentiation of this with reference to y is going to be 2 times of k positive 1 times y raised to the power of k positive 1 minus 1, that's going to be k, right, times x raised to the power of h positive 2. So now comes dou n over dou x, which is equal to 2 times of h positive 1 times x raised to the power of h times y raised to the power of k positive 2, negative h positive 3 times x raised to the power of h positive 2 times y raised to the power of k. Now we can simplify this and rewrite it just to be a little bit consistent. So in fact this is fine. Now clearly what we have to do is probably for m, just for sake of comparison, I'm going to rewrite this as k positive 3 times x raised to the power of k times y raised to the power of k positive 2, negative 2 times k positive 1 x raised to the power of h positive 2 times y raised to the power of k. And for dou n over dou x, I'm going to do the same thing. So 2 times of h positive 1 times x raised to the power of h times y raised to the power of k positive 2. One small correction, this is x raised to the power of h, okay, and everything else is fine. Right, so followed by negative h positive 3 of x raised to the power of h positive 2, y raised to the power of k. Okay, that is fine. So now clearly comparing dou m over dou y and dou n over dou x, we find that dou m over dou y is equal to dou n over dou x. This is x raised to the power of h, y raised to the power of k positive 2. This is x raised to the power of h, y raised to the power of k positive 2. This is x raised to the power of h positive 2, y raised to the power of k, x raised to the power of h positive 2, y raised to the power of k. So we can compare and see that these two are equal. You can also view it in this fashion. Now these two ought to be equal. Now for them to be equal, the coefficients should be equal, right? You can make a judgment like that. So equating, the best word to use in this sense is equating, we get. So what do we get? If I were to equate these two, I get k positive 3 is equal to 2 times of h positive 1, and then negative 2 times of k positive 1 is equal to negative h positive 3. So from your negative 2k, negative 2 is negative h negative 3. So if I were to rewrite this as h negative 2k, I get negative 3 positive 2, which would mean I get h negative 2k is equal to negative 1. So this is one system, and over here I get 2h negative k, and over here I get a 3 and I get a minus 2. So this would mean I have a 2h negative k is equal to 1. This is another system. So I'm going to place these two systems together and evaluate for values of h and k. So if I were to take this as 6 and 7, I multiply 6 by 2. So that's going to be 4h negative 2k is equal to 2, and add it with 7. That's going to be h negative 2k is equal to negative 1. I change the sign. I get negative, negative, positive, negative, positive. This is 3. This is 3h. So therefore h is equal to 1. H is equal to 1. Then if I were to substitute h is equal to 1 here, so this would imply 6 would give me negative k is equal to 1 negative 2. So this is going to be positive 2, it goes here negative 2. So this will give me negative 1. So negative k is equal to 1. So this means k is equal to 1. So I've got h is equal to 1, k is equal to 1. So therefore, let me write that down here. Therefore, the integrating factor which we started as x power h, y power k is actually xy. So what we should do, we should multiply the given system by x and y. So if I were to take this as 1 prime, so let me just place that. If I were to take this as 1 prime, so we can now have a new equation. So let's do that. So hence we have, so 1 prime is now rewritten as xy times y cubed negative 2 times y x squared times dx positive xy times 2 times xy squared negative x to the power of 3 times dy is equal to 0. Right? So you have to multiply this out, you get x y to the power of 4 negative 2 times x to the power of 3 y raised to the power of 2 times dx positive 2 times x squared y raised to the power of 3 negative x raised to the power of 4 times y times dy is equal to 0. So this is what you've got. Now clearly I take m is equal to x y raised to the power of 4 negative 2 times x cubed y squared, and my n is 2 times x squared y cubed negative x to the power of 4 times y. So I find dou m over dou y is 4 times x y cubed negative 4 times x cubed y, and dou n over dou x is 4 times x y cubed negative 4 times x cubed y. So this is working out really beautifully. You can clearly see that. So if you have to take it as say 6 or 7, probably 8 and 9. From 8 and 9, we see that dou m over dou y is equal to dou n over dou x. So this means we have successfully reduced 1 or 1 dash to exact differential equation, right? So once we have reduced it to the exact differential equation, we can go on to consider integral m dx, so which is nothing but integration of x into y raised to the power of 4 negative 2 times x cubed y squared times dx. Y is a constant, so you get integral x times dx negative 2 times y squared integral of x to the power of 3 dx. This is y power 4 x squared divided by 2 negative 2 times y squared x power 4 divided by 4. This can be rewritten as x squared y power 4 over 2 negative x to the power of 4 y squared. 2 divides 4 2 times. So this is what you have got for integral m dx. So therefore dou over dou y of integral m dx has to be found out. So differentiation of this x squared y to the power of 4 divided by 2 negative x to the power of 4 y squared divided by 2. This is equal to differentiation with reference to y partially. So 4 times y power 3 x squared divided by 2 negative 2 times y times x to the power of 4 divided by 2. 2 divides here 2 times, so this is 2 times x squared y power 3. 2 and 2 can be cancelled, followed by negative x power 4 y. This is my dou over dou y of integral m dx. Now consider integral n negative dou over dou y of integral m dx times dy, which is equal to integral. My n is this, you can use this value, so that's going to be 2 times x squared y cubed negative x to the power of 4y, followed by a negative sign and a 2 times x squared y power 3 negative x to the power of 4 times y times dy, right? So this can be rewritten as 2 times x squared y cubed negative x power 4 y negative 2 times x squared y cubed positive x to the power of 4 y times dy. Now 2 times x squared y cubed can be cancelled with negative 2 times x squared y cubed. X to the power of 4 y with a negative sign can be cancelled with x to the power of 4 y with a positive sign, giving me 0. So therefore what happens to the solution? So therefore the solution is going to be integral m dx is equal to c, because this is going to be 0, right? So what is integral m dx? Integral m dx is this quantity, so write that down. So x squared y power 4 divided by 2 negative x to the power of 4 y squared divided by 2 is equal to c. You can either reuse it or you can simply stop here depending on your requirement. I think this is the right place to stop, students. Thank you so much. Welcome students, in this class we will be learning about orthogonal trajectories. Now the meaning, or whenever you see the word orthogonal, it means there is an intersection which is taking place at 90 degrees. Now trajectories means it is actually the mathematical equivalent for the word path. So we are talking about curves which are intersecting at 90 degrees. That is the simplest way to explain this topic. Now there are two different types of questions you will encounter in orthogonal trajectories. One is to obtain the relevant equation for the family of curves in Cartesian coordinates, and the other is to obtain it in polar coordinates. So we will be handling these two questions or these two types. So having mentioned that, trajectory of the following curve, x squared positive y squared is equal to a squared. So what exactly they are asking us? Now just imagine that you have a curve which is moving like this, and this is given, right? Now what they are asking you is, they are asking you to find all the curves which are intersecting this curve. Now when they are saying a curve is moving like this, it means they are giving you a family of curves in this fashion. Okay, the family of curves might be looking like this. I'm just giving you an insinuation. Now what are you expected to do is, you are expected to find all those curves which can intersect the curve at 90 degrees. So this should be 90 degree intersection, this should be a 90 degree intersection. So wherever you can find an intersection, that intersection should take place at 90 degrees. That is the requirement for this question. So they have given us x squared positive y squared is equal to a squared. Now what is this? This is nothing but a family of circles. Okay, the family of circles, and the value of a can start from 1 and it can go on. A can be equal to 1, a can be equal to 2, a can be equal to 3 and 4 and so on. Now for every time value that a takes, there is a family that is being produced, a family of circle. In other words, a circle is being produced for every value that a takes, and the circle is centered around the origin because of the fact x squared positive y squared, right? So it is centered around the origin, but the only difference here is the radius changes. Have that in mind, the radius changes. So we have something of this fashion, and we are expected to find those families of curves that will intersect the given family of curves at 90 degrees. So that is the explanation, or the best way to understand. So how are we going to handle this question? The first point that you need to do is to differentiate. So when you differentiate, what are you trying to do? You're getting rid of the constant. So differentiating with respect to x, that is the simplest fact. Now you got one arbitrary constant, so your differentiation should be for 1. If you got two arbitrary constants, so you have to perform the differentiation twice. So differentiation of x squared will give you 2x, differentiation of y squared will give you 2 times y, dy over dx is equal to 0. From here I can say 2 times y dy over dx is equal to negative 2 times x. The 2 and the 2 can be cancelled, so I get dy over dx is equal to negative x over y. So this is what I've got. Now this is the first step. Now the second step is to obtain that equation for those families of curves. You will have to replace dy over dx by negative 1 over dy over dx. This is the replacement that you will have to do, or I should say the substitution. This is the very important substitution. This is step number 2. So if I were to take this as say 2 and this to be as 1 and this to be as 3, so using 3 in 2 we get, so dy over dx, in place of dy over dx I'm going to use negative 1 over dy over dx, which is equal to negative x over y. Of course the two negatives will become positive, so now I can flip this. When I flip it, I get dx over dy is equal to x over y, and this can be solved using variable separable. So I get a dx divided by x is equal to dy divided by y, and if I were to obtain the integration, then this is going to give me ln x and this is going to give me ln y. Of course, there is an arbitrary constant c. Now what I will do is, you can either place it as c or you can place it as ln c. It doesn't matter. So if I were to bring this ln y to the left, you are going to get ln x negative ln y is equal to ln c. Of course, this is going to be ln of x over y is equal to ln c. And excuse me, if you are not interested to further simplify, you can leave it here, but the usual way is we will proceed on to the simplification. So removing log both sides, so we get removing ln. When I say log, it means ln both sides. So what do you get when you remove that? So you get x over y is equal to c. Now what I wish to do is, I would like to rewrite this as for y. So that means I will bring that c down. X over c is equal to y. Now I got y is equal to x over c. Okay, x over c. Now this c, I can rewrite it as x times 1 over c, something of this fashion. And I can replace 1 over c by some arbitrary constant m. So I now get y is equal to mx. Now what is this? For each value, or I would say for any values that m take, we are getting a family of straight lines. You follow me? We are getting a family of straight lines for different values of m. So m can take 1, m can take 2, and m can take 3, and so on and so forth. So this is the family of curves that is required. In other words, this family of curve is actually intersecting the given curve orthogonally. That is the understanding. So if we have to visualize, how does the visualization go? So in the previous case, I have just shown you this. So this is how the family of curves that are being given. Now this is x squared positive y squared is equal to a squared. So a family of circles. Now we get y is equal to mx, or I would say, okay, that's just y is equal to mx. Now for different values of m, you get a straight line like this. Okay, you get a straight line like this. You can get a straight line like this. You can get a straight line that is moving on like this. You can get a straight line that is moving on like this. So you can find that there are many straight lines that are being obtained for various values of m. So m is equal to 1, m is equal to 2, m is equal to 3, m is equal to 4, so on and so forth. Now the most important point you will have to observe here is, for any place or any intersection that you see here, that intersection will take place at 90 degrees. So there is an intersection here, it's 90. There is an intersection, it will take place at 90. This intersection will be at 90. This intersection will be at 90. So the idea is, we are looking for two set of curves which are intersecting each other at 90 degrees. So that is the reason the name has come up as orthogonal trajectories. Now there are many applications to this particular concept in mathematics, because it is not easy to obtain an intersection of two sets of families at exactly at 90 degrees, right? So mathematically, using differential equations, you can exactly obtain those families of curves, where you can show it in accuracy. This is the family that is intersecting the given family orthogonally. So that is the first question. We will try to push on and move on to other questions. Students, we are expected to find the orthogonal trajectories of the following family of curve: x raised to the power of 2 over 3, positive y raised to the power of 2 over 3 is equal to a raised to the power of 2 over 3, where a is an arbitrary constant. So this is the family of curves that are being given. So first number, or I should say step number 1, let me write this down: x raised to the power of 2 over 3, positive y raised to the power of 2 over 3 is equal to a raised to the power of 2 over 3. This has got one arbitrary constant. So we will have to differentiate this with respect to x both sides once. So differentiation of x raised to the power of 2 over 3 is going to be 2 over 3 times x raised to the power of 2 over 3 negative 1. Positive y raised to the power of 2 over 3 is 2 over 3 times y raised to the power of 2 over 3 negative 1 times the differentiation of y is dy y over dx. A raised to the power of 2 over 3 gives me 0. I can rewrite this as 2 over 3 times y raised to the power of 2 over 3 minus 1. This is going to give me negative 1 over 3, which is, of course, there's a dy over dx. And I'm going to push this to the other side. So that's going to be negative 2 over 3 x raised to the power of negative 1 over 3. Now, I got a 2 over 3 and I 2 over 3. Both of them can be cancelled. So now what I've got dy over dx on the left hand side. Now, you got a negative sign here. Now I can actually push this x raised to the power of 1 over 3 down. So that's going to be a positive value there. Now I already get a y raised to the power of negative 1 over 3. So if I were to bring this down, this is going to be in the denominator, but it's got a negative exponent, right? So I can push it to the numerator. So that's going to be y raised to the power of 1 over 3. So this can be rewritten as negative y raised to the power of 1 over 3 divided by x raised to the power of 1 over 3. So this is what I've got for dy over dx. Now step number 2, what are we to do? We have to replace dy over dx by negative 1 over dy over dx. This is the replacement we will have to do. So what I will do is I will take this as 3. I'm going to take this as 2, probably the given system as 1. So we can simply state that using 3 into we get. So dy over dx is negative 1 over dy over dx is equal to negative y raised to the power of 1 over 3 divided by x raised to the power of 1 over 3. Now these two will become positive. I can flip this. So if I were to flip it, I would get dx over dy is equal to y raised to the power of 1 over 3 divided by x raised to the power of 1 over 3. Now I can just use variable separable. So this will go to the x side and this will go towards the right side. So if I were to rewrite this, let me use this particular space. Let me use a space on this side. So I've got x raised to the power of 1 over 3 times dx is equal to y raised to the power of 1 over 3 times dy. This is what I've got. So now, just for sake of consistency, I want to rewrite it like this. Y raised to the power of 1 over 3 times dy is equal to x raised to the power of 1 over 3 times dx, and then I'll integrate it. So if I were to integrate this, this will give me y raised to the power of 1 over 3 positive 1 divided by 1 over 3 positive 1 is equal to x raised to the power of 1 over 3 positive 1, 1 over 3 positive 1. Of course, there is a constant, so I can place that. This is going to give me x raised to the power 1 over 3 and you get a 3 there. So that means you get 4 over 3 divided by 4 over 3. And then you have a constant there. And then this is y raised to the power of 4 over 3 and you get a 4 over 3. So what you can do, you can multiply by 4 over 3 throughout. So if you were to do that, so that would mean you get y raised to the power of 4 over 3 is equal to x raised to the power of 4 over 3 positive 4 over 3 times c. Now what I can do is, of course, I can push this to the other end and I can bring this y. Now depends on what you want, right? Depends on what you want. Most of the times they will have a positive sign for the x. So I would follow the same thing just for the sake of consistency. And I will move this 4 over 3 times c to the other side. So this is going to become negative 4 over 3 times c, and this is going to be x raised to the power of 4 over 3 with y coming to this side. So it's going to be y raised to the power of 4 over 3. So this entire thing can be replaced as a constant. So I'm going to rewrite this entire thing as x raised to the power of 4 over 3 negative y raised to the power of 4 over 3 is equal to some constant, capital C. So this is the final solution. Now what is this? this is what we want. Those families of curves that are intersecting the given family of curves in an orthogonal fashion or orthogonally. So that completes the solution to this question. Students, we will move on to the next question. Students, we are given this question: find the orthogonal trajectories of the family of curves given by y squared is equal to c times x to the power of 3. Of course, c is the arbitrary constant. Start off by writing the question. The question given to us is y squared is equal to c times x to the power of 3. Now we will perform the first step, which is differentiating the given question with reference to x both sides. So if I were to do that, this is going to give me 2 times y raised to the power of 2 negative 1 times dy over dx is equal to 3 times x squared times c. I can further rewrite this as 2 times y dy over dx is equal to 3 times x squared times c. Now c is the arbitrary constant, so we will have to get rid of this c. So how are we going to get rid of this c? I'm going to take this as 1. Now from 1 we can see that. So what can we see? We have got y squared is equal to c times x to the power of 3. Therefore, c is y squared divided by x to the power of 3. So, if I were to take this as 2, I'm going to write that, using c is equal to y squared over x to the power of 3 into, we get, so what do we get? You got 2y times dy over dx is equal to 3 times x squared. In place of c, this is going to be y squared over x to the power of 3. I can rewrite this as 3 times x squared and x squared can be cancelled, giving me 3y squared divided by x. Now this is 2 times y dy over dx. So let me extract dy over dx from here. So therefore dy over dx is equal to, you get a 3y squared over x is there, you're bringing 2y down, so it's going to be 2 times y and x. I can cancel a y here, so this is going to be 3 times y over 2 times the x. So this is stage 1, right, or step 1. So I have executed step 1 here. Now step 2, what is step 2? Step 2 is take dy over dx to be as negative 1 over dy over dx. Now if I were to take this as 3, or probably, okay, 3, so therefore 3 can be rewritten as, in place of dy over dx, I get negative 1 over dy over dx is equal to 3 times y over 2 times x. So if I were to flip this, this is going to be dx over dy is equal to, I'm going to place the negative sign here, so 3 over 2 times y over x. By using variable separable technique, I can rewrite this as x times dx is equal to y times dy. Of course, we have to be concerned about the 2 and the 3. So I can place a 3 here with a negative sign and a 2 here. So I can integrate both sides. So if I were to integrate this, this is going to give me 2 times x squared over 2. If I were to integrate this, this is going to give me 3 times y squared over 2. Of course, I get a positive arbitrary constant c. Now the 2 and the 2 can be cancelled here. So if I were to cancel it, and then probably I have a quantity of this fashion. So let me just write this down. So I'm going to move this y squared to the other side. So it's going to be 3 over 2 times y squared positive x squared is equal to arbitrary constant c. Now if you don't want anything to be with y, then you will have to multiply every quantity by 2 over 3 throughout. So if you were to do that, this is going to be y squared positive 2 and 3 gets cancelled here. So this is going to be 2 over 3 times x squared is equal to 2 over 3 times c. Now this is an arbitrary constant, so we can replace it as y squared. So we can rewrite this entire system as y squared positive 2 over 3 times x squared is equal to some arbitrary constant capital C. So this is the solution. Either you can replace the solution like this, or you can start with the x term. So 2 over 3 times x squared positive y squared is equal to C. So this is a good place for us to stop. Probably I will place a line there. Students, we are given this question. Find the orthogonal trajectories of the family. The curve is y is equal to c times x and c is arbitrary constant. So let me just write that down. So this is given. So this is our first step. In the first step we write the question down. So y is equal to c times x, and then we will differentiate with respect to x both sides. So when we do that, we get dy over dx is equal to c times x is, the differentiation of x is 1. So we get dy over dx is equal to c, but we will have to get rid of the c. Now I'm going to take this as 1. So from 1, so what do we see from 1? We got y over x is equal to c, right? So using this in 2, so I'm going to take this as 2. So we get, so what do we get if we were to use this in 2? So dy over dx is equal to, in place of c, we get y over x. So this is what we have got. Now step 2, what is step 2? In step 2, we will have to replace dy over dx as negative 1 over dy over dx. So if I were to take this as 3, therefore my 3 can be rewritten as negative 1 over dy over dx is equal to y over x. So if I were to flip this, this is going to give me dx over dy. I'm going to place the negative sign on the right side, so it's going to be negative y over x. So this is what we're going to have. So using variable separable, I can move this and this in this fashion. So this is going to give me x times dx is equal to y times dy with a negative sign. So I would be integrating both sides. So if I were to integrate, this is going to give me x squared over 2. This is going to give me negative y squared over 2, positive arbitrary constant c, which can be rewritten as x squared over 2 positive y squared over 2 is equal to some c. I will have to multiply by 2 throughout. I don't want this 2 in the denominator. So this is going to give me x squared positive y squared is equal to 2 times some c. I want to replace this c by some other arbitrary constant. So I can rewrite it as x squared positive y squared is equal to some a. So this is a beautiful solution. So this is the family of curves that are functioning as an orthogonal trajectory for the given family of curves y is equal to cx. So one is a circle, the other is a straight line. So we'll move on to the next question. Since we are given this question, we are expected to find the orthogonal trajectories for the given family y is equal to c over x. Now this is a special type of hyperbola. I hope you all know this. So let us get started. So step number 1, we will just write the question y is equal to c over x. Then I will perform the differentiation with respect to x. So if I were to do this, this is going to be dy over dx is equal to differential of 1 over x. So this is going to be negative c over x squared, right? Because x is in the denominator. Now if I were to take this as 1, from 1 I can rewrite 1 as, I want to get rid of the c, so I will have to write a representation for c. So c is equal to x times y. Now using this, I'm going to rewrite 2. Therefore 2 can be rewritten as dy over dx is equal to negative x times y divided by x squared, which is equal to y over x with a negative sign. So step 1 is finished. So coming to step 2, what do? We take dy over dx to be as negative 1 over dy over dx. So this is a substitution that we will follow. Now if I were to take this as 3, so therefore I can rewrite 3 as, in place of dy over dx is going to be negative 1 over dy over dx is equal to negative y over x. So this will become positive I can flip and rewrite it as dx over dy is equal to y over x. I can move them by variable separable technique. So this is going to be x times dx is equal to y times dy. So if I were to integrate this would give me x squared over 2 is equal to y squared over 2 positive arbitrary constant c. Now what we can do is we can bring everything to the left hand side. So I'm going to place the output here. So this is x squared over 2 negative y squared over 2 is equal to constant c. So now I'm going to multiply by 2 both sides. So if I were to do this is going to give me x squared negative y squared is equal to 2 times c. Now I can replace this 2 times c as some capital arbitrary constant c. So on the left hand side I get x squared negative y squared. What is this? This is actually an hyperbola, right? We have studied this. So if you were to picturize this, how are you going to picturize this? Say this is the x-axis. Let me draw the x-axis, and this is the y-axis. So we have given y is equal to c over x. So that hyperbola will be of this fashion. Okay, this is how it will be. Okay. Now we have x squared negative y squared. So how that would be? That would start like this, like this, like this, like this. Okay. So this is a beautiful question, and I hope you are able to visualize this. So thank you, students. We'll move on to the next topic. Students, we have got this question. Let me write the question down. We are expected to form or find the family of curves that are orthogonal trajectories to the family x squared positive y squared negative 2 times c times x is equal to 0, where c is the arbitrary constant. Okay. So this is the question that has been given. So as usual, what I will do is I will start with step 1. Step 1 is I will write x squared positive y squared negative 2 times c times x is equal to 0, and then I will differentiate the terms with respect to x both sides, and that would give me 2 times x positive 2 times y dy over dx negative 2 times c is equal to 0. Now I should eliminate this arbitrary constant c. So I'm going to rewrite this as 2 times x positive 2 times y dy over dx is equal to 2 times c. I can cancel the 2 and then rewrite this as x positive y times dy over dx is equal to c. Now I'm going to take this as 1. What I would like to do is using, if I were to take this as 2, using 2 in 1. So in place of c, I'm going to substitute this in this system. So we get, so what do we get? This is x squared positive y squared negative 2 times x positive y times dy over dx is equal to 0. So this is what we have got, and I can rewrite this as x squared positive y squared negative 2 times x squared negative 2 times x times y dy over dx. This is what I've got. X squared and negative 2x squared can be added, so this is going to give me negative x squared positive y squared negative 2 times xy dy over dx. So I'm going to push this to the other side, and this is going to give me 2 times xy dy over dx. Now this is my step 1. Now for my step 2, what I wish to do is I'm going to say let dy over dx is equal to negative 1 over dy over dx. So this is the substitution that I will have to make, and probably I will have to take this as say sum 3. So I'm going to take the substitution over here, and I need to have a space. Probably I will use this space over here. So what happens, 3 will now be rewritten as negative x squared positive y squared is equal to 2 times x times y times negative 1 over dy over dx. So I can actually flip this and bring everything down. So let me just flip this. So this is going to give me 2 times xy dx over dy. There is a negative sign there, so there is a negative x squared positive y squared. So this is what I have got. So now I will have to do some manipulations so that we can solve this. So this is our objective, so we will have to solve this. So I will have to move to the next page and then I will solve that. So this is what we've got. So what I would do is I would rewrite this as negative x squared positive y squared divided by negative 2 times xy is equal to dx over dy, and from here dy over dx is going to be negative 2 times xy divided by negative x squared positive y squared. Now I want to get rid of this negative sign here, so I'm going to take a negative sign out and rewrite this as x squared followed by negative y squared. So this is what I get, and I got a negative 2 times xy in the numerator. So this is fine. Negative times positive is negative, negative times negative is positive, so this one is going to be positive. So you got dy over dx is equal to 2 times xy divided by x squared negative y squared. Now you have to solve this. Now this is homogeneous equation, and so I will just say let y be equal to vx, and then dy over dx is equal to v positive x times dv over dx. So this is the substitution we know already. So in place of dy over dx, I will substitute v positive x times dv over dx. In place of y, it's v times x divided by x squared negative v squared x squared. This is 2 times v times x squared divided by x squared of 1 negative v squared. I can cancel the x squared out. So this is going to give me 2 times v of 1 negative v squared. And I can push this v, I get a negative v there, so it's going to be x times dv over dx. Now if I were to take the LCM, I get 1 negative v squared, 2v, negative v of 1 negative v squared, which is 2 times v negative v. This is going to be a positive, negative negative positive, v times v squared. That's going to be v raised to the power of 3 divided by 1 negative v squared. So 2v and v, they can be taken summed up, so that's going to be v positive v cubed divided by 1 negative v squared. So I can take a v out, rewrite this as 1 positive v squared divided by 1 negative v squared. I have to just retain it as it is because I can't do anything as of now. So now I get dv on this side. So what I wish to do is I would be moving all the v towards the left hand side. So I would get 1 negative v squared divided by v of 1 positive v squared times dv is equal to dx divided by x. Now let me consider 1 negative v squared divided by v of 1 positive v squared. I have to use partial fraction, so I'm going to rewrite this as a over v positive bv positive c divided by 1 positive v squared. So if I were to multiply, I get a of 1 positive v squared positive bv positive c times of v. This is what I get. I need to simplify this, so I take v to be as 0. If I take v is equal to 0, then this would become 0 and I get a this is 0, and this is 0, so I get a is equal to 1. That's fine. Now the next case is I have to take v squared is equal to 1, or v squared is equal to negative 1. So that would mean this will create an issue for me. If I were to take v squared is equal to negative 1, it will become a complex quantity. So I have to avoid that. So to avoid that, I will just take v is equal to 1. Now if I take v is equal to 1, this one will become 0. Right, so I got a 0 there. So this is going to be 2 times a. I will get a b positive c. Right, so b positive c, v is equal to 1. So a is already 1 here. So minus 2 times b positive c would be one system. So I will take v is equal to, say, some 2. So if I take v is equal to 2, this one is going to be 1 negative 2 squared is 4. So this is v is equal to 2, 4 positive 1, that's 5 times a, and this is 2b positive c. Now probably what we could have done is, even if I take v squared is equal to negative, v is equal to negative 1, if I take v is equal to negative 1, there wouldn't be any harm here. So instead of complicating it with v is equal to 2, let me just show that to you. If I were to take v is equal to negative 1, so this one will still be equal to 0. Now v is equal to negative 1, so this is going to be 2 times a, and negative b positive c negative 1. That's going to be giving me a is 1, 2, positive, negative will become positive, and negative c is equal to 0. So negative 2 times b negative c. So I'm going to use here b negative c is equal to negative 2. So clearly my c can be cancelled, giving me 2 times b is equal to negative 4. So therefore b is equal to negative 2. Right? So I get a b is equal to negative 2. I already get a. So if b is equal to negative 2, if I were to take this as some 4, so I substitute negative 2, and c. So c will be equal to 0. Because negative 2 positive 2 is equal to c, therefore c is 0. So that's fine. So I'm getting c is equal to 0. So if I were to take this as some 3, okay, so therefore I can write 3 as 1 negative v squared divided by c times of 1 positive v squared is equal to, my a is 1 over v positive, my b is negative 2 times v, my c is 0, divided by 1 positive v squared. So that's fine. So it all comes down to this. So I'm going to take this as 2. So what have we achieved? So therefore I can rewrite 2 using this. So that would mean 1 over v negative 2v over 1 positive v squared. This entire thing has to be multiplied with dv is equal to dx over x. So if I were to integrate this, this is dv over v negative 2 times, probably I can just place 2 inside. I should have done that. Never mind. So this is what you've got, dx over x. Now this is ln v. Now this is, I'm going to use a substitution here. Now 1 positive v squared is equal to some t. So 2v dv is dt. So I got 2v dv and I'm trying to integrate that. So in place of 2v dv, it's going to be dt, and in place of 1 positive v squared is t. So this is going to be ln t, but this is going, t is 1 positive v squared. Right, so I have a negative sign, so this is going to be ln of 1 positive v squared is equal to ln x, plus I can put a ln c. Now this is ln A minus ln B, so it's going to be ln of V divided by 1 positive V squared. I can rewrite this as ln of x times C, so ln can be cancelled, so V is equal to 1 positive V squared is equal to x times C, but y is equal to Vx. So my V is y over x, so I substitute here. So let me use this space here. So this one is going to be y over x divided by 1 positive y over x raised to the power of 2 is x times C. This is y over x divided by 1 positive y squared over x squared is equal to x times C. Now this is y over x divided by x squared positive y squared divided by x squared. So I can actually, okay, I will flip it in the next. So this is x into C. So I'm going to use a space here. So if I were to flip it, this is y over x. I flip it, I get x squared over x squared positive y squared is equal to x times C. Now x and x gets cancelled. That is a x and a x can be cancelled. So this is going to be y over x squared positive y squared is equal to C. This is what we have got. Probably we can stop here, or if you want you can rewrite this as y is equal to C times x squared positive y squared. Right, so this is the solution. So this is the family of curves that is actually has an orthogonal trajectory with a given system. Now you have to do all of these. Now why you have to do all of this is this problem. I will just show you this. Now all happened because of two reasons. Instead of this x, you can try this out. If they have given you this x squared positive y squared negative 2 times cy is equal to 0, if they had given you this would be a cakewalk. Okay, if they had given you this, but they didn't give you that. They gave you negative 2 times c times x. So that is the reason the entire system got complicated. Alternatively, they will, if they don't want to take you on, instead of find the family of curves, they will say find the differential equation. That's all. Okay, instead of giving you the family of, asking you to find the family of curves, they will say find the differential equation. So that reduces the question's complexity in a greater manner. So thank you, students. Students were expected to obtain the orthogonal trajectories for the family of cardioid given in polar coordinates. So r is equal to a times of 1 negative cos theta. So this is a new way, or I should say another technique for us to obtain orthogonal trajectories in polar form. So having mentioned that, let me just show you with this illustration. So step number 1, r is equal to a times of 1 negative cos theta. So I'm going to find differentiating with respect to theta. So this is going to give me dr over d theta is equal to, a is a constant, differential of 1 is 0, differential of cos theta is going to be negative sin theta. There is already a negative sign, so this is going to give me a positive sin theta. So I got a times sin theta. Now a is an arbitrary constant. Now we'll have to get rid of this. So if I were to take this as 1, I'm going to take this as 2. From 1, I can rewrite this as r over 1 negative cos theta is equal to a. So I got an a there. So therefore, using this, I'm going to rewrite 2. So how do I rewrite 2? So therefore, I got dr over d theta is equal to, in place of a, it's going to be r over 1 negative cos theta times sin theta. So this is what I've got. Now I would want to represent this. In fact, I will have to change everything. So how I'm going to change it? I'm going to use trigonometric formulae. So I know that sin 2 theta is equal to 2 times sin theta cos theta. That's fine. Now if I were to take 2 theta is equal to sum t, then this is going to be sine of t is equal to 2 times, in place of theta I will have to substitute t over 2. So this is a substitution that will come into play. So this is going to be sine of t over 2 times cos of t over 2. So this is what happens actually if I have sine t, but in this case it is theta. So I'm going to rewrite this as 2r times, so that's fine. Now there is another formula. What is the formula? 1 negative cos 2 theta divided by 2 is equal to sine squared theta. So this is a formula. Now if 2 theta is equal to t, so therefore I can rewrite this as cos of t divided by 2 is equal to, so this would mean theta is equal to t over 2, right? So this is going to be sine squared of t over 2. This is provided, of course, I have things in t. So in fact I can go one more step further and rewrite this as cos of t is equal to 2 times sine squared t over 2. So this I can very well do it. So if you have 1 negative cos t, you can replace it like this. But in this case it is 1 negative cos theta. So I'm going to replace it as 2 times sine squared of theta over 2. So that's fair enough. So now I can cancel the 2 and 2. And I can cancel a sine theta over 2 and a sine theta over 2. So this is going to give me r times cos of theta over 2 divided by sine of theta over 2, which is nothing but r times cot theta over 2. On the left I got dr over d theta. So that is a good simplification. Now just as we had step 2 in Cartesian forms, there is also going to be a step 2 here. But in this case, what is that step 2? I'm going to replace dr over d theta as negative r squared divided by dr over d theta. This is the replacement I'm going to do. Have that in mind and don't forget this. So negative r squared divided by dr over d theta. So if I were to take this as 3, so therefore I can rewrite 3 as, in place of dr over d theta, it's going to be negative r squared divided by dr over d theta is equal to r times cot theta over 2. Now I can cancel a r and a r, and I can flip this. If I were to flip this, this is going to be d theta over dr with a r is equal to cot of theta over 2. Now I can push this down and perform variable separable. So this is going to be d theta over cot of theta over 2 and dr over r. Now cot theta is nothing but cos theta over sine theta. So if I were to flip this, this is going to give me sine theta over 2 divided by cos theta over 2 and times d theta is equal to dr over r. So what is this? This is nothing but my integral tan theta over 2 times d theta. Now what I wish to do, I would like to first get rid of this theta over 2. So I'm going to say theta over 2 be equal to sum t. So that means d theta is equal to 2 times dt. So if I were to make that substitution, this is for your understanding. So this is going to be integral tan of t. In place of d theta is going to be 2 times dt. So I got integral tan t. Now how am I going to integrate this? This is going to be 2 times of sine t divided by cos t. Of course I have got a formula, but I can substitute that formula. But before I could substitute, I would like to show you all how and what is exactly happening. So this is going to be cos t is equal to sum u. So negative sine t dt is equal to du. So this is going to be equal to, in place of this entire component, I'm going to say du divided by u, which is going to be ln of u. Of course there's a 2 then with a negative sign. Now my u, what is my u? My u is nothing but cos t. So it's going to be negative 2 times ln of, I substitute cos t, so this negative goes to the other end, and that would become 2 times ln of 1 over cos t, right? Now this 1 over cos t is nothing but secant t, so I can very well write this as secant t. In fact, I can write this as secant squared t, because I can push this 2 there. Now my t is theta over 2, so I have to bring it back here. So let me just do that. So this is equal to ln of secant squared of theta over 2. So this is what I got for integrating tan theta over 2. Okay, so this is going to be integral sign, that's fine. This is, let me rewrite that, this is nothing but integrating tan theta over 2 d theta. This is integrating dr over r. The integration of this is going to be negative of ln of secant squared theta over 2 is equal to integral of this dr over r is going to be ln r. I can just place a constant as ln c. Now I can actually push this negative sign to the secant squared and write that as 1 over secant squared theta over 2, which is equal to ln r plus ln c. But secant theta over 2 is nothing but 1 over cos theta over 2. So therefore secant squared theta over 2 is nothing but 1 over cos squared theta over 2. So if I were to use this, this is 1 over cos squared theta over 2. I can flip it. So I get ln of cos squared theta over 2 is equal to ln a and ln b. This is going to be r times, in fact let me write that on as ln of r times c. I can get rid of ln both sides, so that would mean I get cos squared theta over 2. Of course I get r times c, but I can push the c down over here. So if I were to push the c down, I would get 1 over c times cos squared theta over 2 is equal to r. This is what I get. Now c is an arbitrary constant. Now moving back, I would like to draw your attention to this all important formula. So what is that all important formula? Now let me just use this space. So what we have got now r is equal to 1 over c times cos squared theta over 2. Right, this is what we have got. I want to show you this formula. 1 positive cos 2 theta over 2 is cos squared theta. Now if I take 2 theta is equal to some t, then I can rewrite this as 1 positive cos t divided by 2 is equal to 2 theta is equal to t, so cos squared t over 2. Right, so there is a formula that is of this fashion. Now I've got cos squared theta over 2, so therefore what I can do is I can rewrite cos squared theta over 2 as 1 positive cos theta divided by 2. How is it possible? It's because of this formula that we know, right? Of course I have placed in here as 2 theta. Probably if you are a little bit confused, I can just use it as cos 2a. This is cos a and 2a. So 2a is equal to t. So therefore in place of a, I can substitute t over 2. So that's exactly what happens. So this is for a. So if I were to translate this to theta, this would become cos squared theta over 2 is equal to 1 positive cos theta divided by 2. So that is what we are going to do. So if I were to take this as some 5, okay, therefore I can rewrite 5 as r is equal to 1 over c times 1 positive cos theta divided by 2. So this is what I have got. Now this can be rewritten as 1 positive cos theta divided by 2c, which is r. Now let me write that down here, the final one. So what we have got here, r is equal to 1 positive cos theta divided by some 2 times c. So I want to replace this as 1 over 2c times 1 positive cos theta, which 1 over 2c can be replaced as some arbitrary constant, capital C. So this is going to be c times of 1 positive cos theta is equal to r. So this is the final solution that we are looking for. So this is going to be those families that are actually the orthogonal trajectories for the family of Cardior. So this is the final solution, and we can box this. I hope this is quite a sum, and I hope you understood this. Thank you, students. Students, we are given this question: find the orthogonal trajectories of the family of curves r raised to the power of n is equal to a raised to the power of n times cos n theta. A is the arbitrary constant there. So step number 1, I will start off like this. This is step 1. This is given. So given is r raised to the power of n is equal to a raised to the power of n times cos n theta. So what I'm going to want to do is I would like to take ln on both sides. So if you had to take ln on both sides, it's going to be ln r raised to the power of n is equal to ln a raised to the power of n times cos n theta. Now there is a formula, ln AB is equal to ln A plus ln B. Using this formula, this can be rewritten as ln A raised to the power of n positive ln cos n theta, and there is also another formula which states that ln A power n is equal to n times ln A. So this is going to be n times ln R. So fair enough. In fact, I can also rewrite this, but there is no point in writing this because this is a constant. It's going to perish. So now I'm going to be differentiating with reference to theta. So differentiating with reference to theta both sides. So what happens if we are going to do this? So this is going to be differential of ln r is going to be 1 over r times dr over d theta. Differential of this is 0. Differential of ln cos n theta is going to be 1 over cos of n theta times differential of cos is negative sine n theta, n here. So now I am going to rewrite this as n over r dr over d theta is equal to negative n times tan n theta. Of course n and n can be cancelled. So now I have 1 over r dr over d theta is equal to negative tan n theta. So this is what I have got. So now what we got to do is we will have to perform step 2. What is step 2? dr over d theta is equal to negative r squared divided by dr over d theta. So we have to perform this replacement. So if I were to take this as 2, therefore I can rewrite 2 as, in place of dr over d theta, I'm going to get negative r squared divided by dr over d theta is equal to negative tan n theta. Of course, this is going to become positive. R and R can be cancelled. This is going to be r times d theta over dr is equal to tan n theta. Now, I'm going to separate this by variable separable. So I would get d theta divided by tan n theta is equal to dr over r. Now this can be rewritten as, I need to integrate this. So sine theta or cos theta. When I flip it, it will be cos n theta divided by sine n theta times d theta is equal to dr over r. So we need to integrate this. So we will perform the integration in the following fashion. Now let me show you how to integrate this particular quantity. So I'm going to use this space here. So I got integral cos n theta divided by sine n theta times d theta. I'm going to retain or rewrite this as cot n theta d theta. Now let me take n theta to be equal to some u. So this one would be n times d theta is equal to du, and then my d theta is du over n. So I can rewrite this as 1 over n for d theta, and then I will have du there. So in place of d theta, I am writing du over n. So the n is placed over here. So followed by cot of n times theta is u. So this is what we have to integrate. I know the formula, but just for sake of understanding, I am going to be making a substitution. So this is 1 over n integral cot u is going to be cos u divided by sin u times du. I'm going to take, let sin u be equal to some p, so cos u du is dp. So this is going to be 1 over n, cos u du is dp, sin u is p, so this is going to be 1 over n ln p, which is 1 over n. My my p is nothing but sin u, but my u is nothing but n theta, right? So I need to revert it back. So this is going to be 1 over n ln of sin n theta. Of course, there's an arbitrary constancy. So all of this I did just to give you an air of understanding. So I can directly substitute this particular output here. So this is going to be 1 over n ln of sin n theta. This is going to give me ln r. Of course, there is an arbitrary constant which I will have to place in. I will write the arbitrary constant as some ln c. Now I want to get rid of this n, so I will have to multiply every quantity by n. So that would give me ln of sin n theta is equal to n times ln r positive n times ln c. Now there is a formula, a times ln b is ln b raised to the power of a. I can write that. So this is going to be ln sin n theta is equal to ln r raised to the power of n positive ln c raised to the power of n. Now this is an arbitrary constant, so I can actually place this as some entire c, but before that I will have to make some simplification. This is going to be ln c raised to the power of n, and this is going to be ln r power n minus ln sin n theta. This is what I get. Now there is a formula, ln of a negative ln of b is ln of a over b. So by this is going to be ln of r raised to the power of n divided by sin n theta. So this is what I got. Now this is ln, let me write that down, ln c raised to the power of n. Now I can remove ln both sides. So if I were to remove ln both sides, this would give me c raised to the power of n. This is some constant, and r raised to the power of n divided by sin n theta. Now what you can do, you can replace this by some k is equal to r raised to the power of n divided by sin n theta. Now I can rewrite this as r power n is equal to some k times sin n theta. So this is a beautiful curve, family of curves, and that is a good place for us to draw the red line. So this is a beautiful question, students. I hope you understood this. Thank you. Welcome, students. In this class we will be looking up to Clairaut's types of differential equations. Now this is actually a technique given by Alexis Clairaut to solve nonlinear differential equations of degree greater than 1. Now so far we were actually studying about solving differential equations of degree 1 and order 1. In other words, we can address them as differential equations of order 1 and degree 1. But in this type of differential equations, the degree will be greater than 1. So these types of differential equations are categorized as nonlinear differential equations. So we are going to look into ways by which we can solve. Now the form of Clairaut's type is given to be as y is equal to x times p positive f of p. Now this is the known form for Clairaut's type, and if you were to look into the value of p, in other words the value that p takes here is dy over dx. So this is a very important point you will have to know. Now what we are going to do is we are going to solve this type of differential equations. Now I'm going to take an example. Before I could take an example, I would like to mention that the Clairaut's type of equation produces two types of solutions. So one is called as the general solution, and you got the other solution. The other solution is called singular solution. Now for general solution, the value that you get is applicable for any system which falls into the Clairaut's type. Now singular solutions, they are applicable only for that particular problem that we are dealing with. Now the best way to understand is or I would say by means of an example. So let's get it started, by which you would be able to understand the solution. So to start off with, let me just give you this question. Solve y is equal to x times dy over dx positive dy over dx raised to the power of 2. So this is a differential equation. Clearly the degree is greater than 1. The degree here is 2. So we are expected to solve this. So foremost, the solution in this case would be, we would like to bring it to the Clairaut's type. So that is our objective. So what I will do is, I will say let dy over dx is equal to p. Now if I were to take this as 1, so therefore I can rewrite 1 to be as y is equal to x times p positive p squared. So this is what I have got. Now from here onwards, I would have to obtain two solutions. One is general and the other is singular. So I'll show you how to do it. So now having got this y is equal to xp positive p squared, what we will do is we will just differentiate this with respect to x both sides. So this is going to give me dy over dx is equal to uv method. Let me write that product rule. D of uv is equal to u times v dash positive v times u dash. So by applying the product rule, this is going to be x times, differentiating this is going to be dp over dx positive p times differentiation of x is 1 positive 2 times p times dp over dx. So this is what we have got. Now what I wish to do is, I would like to substitute in place of dy over dx p. So this is going to give me p is equal to, I can take dp over dx out, so this is going to give me x positive 2 times p. Already there is a p there. Now if I were to bring this p onto the left side, I will get p negative p is equal to dp over dx of x positive 2p. Now this is going to be 0. So 0 is equal to dp over dx of x positive 2p. So from here we get dp over dx is equal to 0. This is one possibility, or x positive 2p is equal to 0. So if x positive 2p is equal to 0, 2p is equal to negative x, so therefore p is equal to negative x over 2. So we have got this. Now from here I can rewrite dp is equal to 0. So integrating, when you integrate this, you get integral dp. This is going to be equal to 0. Now integral dp will be p positive c, but I would write that positive c as, if I were to push it to the other side, it's going to be negative c, but I can simply write that as some c. So p is equal to c is one solution, and I have got p is equal to negative x over 2. Now as I mentioned to you, there are two solutions. The given system is y is equal to xp positive p squared. This is the given system that we have obtained. Now for the general solution, what we substitute is, we substitute p is equal to c here, okay, to get the general solution. So if I do that, I get y is equal to x times c positive c squared. Now the reason that we call this a general solution, as I mentioned to you, that this is universally applied whenever we find a Clairaut's type. Whenever we are able to see a system which is Clairaut's type system, then we can simply substitute p is equal to c, and that would give us a general solution. But the singular solution, as I mentioned to you, that is little bit different. Now the objective of the singular solution is that what exactly we need to do is to eliminate p. That is the sole objective. So now we have got the system. We got y is equal to xp positive p squared. Now the singular solution is what? Since p is equal to negative x over 2, I will substitute here. If I were to take this as 2, so therefore 2 can be rewritten as y is equal to negative, since p is equal to negative x over 2, this is going to be x squared over 2 positive negative x over 2 raised to the power of 2. So I can rewrite this as negative x squared over 2 positive x squared over 4 is equal to y. Now if I were to multiply by, say if I were to take the LCM as 4, this is going to give me 2 times x squared positive x squared is equal to y. So y is equal to negative x squared over 4. So this is a solution. So I've got a general solution. Probably you can mark it as what? As 3, and you can mark this as 4. So clearly we can see 3 and 4 are the general solution and singular solution. So this is the completion for this particular question which we started. Okay, so we will move on to the next question. So as I mentioned to you, the more question we do, the better understanding we will get. Now let's do the second question. Now this is the question: find the general solution and singular solution of y negative x times dy over dx negative 1 over 4 times dy over dx raised to the power of 4 is equal to 0. Now what I'm going to do first thing is push all these terms to the other side. So I would now have y is equal to x times dy over dx positive 1 over 4 times dy over dx raised to the power of 4. Now let me just take p to be as dy over dx, and then I rewrite 2. So therefore 2 can be rewritten as y is equal to x times p positive 1 over 4 times p raised to the power of 4. Now this is actually in Clairaut form, so you can state that this is in Clairaut form. So since this is in Clairaut form, the first thing that I would like to do here is differentiating with respect to x both sides. So we get, so differentiation of y would give me dy over dx. This is product rule, d of uv is equal to u times v dash positive v times u dash. This is the formula I will be applying, so it's going to be x times dp over dx positive p times differential of x is 1 positive 1 over 4 times differentiation of p power 4 is 4 times p power 3 times differentiation of p, that's going to be dp over dx. So we got a dp over dx, so I would take dp over dx out, so it's going to be x. 4 can be cancelled. Since I've taken dp over dx out, I got an x here followed by p raised to the power of 3 followed by this positive p. But since dy over dx is taken to be as p, this is going to be p. So if I were to move this to the other side, you get p negative p is equal to dp over dx of x positive p cubed. So this is going to be 0. So 0 is equal to dp over dx of x positive p cubed. Now I'm going to use the space. So from here, this is actually dp over dx is equal to 0, or let me draw a line, or x positive p cubed is equal to 0. So from here p cubed is equal to
negative x, so p is equal to third root of negative x. So this is what you have got. So you will have to eliminate p using this third root of negative x. So this is acceptable. Now dp over dx is equal to 0, which means dp is equal to 0, which means p is equal to some constant c. So to get the general solution, what we are going to do is our Clairaut system is, so what is our Clairaut system? Y is equal to x times p positive 1 over 4 times p raised to the power of 4. So the general solution is substitute p is equal to c, right? So this is y is equal to c times x positive 1 over 4 times c raised to the power of 4. So this is my general solution. Probably I can box this. Now to get the singular solution, I need to substitute the value of p. Okay, so I'm going to give the singular solution over here. Okay, this is the singular solution. So I'm going to take p is equal to negative x raised to the power of 1 over 3. This is going to go. So therefore, if I were to take it as 3, therefore I can rewrite 3 as y is equal to x times negative x raised to the power of 1 over 3 positive 1 over 4 negative x raised to the power of 1 over 3, but this has got 4, so this is going to be rewritten as x times negative x raised to the power of 1 over 3 positive 1 over 4 times negative x raised to the power of 4 over 3. So this is my y. Now if in case if you want to simplify this, it can be done. So let me show you that. Now I'm going to use this space over here. Okay, so let me rewrite that. I got y is equal to x times negative x raised to the power of 1 over 3 positive 1 over 4 times negative x raised to the power of 4 over 3, right? Now I can rewrite 4 over 3 as 1 over 3 plus 1. You all agree with that, right? Now what we have got negative x raised to the power of 4 over 3. I'm going to rewrite this as negative x raised to the power of 1 over 3 positive 1. By the law of indices, a raised to the power of m positive n is a raised to the power of m times a raised to the power of n. By this property, this is going to be negative x raised to the power of 1 over 3 times negative x raised to the power of 1. Okay, so whenever you find negative x raised to the power of 4 over 3, we can substitute this. That's exactly what I'm going to do. So this is going to be x times negative x raised to the power of 1 over 3 positive 1 over 4 fine negative x raised to the power of 4 over 3. I'm going to rewrite it as negative x raised to the power of 1 over 3 times negative x raised to the power of 1. If I were to take negative x raised to the power of 1 over 3, this would give me x, and this would give me a negative x divided by 4. So let me use this space. So if I were to take the LCM, 4x negative x, that's going to give me 3x divided by 4, and that has to be multiplied with negative x raised to the power of 1 over 3 is equal to y. So this is what I've got. Now if in case if you are cross multiplying, so you would get 4 times y is equal to negative x raised to the power of 1 over 3 times 3x. So this is what you've got. Now if you plan to say get rid of this 3, what you should do. So let me use this space here. I know this is little bit effective utilization of the space, so please bear with me. So you got 4y is equal to negative x raised to the power of 1 over 3, and you got 3x, right? If you want to get rid of this 1 over 3, you cube both sides. So this is going to be 4 cubed y cubed negative x, and this is going to be 3x raised to the power of 3. This is going to give me 4 was a 1664 y cubed negative x. This is going to be 3 times 3 raised to the power of 3 is 927. I got a negative sign, and this is raised to the power of 3, and you got x there, so this is raised to the power of 4. So this is what you've got. But if you want to rewrite this further, you can rewrite this as 27x to the power of 4 positive 64y cubed is equal to 0. This is the singular solution. Now why did I do all these things? Because in case if you would have come across this in MCQ, and if you don't see this and you see only this, then you will have to do the process which I showed you, starting from here, following it up with this, and then directly coming to this point. So that would be a good place to stop for this particular question. Question number 3, students, sometimes the questions are straightforward. They would just simply give you y is equal to px positive a over p and ask you to find the general solution and the singular solution. This is a cakewalk. So first what you have to do is you will have to, this is already in clear outs type, so there isn't anything you need to do in this. So all you need to do is just differentiating with respect to x both sides. So when you do that, you get dy over dx is equal to, you are applying uv formula. This is the product rule. D of uv is equal to u times v dash positive v times u dash. So by this product rule, this is going to be p times the differential of x is 1, and x times differential of p is dp over dx positive. Now a is a constant, but p has to be differentiated. So if you differentiate that, you get negative 1 over p squared times dp over dx. Now since we have taken p is equal to dy over dx, I can rewrite this as p is equal to p positive. I'm going to take dp over dx out. If I do that, I get a x here, and then I get negative a over p squared. Now if you were to move this p to the left, I would get p negative p is equal to dp over dx of x negative a over p squared. This is going to be 0. So you get dp over dx of x negative a over p squared is equal to 0. So this would mean you get dp over dx is equal to 0, or x negative a over p squared is equal to 0. From here you get p is equal to c, and I can rewrite this as x is equal to a over p squared, and then subsequently p squared is equal to a over x. Then p is equal to root of a over x. So we got a p here and we got a p here. So the general solution, therefore the general solution is substitute p is equal to c in the system y is equal to p times x positive a over p. So if I do that, I get y is equal to c times x positive a over c. This is my general solution. Probably I should have used red to box this up. Now in the singular solution, we will have to get rid of the p. So the singular solution is, we need to substitute y is equal to, okay, so to get the singular solution, substitute p is equal to root of a over x in the above. So that would mean this is going to be y is equal to root of a over x times x positive a over root of a over x. So this is what we've got. Now I can rewrite this as root of a divided by root of x times root of x times root of x positive. This is going to be a. If I flip it, this is going to be root of x divided by root of a. This can be further rewritten as, clearly root of x can be cancelled. So I get root of a times root of x. However, I have a here, I'm going to write that a as root of a times root of a times root of x divided by root of a. I can also cancel this root of a. So that would give me root of a times root of x positive root of a times root of x. I can add these two things together to give 2 times root of a times root of x is equal to y. Now, if I were to square both sides, squaring both sides, we get, now this is going to give me y squared, this is going to give me 4. If I were to square root of a, that's going to give me a. Square root of x, that's going to give me x. So this is a beautiful singular solution. Y squared is equal to 4ax. So we can move on to the next question. Now we will move on to the next example. This is question number 4, students. We've been given p times y is equal to p squared of x negative b positive a. Now to convert, this is not in Clairaut's type clearly, so to convert this into Clairaut's type I would be dividing by p both sides. So when I do that I would get py divided by p is equal to p squared of x negative p divided by p positive a over p. So this can be rewritten as y, p and p can be cancelled, a p and a p can be cancelled. So we get y is equal to p times of x negative b positive a over b. So this is of Clairaut's type. So now what I wish to do is I would like to differentiate both sides with respect to x. Now why am I doing this? Because most times questions like this, they will give you this question and they will say find the general solution and the singular solution. So for that I need to differentiate both sides with reference to x. So if I do that, I get dy over dx is equal to, I'm going to apply the product rule, which is d of u times v is equal to u times v dash positive v times u dash. So by this product rule, this is going to be p times of, differentiation of x is 1, b is a constant, so don't need to worry. So followed by x negative b times differential of p is going to be dp over dx positive, a is a constant, differentiation of p 1 over p is going to be negative 1 over p square times dp over dx. So this is what we have got. Now since dy over dx is equal to p, this is going to be a p is equal to p positive. I'm going to take dp over dx out. If I were to do that, I get x negative b followed by a over p squared. Of course it has a negative sign. So this is what I've got. Now clearly p can be moved here. So if I were to move that, I would get p negative p is equal to dp over dx of x negative b followed by negative a over p squared. So this is going to be 0. Now let me use the space here. So now I've got dp over dx of x negative b negative a over p squared is equal to 0. So this means dp over dx is equal to 0. This is one side. Let me use the other side here. The other side is going to be x negative b negative a over p squared is equal to 0. So from here I get dp is equal to 0. Integrating both sides, I would get p is equal to c. So this is one part. This will produce the general solution. Over here I want to eliminate p, so I need to extract the value for p. So I can rewrite this as x negative b is equal to a over p squared. My p squared can be pushed to the left. That would give me p squared is equal to a over x negative b can be brought down. Now this is my p squared, so therefore I'm going to use the space here. So therefore my p is going to be square root of a over x negative b. So this will produce my singular solution. So now what I'm going to do is I'm going to use this particular space over here because of efficiency. So that would mean the efficient use of space management. Okay. So having mentioned this, so we have got the system. So this is the Clairaut system. So to obtain the general solution, so I can just say to obtain general solution, put p P is equal to C in, suppose I take this 2, so in 2. So therefore the general solution is y is equal to C times x negative b positive a over C. Probably I can place it in a box. Now to obtain the singular solution I need to use P is equal to square root of, so probably I can write that here. To obtain singular solution, put P is equal to root of a over x negative b in 2. So it's going to be y is equal to, so root of a over x negative b, that's my P here. There is already an x negative b there, positive a over root of a over x negative b. Now this is going to be interesting because I can rewrite this as root of a, x negative b I can rewrite it as x negative b times x negative b, of course there's a root there, divided by root of x negative b positive. Now I can flip this and rewrite it as root of x negative b. There is a there. I'm going to rewrite that a as root of a times root of a divided by root of a. Now clearly what we can do is we can cancel root of x negative b, root of x negative b, root of a, and subsequently we will get a solution. So what I wish to do is I would like to write that solution by using this particular space here. So therefore my y is equal to root of a times root of x negative b positive root of a times root of x negative b. So I can add these two things. So that would give me 2 times root of a times root of x negative b, right, is equal to y. Now squaring both sides, I would get y squared is equal to 4a times x negative b, right. So this is a beautiful solution, and this is a good place to stop. So we will move on to the next question. So this is the 5th question. We are expected to find the general solution and singular solution for y is equal to 2 times px positive p raised to the power of n. Now this is in clear out steps, so I would start off by stating that differentiating with respect to x both sides, we get differentiation of y is dy over dx. This is constant. Take it out. We will be applying v method, which is nothing but u times v dash positive v times u dash. So that's going to be differentiation of x, that's 1, positive x times differentiation of p, which is dp over dx. Differentiation of p raised to the power of n is going to be n times p raised to the power of n negative 1 times dp over dx. Now this is going to be 2 times p positive 2 times x times dp over dx positive n times p raised to the power of n minus 1 times dp over dx. On the left you get dy over dx, but my dy over dx is equal to p, so I can replace that. So p is equal to 2p positive 2 times x dp over dx positive n times p raised to the power of n minus 1 dp over dx. I can move this, it will become negative p. So what I would do is, still I will proceed. So p negative 2p is equal to, so I take dp over dx out, so this is going to be 2 times x positive n times p raised to the power of n minus 1. So this is going to be negative p is equal to dp over dx of 2x positive of np negative 1. So now we need to do some alterations and multiplications. So let's do that. So now what I would do is I would multiply both sides by dx over dp. Now if I were to do that, this is going to be giving me negative p times dx over dp. Dx over dp times dp over dx, they get neutralized, giving me 2 times x positive n times p raised to the power of
n negative 1. Now what I wish to do is I would like to place this thing on one side and move everything to the other side. So this is going to be negative p times dx over dp. Negative 2x is equal to n times p raised to the power of negative n, I would say p raised to the power of n negative 1. Now I don't want a negative sign present here, so what I will do, I will multiply by negative 1 throughout. So if I were to do that, this is going to be giving me p times dx over dp. Positive 2 times x is equal to negative n times p raised to the power of n minus 1. Now I want to get rid of this p, so dividing by p both sides, that would give me dx over dp positive 2 times x over p is equal to negative n times p raised to the power of n minus 1 divided by p. If it goes up, it will become n minus 2, right? So this is what I've got. Now this is a popular equation which can be solved. What is that? So this is, I hope you all remember, this is a linear differential equation with my value of p being equal to 2 over p and my q being equal to negative n times p raised to the power of n minus 2, and my integrating factor is e raised to the power of integral p. It's not dx here, it's dp. So this is going to be e raised to the power of integral. My p is 2 over p times dp, which is equal to e raised to the power of 2 times integral dp over p, which is e raised to the power of integral dp over p. This is going to give me ln p. I can rewrite this as e raised to the power of ln p squared. E and ln gets neutralized, giving me p squared. This is my integrating factor. So the solution in this case is going to be x times integrating factor is equal to integrating q times integrating factor. So it's going to be negative n times p raised to the power of n minus 2 times p squared times dp, right? So this is what you're going to get. So if you are going to integrate this, clearly you got a positive 2 and a negative, so that can be neutralized. So if you are going to be rewriting this, this is going to be integral n times p raised to the power of n negative 2 positive 2 times dp, which is equal to negative n integral p raised to the power of negative 2 positive 2 gets cancelled, so you got p raised to the power of n times dp, which is going to be negative n times, if you integrate this you get p raised to the power of n positive 1 divided by n positive 1. Of course you got the positive constant c. On the left you got x times p squared, so you can rewrite that x times p squared is equal to negative n p raised to the power of n positive 1 divided by n positive 1, positive arbitrary constant. Now we can clearly extract x from here, so what I wish to do is I would use this space here. So from here x is equal to, I push this p squared down, so you get negative n p raised to the power of n positive 1 divided by n positive 1 times p squared positive c over p squared. Now you can push it up. If you were to push it to the numerator, let me use this space here. I would need all of this probably. So I'm going to get x is equal to negative n times, if I were to move this p to the numerator, it is going to be p raised to the power of negative 2 divided by n positive 1 positive c times p raised to the power of negative 2. Now this can be further rewritten as negative n times p raised to the power of n positive 1 negative 2 divided by n positive 1 positive c times p raised to the power of negative 2. On the left I've got x. This can be further rewritten as negative n p raised to the power of n positive 1 negative 2. That's going to be n negative 1 divided by n positive 1 positive c times p raised to the power of negative 2 is equal to x. So you've got an expansion or an expression for n, I should say for x. So what we can do is we can substitute this in the system. So we have the Clairaut system as y is equal to 2 times px positive p raised to the power of n, right? We started here with that, right? So what we can do is we can take the value of x and substitute here. So hence if I were to take this as say initially I'm taking it as 1, so therefore 1 can be rewritten with x, right? So y is equal to 2 times p of x. I start with cp raised to the power of negative 2 followed by negative sign and p raised to the power of n negative 1 divided by n positive 1 positive p raised to the power of n. So this is the system. Probably you can multiply and remove the parenthesis. So this would give me 2 times c times p raised to the power of negative 2 times p, that's going to be positive 1, negative 2 times p raised to the power of n minus 1, positive 1, right? P is coming inside, divided by n positive 1, positive p raised to the power of n. So this can be further rewritten as 2 times c p raised to the power of negative 1, negative 2 times p raised to the power of negative 1, positive 1 will give me n, divided by n positive 1 positive p raised to the power of n. However, you can stop here. This is a good place to stop. And on the left hand side you get y. So this is a solution, a general solution for the given Clairaut's form equation. And that is a good place to wrap up this topic. Thank you, students. Welcome students. In this class we will be learning how to handle a special type of differential equation which goes by the name Riccati. Now foremost, let us have a brief review of whatever we have done. Now we started off learning what is called as the standard ordinary differential equation. The form is dy over dx positive p times y is equal to q, where p comma q are functions of x, right? So this is the first type we studied. Now we also got exposed to what is called as the Bernoulli's ODE. Now the form of this Bernoulli ODE was dy over dx positive p times y is equal to q times y raised to the power of n. And the values of n was higher than 1. So in other words, the n cannot take the value 0 or 1. So have that in mind. So this is Bernoulli's. Now, having studied the Bernoulli, now there is a special type, the third type, which is called as Riccati ODE. Now the form is dy over dx positive p times y is equal to q times y squared positive r, where p comma q comma r are functions of x. Now the same thing goes here. P comma q are functions of x, right? So we are looking to solve the differential equation of this type. And why is it called Riccati's equation? Because this method is originated by the person's name. Probably many are involved in its outcome, we don't know, so we know how to solve it. So whoever has given us this great method, we respect them and we give them our gratitude of thankfulness. So having mentioned this, let me just start off. The Riccati equation. When I say equation, it's a differential equation, right? So let me state that the Riccati differential equation is of the form dy over dx is equal to, you can either write p of x or simply py q times y squared plus r. So this is the standard form that we would be using. Of course, you can state here p, q, r are functions of x. So always remember, this is the pattern, or this is the form we will be comparing any given equation to. Now suppose we are given, say, I'm giving you an example, say for example dy over dx is equal to, say, sum x squared y positive sum x cubed y squared positive sum x to the power of 4. Now this is a Riccati differential equation, and clearly our p of x is x squared and q of x is x to the power of 3 and our r of x is equal to x to the power of 4. So it's just an illustration, right? So now we have to look into the method to apply this method of obtaining the solution. How do we obtain the solution? Foremost, this is the step we will be following. Step 1, y1 is given, right? y1 is given to be the particular solution. This is the term we will use. Now when this happens, we follow the step 2. What is step 2? We put y to be as v plus y1, some v. So v is also a function, some function of x, right? So I will show you how to do this, but for now just take the steps. Put y is equal to v positive y1 in the given question. Next, step number 3 is simplify, and you can either say simplify or you reduce. The system will get reduced to Bernoulli type. Okay, Bernoulli's type of ODE, from where the system is solvable. System is solved. That's all. Step 1, step 2, step 3. I know it is a little bit confusing. It might be a little bit confusing because of the nature of the type, Riccati equation type, but as I always mention, examples will clear any element of doubt. So let's do some examples. Students, we're given this question. Solve the following Riccati equation given that dy over dx is equal to negative 1 over x times y positive y squared followed by a negative 1 over x squared, given that y1 is equal to 1 over x is a solution. Now I'm going to show you that it is indeed that y1 is equal to 1 over x is the solution for this particular equation, but this is not part of the solution to this question. This is just for your understanding. Now y1 is equal to 1 over x, so let me use the space here, right? So dy1 over dx is equal to negative 1 over x squared, right? So I'm going to rewrite this as dy1 divided by dx is equal to negative 1 over x times y1 positive y1 squared negative 1 over x squared, which is equal to y1 is 1 over x, so it's going to be 1 over x times 1 over x positive 1 over x, it's raised to the power of 2, so it's going to be 1 over x squared followed by negative 1 over x squared. So positive 1 over x squared negative 1 over x squared gets cancelled, giving me on the right hand side negative 1 over x squared, on the left hand side dy1 over x. But what is dy1 over x? Negative 1 over x squared. So clearly left hand side is equal to right hand side, which means that y1 is equal to 1 over x is a solution indeed. So that is just for your understanding. Now according to our step, just let us go to the way in which we need to solve. If y1 is given to be a solution, then we take y to be equal to v positive y1. So this is the start of the solution. The solution is, let y be equal to v positive y1, right? Now what we are going to do from here, we will actually, now since y1 is 1 over x, this is nothing but v positive 1 over x. So therefore we got y to be equal to v positive 1 over x. Now if I were to differentiate both sides, differentiating with respect to x both sides, we need to do that, right? Because we got dy over dx. This is going to be dy over dx is equal to differential of v. V is some function of x, so it's going to be v dash positive. Now 1 over x differentiation is going to give me negative 1 over x squared. So this is for dy over dx. Now what I'm going to do is, I'm going to take this as 1, using this in 1 we rewrite, okay, we rewrite 1 as, in place of dy over dx, I'm going to substitute this. So it's going to be v dash negative 1 over x squared is equal to negative 1 over x. In place of y, I'm going to substitute v positive 1 over x. That's what I'm going to do. So followed by v positive 1 over x raised to the power of 2, and then negative 1 over x squared. Now clearly negative 1 over x squared, negative 1 over x squared can be cancelled, so I get v1 is equal to, now this can be simplified by distributive property, so take out the parenthesis, so it's going to be v over x with a negative sign, negative 1 over x squared. I expand this, I get v squared positive 2 times v over x positive 1 over x squared, negative 1 over x squared positive 1 over x squared can be cancelled. So I get v over x with a negative sign and 2v over x. So if I were to take v over x out, this is negative 1 positive 2 and positive v squared, and on the left side I got v dash. So negative 1 positive 2, this can be rewritten as v dash is equal to v over x positive v squared. Now what I'm going to do, I'm going to move this guy to the left hand side. So I get v dash negative v over x is equal to v squared. Now since v is a function of x, I can rewrite this as dv over dx negative 1 over x times v is equal to v squared. Now is this similar or to what we have studied? Yes, this is v squared on the right hand side. So this is nothing but, this is Bernoulli's equation, Bernoulli's ODE, which can be solved. I can easily solve this. Now how do I solve it? I divide by v squared. So when I divide by v squared, this is going to be v raised to the power of negative 2 dv over dx negative 1 over x. I get a v here, but I want to write the v as v power minus 1, which is equal to 1. Fair enough. Now we are going to be making some substitution, so we need to go to a new space, a new page. So we are on a new beautiful page, and we got v raised to the power of negative 2 dv over dx negative 1 over x times v power negative 1 is equal to 1. So this is what we've got. Probably we can name it as 2. Now what I'm going to do is I'm going to take, let v raised to the power of negative 1 be equal to some z. I differentiate, I get v power minus 2 dv over dx is equal to dz over dx. So I'm going to use this, right? So therefore I can rewrite to, in place of v raised to the power of negative 2 dv over dx, I'm going to substitute dz over dx negative 1 over x. In place of v power minus 1, it's going to be z is equal to 1. So this is a beautiful system. We have got, because when you differentiate v power minus 1, we will have a negative sign here, so that is important. So if you miss a negative sign, it would be problematic. So we can rewrite this as dz over dx is followed by a positive 1 over x times z is equal to negative 1. Now what is this? This is nothing but a linear differential equation, right? With the integrating factor is e raised to the power of integral p dx, which is equal to e raised to the power of integral, my p is 1 over x times dx, which is equal to e raised to the power of integral dx over x, which has nothing but e raised to the power of ln x. E and ln gets cancelled, giving me x. So consider now integral q times e raised to the power of integral p dx times dx, positive c, right? That's going to be there, but we can add it at the later stage. So it's going to be integral negative 1 times x times dx, which is negative x times dx, which is negative x squared over 2, positive arbitrary constant c. So therefore, if we are going to be writing this, this is in z. So the solution is going to be z times x is equal to negative x squared over 2 positive c, right? This is what we've got. But my z is v power minus 1, so we have to take care of that. So we know that, I want to state that we know that v power negative 1 is equal to z. So therefore, if I'm going to use this, this is going to be, hence we now have, in place of z, it's going to be v raised to the power of negative 1 times x is equal to negative x squared over 2 positive c. I can move this x down, so that would mean I get v power minus 1 is equal to negative x over 2, because x is coming down, positive c over x. So now what we can do is take an LCM of 2 times x. So this is going to be negative x squared positive, x and x cancel, so this is going to be 2c. So I can rewrite this as 2c negative x squared divided by 2x. So this is my v raised to the power of negative 1. Now if v raised to the power of negative 1 is this, so what would be v? So therefore my v is, just revert everything. So this is going to be 2x over 2 times c negative x squared. So I can rewrite this as 2x over, now 2c is a constant, so I'm going to replace it as some capital C negative x squared. So this is my v. But we know that, we started off, what did we started off? We started off by assuming y is equal to v positive 1 over x. Okay, so this would mean in place of v, I would substitute 2x over c negative x squared positive 1 over x, which is the required solution to the Riccati equation, right? So we have achieved this solution. So we will move on to the next question, students. Students, we are given this question: y dash positive 1 over x times y negative 1 over x cubed times y squared is equal to 2x. This is a Riccati differential equation. And it is given that y1 is equal to x squared is a particular solution, and we are expected to solve this. Now to start off, I would like to show it to you that y1 is equal to x squared is indeed a solution for this. Now clearly y1 dash is equal to 2 times x, so I can rewrite this as y1 dash. This is not part of the solution, but this is just for your understanding. So that has to be followed by positive y1 over x negative y1 squared over x to the power of 3 is equal to 2 times x. Now y1 dash is 2x, y1 is x squared, this has to be divided by x, followed by y1 is x squared, but that has to be raised to the power of 2, so it's going to be 4 here, divided by x cubed. This has to produce 2x.
So now I can just cancel x and x. I can cancel this. Now I got an x here and I got an x here, so both of them they get cancelled. So I get a 2x on the right, on the left, and 2x on the right. So clearly y1 is equal to x squared is a solution indeed. So this is just to show you that fact. Now step 1. So let us start the solution. So what we are going to do is we are going to take y to be equal to some v positive y1. Now why am I taking this? You might be asking, why are you taking this? Now this is a guessed solution which has been arrived over years of hard work by great people. That's the best answer I can give you. So having mentioned that, this can be rewritten as v positive. In place of y1 I'm going to say x squared. So therefore I got y to be equal to v positive x squared. Now from here y dash is going to be v dash positive 2 times x. So if I were to take this as 1, using this I can rewrite 1 to be as the following. So in place of y dash, this is going to come in. So this is going to be v dash positive 2 times x, and positive, my y is v positive x squared divided by x, that's fine, negative, my y is v positive x squared, that has to be raised to the power of 2 divided by x to the power of 3 is equal to 2x. So we need to do some simplification over here. So I can rewrite this as v dash positive 2 times x, positive v over x, positive x squared over x will give me x, and this one I need to expand this. So this is going to give me v squared positive 2 times v times x squared positive x to the power of 4. This entire thing has to be divided by x cubed, x cubed, x cubed. This is equal to 2 times x. So I can rewrite this further as v dash positive 2 times x, positive v over x, positive x, negative v squared over x cubed, negative 2 times v. I can cancel x squared and a x, so I get a x here. So followed by negative x is equal to 2 times x. So negative x, positive x can be cancelled, and of course 2x and 2x can be cancelled. So I got a quantity of this fashion. So what I'm going to do, I want to push this guy to the right hand side, so I get a v squared over x cubed. So that is fair enough. And then I want to add these two things. So if I want to add these two things, I would get a negative v over x. That is fair enough, followed by v dash. So I've taken care of all these quantities. Now I would like to rewrite this by using the space. So it's going to be dv over dx, negative 1 over x times v is equal to v squared over x to the power of 3. This is what we have got. Now what I want to do is I will have to get rid of this v squared, because this is I want to achieve in fact the linear differential type, because this is of Bernoulli type. Okay, from Bernoulli we have to convert this into linear differential equation. So to achieve that, so that I can extract integrating factor, so I'm going to divide by v squared throughout. So if I do that, I get v raised to the power of negative 2 times dv over dx. This is v raised to the power of negative 1 divided by x is equal to 1 over x to the power of 3. Fair enough. So now let us make the substitution. Now let me say let z be equal to v raised to the power of negative 1, and I differentiate this. dz over dx is equal to negative, because of the differentiation of v raised to the power of negative 1. So this is going to give me negative followed by v raised to the power of negative 2 dv over dx. So instead of this I will be substituting this. So therefore probably I can write it down here. So v raised to the power of negative 2 dv over dx is equal to negative dz over dx. So if I were to take this as 2, therefore I can rewrite 2 as negative dz over dx followed by negative sign. V power minus 1 is z over x is equal to 1 over x to the power of 3. I can move the negative sign to the other side, so this is going to be dz over dx positive z over x is equal to negative 1 over x to the power of 3. So this is what I've got. So now the important property is to find the integrating factor. So therefore integrating factor is e raised to the power of integral p dx. So what is the coefficient of z? It's 1 over x. So substitute that. Let me do that here. Which is equal to e raised to the power of integral dx over x, which is equal to e raised to the power of ln x, which is equal to x. So my integrating factor is achieved. So therefore consider integrating q times e raised to the power of integral p dx times dx, which is integral dx. In fact, I should have started with writing negative 1 over x to the power of 3 times x times dx, so that this is equal to negative x to the power of negative 2 times dx, right? I can easily cancel this x with the x present there, so that would leave me with x squared, so I can push it up to the numerator. So that's going to be negative x to the power of negative 2 positive 1 divided by negative 2 positive 1, which can be rewritten as negative x power negative 1 divided by negative 1. I can push this, negative will become positive, so this is going to be 1 over x, positive arbitrary constant c. This is for q. Now the solution, so let me use this space over here for the time being. So we started with z, right? So the solution is going to be z times integrating factor is x is equal to the output that we have got here is 1 over x positive c. I want only if I want to get rid of this x, I can push it down, so I get z is equal to 1 over x squared positive c over x. If I want to take the LCM as x squared, I can take the LCM as x squared. There's no harm in that. So if x squared is the LCM, this is going to give me 1 positive c times x. This is z, but what is z? We have taken z to be at v negative 1, v raised to the power of negative 1. So we replace that. So this is going to be v raised to the power of negative 1 is equal to 1 positive cx over x squared. So this is v raised to the power of negative 1. So therefore v will be x squared divided by 1 positive c times x. So this is for v. But we started with this thing. Okay, so probably I will place this as 1 prime. So I need to take the value of v and substitute in 1 prime to get the solution. Therefore the solution, I'm writing it down here, the solution is y, let me show that to you, y is equal to x squared positive 1 positive cx positive x squared. So this is the solution. Probably I can box this using a red. So this is the complete solution for this question, students. We will move on to the next question. Students, we are given this question, y dash positive 2 times xy is equal to 1 positive x squared positive y squared, given that y1 is equal to x is a solution. Now we will start off with the quest to obtain the solution. So what I will do is, since y1 is equal to x is a solution given, I'm going to take y to be equal to v positive y1, and this would imply that y is equal to v positive x. So if you were to differentiate this, differentiating with respect to x both sides will give me, so this is going to be y dash is equal to v dash positive differential of x is 1. So if I were to take this as 1, therefore 1 can be rewritten as, in place of y dash I will substitute v dash positive 1 positive 2 times x. In place of y, I'll substitute v positive x is equal to 1 positive x squared. In place of y, I'll substitute v positive x raised to the power of 2. I expand this, I get v dash positive 1 positive 2 times x v positive 2x squared is equal to 1 positive x squared positive v squared positive 2xv positive x squared. I add x squared with x squared, and then I rewrite this as 1 positive v squared positive 2xv positive 2 times x squared. On the left I got a v dash positive 1 positive 2xv positive 2x squared. Now clearly 2x squared 2xv 2xv can be cancelled, and then I get a plus 1 and a plus 1, they also can be cancelled. So I get v dash is equal to v squared. This is what I get. Now I am going to write v dash as dv over dx, and this is equal to v squared. Now this is variable separable, right? So this can be rewritten as dv over v squared is equal to dx, and integrating both sides, this can be rewritten as v raised to the power of negative 2 times dv is equal to integral dx. So if I were to integrate this is v raised to the power of negative 2 positive 1 divided by negative 2 positive 1 is equal to x. Of course, there's an arbitrary constant c. I'm going to use this space. So v power minus 1 divided by minus 1 is equal to x positive c. If I were to bring this v power minus 1 down, this is going to be negative 1 over v is equal to x positive c. But I can have to, in other words, I need to get the value of v, right, not 1 over v. So if I were to multiply by v both sides, I would get negative 1 is equal to v times of x positive c. So from here v is 1 over x positive c with a negative sign. So I got the value of v. So what I'm going to do, I'm going to take this value of v and substitute it here. So if I were to take this as 2, therefore 2 can be rewritten as y is equal to negative 1 over x positive c positive x is the required solution. So this is a simple question and it's been solved beautifully. We move on to the next illustration. Students, we are expected to solve this Riccati equation given that y dash is equal to y squared negative of 2x negative 1 of y positive x squared negative x positive 1, given that y1 is equal to x. So to start off with the solution, we've been given y1 is equal to x is the solution. So I'm going to just take, let y to be equal to v positive y1. So this would mean my y is equal to v positive x. So I'm going to be differentiating both sides with respect to x. So this would give me y dash is equal to v dash positive differentiation of x is going to give me 1. So if I were to take this as 1, therefore 1 can be rewritten. In place of y dash I would be substituting v dash positive 1. In place of y it's going to be v positive x. The degree is 2, so place that, followed by 2x negative 1 times y is v positive x. Positive x squared negative x positive 1. So we will expand this. This is v squared positive 2 times x v positive x squared negative, I want to use distributive law here. So this is going to be 2 times x v positive 2 times x squared negative v negative x positive x squared negative x positive 1. This is v squared positive 2 times xv positive x squared. I'm removing the parenthesis, so this is going to be negative 2 times xv negative 2 times x squared positive v positive x squared negative x positive 1. On the left it's v dash positive 1. So let us see what we can get rid of. So clearly we can see that negative 2x squared, positive x squared, positive x squared can be cancelled. Positive x, negative x can be cancelled. Positive 1 can be cancelled. So we got positive 2xv, negative 2xv. This is also cancelled. So I get a v squared, and then I got a v, and then I got a v dash. So now what we can do is I'm going to bring this v to this end. So let me make sure that I've got rid of everything. So this is going to be v dash negative v is equal to v squared. So I'm going to rewrite v dash as dv over dx negative v is equal to v squared. So this is Bernoulli type, so I will be dividing by v squared both sides. So when I do that, I would get v power minus 2 dv over dx negative v power negative 1 is equal to 1. So now what I wish to do is I would like to take v power minus 1 is equal to z. If I differentiate this, this is going to be negative v raised to the power of minus 2 dv over dx is equal to dz over dx. I need only positive sides, so v power minus 2 dv over dx is equal to negative dz over dx. So this is the substitution that would go here. So if I were to take this as 2, therefore I can rewrite 2 as, in place of this I get negative dz over dx followed by a negative sine v power minus 1 is z is equal to 1. I want to multiply by negative 1 throughout so that I can have a positive. So this is going to be dz over dx positive z is equal to negative 1. So the coefficient, so therefore the integrating factor is e raised to the power of integral p dx. My p is 1, so this is e raised to the power of integral dx, which is nothing but e raised to the power of x. So this is what I've got. So therefore integral q times e raised to the power of integral p dx is equal to integral, my q is negative 1 times e raised to the power of x times dx is negative e raised to the power of x times dx, which is e raised to the power of x positive c. So therefore if you are going to write the solution is z times my integrating factor, which is e raised to the power of x, is equal to negative e raised to the power of x positive c. I need only z, so my z is negative e power x divided by e power x positive c times e raised to the power of x. This can be cancelled, giving me negative 1 positive. I'm going to write this as c times e raised to the power of negative x is equal to z, but my z is v power minus 1, right? So if we were to substitute here, so this is going to be v power minus 1 is equal to negative 1 positive c times e raised to the power of negative x. So I need my v. So this is 1 over v is equal to negative 1 positive c times e raised to the power of negative x. So if I were to extract only v, I will have to push everything down. So this is going to be, if I were to club this as one component, so this is going to be 1 over negative 1 positive c times e raised to the power of negative x. This is going to be equal to my v, right? So I need to use this and substitute it here. So if I were to take it as, say, some 1 prime 1 dash, so let me just use this space here. So therefore my 1 dash, which I started as y is equal to v positive x, in fact I am going to take this as 1 dash, right? So let me just show it to you. This should be my 1 prime. I'm going to take this as my 1 prime. So therefore my 1 prime, which is y is equal to v positive x, can be rewritten as, is now, in place of v, I'm going to substitute this. So it's going to be y is equal to 1 over c times e raised to the power of negative x negative 1 positive x. So this is going to be my solution,
Just a quick note here, if you're not happy with this could be rewritten as 1 over, now e power minus x can be written as c over e raised to the power of x negative 1. Of course this follows. Now if you were to take the LCM as e power x, this is going to be 1 over c negative e power x divided by e power x positive x. So if you were to flip this is going to be e raised to the power of x divided by c negative e raised to the power of x positive x, which is equal to y. So this would be my general solution, right? So you can either stop here or you can stop here depending on the requirement. Thank you students, I hope you enjoyed today's class. This completes our study on Riccati's differential equation.